Hello everybody, hope you're doing okay. In this video we're going to be doing all of circular motion that you will be seeing in your A-level physics. So let's get into it. So the first thing we want to do is we want to build some intuition for what circular motion even is. And the way we're going to do that is we're first going to learn what causes a circular motion. When do you have a circular motion? So if you have centripetal force, you will have circular motion. This is the cause of your circular motion. Now, what is centripetal force? It's easy to say that word, but it's much more nuanced when it comes to the understanding. So centripetal force is basically a force that is acting towards the center of a body that's moving in a circle. So it's basically, you can say a net force or a resultant force that's acting towards the center. So it's a net force acting towards the center, towards the center. Now let's look at some examples, try and understand what this really means. So let's say I'm going to take the easiest example because we've all somehow done that in our daily lives. And it's the example of when you have a rope and you attach an object at the end of that rope, and then you have it in your hand and you're just like spinning it around. So that is what a circular motion is, because that, if you look at that particle, let's say, or that object, you have, let's say, your hand over here. So you have your hand and you have a rope coming out of your hand, and let's say there's an object at the end of this rope. What you're doing is you're spinning it around in a circle. So you're spinning it around vertically in a circle. So then this is sort of what the motion, this is what the motion looks like. And if you think about it, there are some forces that are acting towards the center, this as this object is sort of going around the circular path. I'm not going to talk about what those forces are right now, but I'm just telling you guys that this is one example of circular motion. Another example would be, for example, when you have the sun. So you have the sun over here, this is the sun, and then you have the earth over here, and it's going around a circular path in an orbit around the sun. So that is also an example of circular motion. Now, what else would be an example of a circular motion? So if you guys have done chemistry or maybe particle physics, what you guys may have learned that for the old model of the atom at least, there's a nucleus in the center of an atom, and that nucleus has two kind of particles, positive particles and negative particles. So the positive particles are what we call the protons. So I'm going to draw the protons right now. And then of course there are neutral particles as well, but they have no charge, so we can ignore them. And there's these electrons that are spinning around the nucleus. So these electrons are negatively charged particles, and they're sort of spinning around the nucleus. I can just draw one electron over here. So this electron would be spinning around the nucleus, and I can sort of draw one proton over here. So this would also be an example of circular motion, where you have an electron sort of spinning around the, what do you call it, the nucleus on its own. And then one example would be when you're doing donuts with a car. Essentially what you're doing is, let's say, this would right here would be a car, somewhat like this, and you're doing donuts with it. So when you're doing a donut with a car, you're basically sort of going around some center. Okay, so you're sort of making circular motion. You're doing a circular motion, or you're doing donuts like this. So we can say there's some center point around which you're doing the donuts, and so you're in a circular motion. It has a center point, and around that center point you're doing a donut. So all of these would be examples of circular motion. And I'm trying to think of more examples. Of course, there's also an example of the plane. So when a plane is sort of flying and it wants to sort of take a turn, what it does, it sort of rotates itself like this, it tilts itself like this, and then it sort of does something like this where it does that. So if this is the airplane, hold on, I have a trying to look for an object I can show you guys. So show you guys what the circular motion of a plane would look like. So I have, imagine this is a plane, right? And when it wants to turn around, let's say it wants to turn around this point. So it doesn't turn around that point like this. In fact, what it does is it sort of tilts itself like this, and then it sort of does a circular motion like this. So for the plane, let's say this right here would be an airplane. So this would be its wing, and this would be its body, and this would be its other wing, and its tail would sort of be going up like this. So that would be the tail of the plane. And then this plane would sort of be doing a circular motion like this around some circular path. So that would somewhere be the center in the sky, and then it would sort of be doing a circular motion, or would be doing a circular movement around that center in the sky. Okay, what else do we have? Other examples. So you have something called a banked road. I don't know if you guys have noticed this or not, but yeah, this isn't that common. But what you have is sometimes you have a tilted road. So you have a road that looks something like this. You have a road that looks. I'm trying to. Uh, I'm going to do a really bad job at drawing this road, but it's sort of something like this. And imagine you're looking at it from the top. So it's sort of going. It's sort of. It's like this cone. It's this cone, and so you sort of have you have a bottom point over here, and it's going sort of down like this from all sides, sort of going down into that cone. And you can have your car or your bike maybe over here going around this circle. And of course, since this is a banked road, you have straight sides over here. It's something like that. I'm not going to be doing this justice, but it's something like that, and it's something like that. Yeah, I did a really bad description of this bank road. But anyways, from these other examples, you can sort of understand what circular motion is. And we just went over this idea that a circular motion happens when you have a centripetal force. A force, what is a centripetal force? It's a net force that is acting towards the center of a circular path. So that's what we're going to be looking at in all of these examples, is that they all are going to have that centripetal force, or that net force that acts towards the center. That's the reason why there exists the circular motion for all of these examples in the first place. So let's look at them one by one. Now, if you look at this ball, or this object, so we look at this first example, what you're doing is you have a rope in your hand and you're spinning the object around uh, a circular vertical path. So what you're doing is you're pulling it with a rope. There's tension in the rope. That rope is what provides the centripetal force. Or what did we really say a centripetal force was? It was a net force that acts towards the center. So if you think about it, if I draw the free body diagram of this object being swung around by a rope, well, of course, there's going to be that tension force over here due to that rope that is acting towards the center. And remember, your hand is the center, so your hand is the center point. That is the tension force. Now, if I'm talking about this ball being at that top position, that vertical position up top, it also has its weight acting downwards. So it has its weight mg, or w if you want to call it that. It's acting downwards towards your hand. So you have essentially two forces that are acting towards the center. So those two forces, again, what is the centripetal force? Centripetal force is the net force that act towards the center. So if I just make an equation for the net force in this particular situation, so Fn is the net force, or it's also called the resultant force. Some of you may call it Rf. If you want to find the Rf or the F net, what you can sort of do is you can realize that it would be this tension force plus this weight. So F net is this tension force that's acting towards the center, and this weight acting towards the center. You add them up, and then you get this new force that's acting towards the center, and that new force is basically what your centripetal force is. So it's essentially the magnitude of this tension force plus this weight force. Whenever, let's say this tension force is 16 newtons, and this weight is 14 newtons, then your F net will just be 16 plus 14, and whatever this gives you. So for this, no, my mental math is really bad. I'll just do it over here. 14 plus 16, so this would be 10, and this would be 3. So you would have 30 newtons as your net force. And again, this net force, we give it a special name in the case of circular movements. When circular movements are happening, we call the net force centripetal force. We give it a special name. So over here, this net force is what your centripetal force is. It's going to be of 30 newtons. Now, of course, as this object moves in the circle, the situation changes. For example, if I just bring it over here at the bottom, so if I just bring it over here at the bottom, what you can sort of see is now the net force, or the centripetal force, will have a different value. The way you can find that out is you can essentially do the same thing again. So F net, first you make the free body diagrams. Free body diagrams are really important when you're doing circular motion problems. That's how you will understand what's going on. So tension is acting over here in this direction. Tension always acts towards your hand. And then, of course, the weight acts downwards, so the weight is going to go in that direction. So it's going to be W in the downward direction. So now the F net is going to be the tension minus the weight. Okay, now you guys may be thinking about, how do I know if I'm supposed to subtract the weight from the tension or the tension from the weight? See, I'm subtracting the stronger force from the weaker force. So the way I know I'm supposed to subtract weight from the tension is because I know the object or the body is in a circular motion. Now here's the thing. If it was not in a circular motion, it wouldn't, so try and understand it like this. If you're in a circular motion, you have to have some amount of force that's acting towards the center. Now, if tension if tension was smaller than weight, what would happen is that this would give me, tension minus weight would give me a negative answer. And what would that mean? That would basically mean that this weight right over here is the stronger force. It has a greater magnitude than that tension. Now here's the problem. If you have, so then this weight the overall net force would be acting downwards in the direction of weight, not in the direction of the center. So if that would happen, basically this definition that we just set for circular motion is we said that the net force is a force that should be acting towards the center. If weight is stronger, if weight is the stronger force, then what happens is you get a net force that acts away from the center. If that's happening, then you don't have a circular motion anymore, because that's what circular motion is. You have a net force that acts towards the center. Therefore, if you have a force, a net force that is acting away from the center, you don't even have a circular motion in the first place. So that's how I know that I have to subtract weight from the tension. Why? Because I know tension is the stronger force. If tension was not the stronger force, I would not have a circular motion. I'm assuming that I have a circular motion. When I assume that, what I can say is I can say that tension is greater than weight, and so I can put T minus W. Now, if somehow, let's say my assumption was wrong and I did end up getting a negative answer, what would that mean? That means tension is smaller than weight. That would mean this is true. Tension is smaller than weight. What would this imply? This would imply that I will have a net force that acts away. This negative answer would just tell me that weight is the stronger force, and therefore the net force must act in the direction of the weight. And therefore, if it acts away from the center, or if it acts in the direction of the weight, I don't have a centripetal motion in the first place. Because in order for me to have a centripetal motion, I need a centripetal force that acts towards the center. So that's why I put T minus W and not the other way around. So let's say if W was the stronger force and I put W minus T, then this means that this net force is not my centripetal force. It's going to be acting away from the center. I would not be calling it my centripetal force. So I would not give it that special name. Now, in a different example, let's say I take the rope all the way to this point. So I'm spinning it and I sort of pause my time at this instant. So over here, you can sort of see that this right here is the force that would be acting towards the center. Again, this is the tension force, and then the weight is acting downwards. So the weight is acting downwards. In this case, when you sort of do the F net thing so you have essentially you have two directions right now. So you have this upwards direction, this direction, the up down direction, and then you have towards the center and away from the center direction. So you can say you have the up down, which we can call force, or we can call the Y direction. So Y direction. And then we have this other direction, which we can call the center direction. So what I want you guys to sort of understand is that if you look at the center direction, your F net will simply just be equal to the tension force, because there is no other forces that are acting in the center direction. There's no force that's acting away from the center, no force that's acting towards the center along with tension. So there's just that tension force that's acting in the center direction. So if you're sort of making equations for the center direction, then your centripetal force or your net force would just be F net is equal to tension. There are no other forces to take into account. However, if you're talking about the Y direction, what happens is that you will get a different equation. So you will get maybe the equation, let's call it, you would just get F net equals W, because there are no other forces that are either pulling this object up in the Y direction or that are pulling this object down in the Y direction along with that weight. So in this particular case, your F net, so this center direction is where you get your net force from. So that you can call this net force, you can give it that special name, which we were calling the centripetal force. So I'm going to write FC, and you can say that the FC is being provided by the tension force. Now, we were not going to consider the Y direction for the centripetal force because, again, centripetal force is the net force that acts towards the center. That weight is not involved in that center direction in this case. It's involved in the vertical direction in this case. So it doesn't contribute to the centripetal force. Okay. Same goes for when you have this object on this side. So if I erase it from here and I draw it over here in the other direction, this is where you would have your tension, and then the weight would be acting downwards. So the weight would be acting downwards. Okay, so those are just some ideas for centripetal motion in this particular example of a rope and an object. Now, one thing that you will notice in all of these examples is that the velocity in all of these circular motions has to be tangential to the path. What does that mean? So that means if, let's say, this ball is sort of moving in this way, which is the anti-clockwise direction, at every point, its velocity will be here. So over here, its velocity will be here. When it reaches this point, its velocity will be over here. And then when it reaches this point, its velocity will be over here. When it reaches the next point, its velocity will be there. And then when it reaches this point, its velocity will be here. So you can see if this is the dashed line, this right here, if my object is right here, I make an arrow that's sort of popping away from this dashed line, and that's going to be the direction of my velocity. So if I draw the object over here, I can take this dashed line and sort of extend it, and this would be the direction of my velocity. So velocity in these directions, these are called tangential directions. We call them tangential to the circular path. So in all of these circular motion, in all of these examples, the velocity is tangential to the circular path. And since the net force, or the special name for it, the centripetal force, is always acting towards the center, there will always be a relationship between the direction of the velocity of the object and the direction of the centripetal force of the object. They will always be 90 degrees to each other. So if I draw the rope over here for this particular scenario, they would also be at 90 degrees over here. And if I draw them over here for this particular scenario, they will also be 90 degrees over here. In fact, for all of these positions, the net force, the centripetal force, it will always be at 90 degrees to that velocity direction. That's just a property of circular motion. So two properties of circular motion. One, the velocity direction will be tangential to the centripetal force direction, and two, it will be at 90 degrees to the net force, or to the centripetal force. Here's the other idea. The third property, you can call it, and this isn't a property, it more so comes straight from the law of Newton, the second law of Newton, and it's that the resultant force, or the F net equals ma. Over here, you can sort of see that acceleration is caused by net force. In this case, since the net force is acting towards the center, we're talking about circular motion, we're calling that net force the centripetal force, which acts towards the center. What we can sort of say is this acceleration will be the centripetal acceleration. We can give this acceleration a special name. For circular motions, we can start calling it centripetal acceleration. And since we've sort of learned from our dynamics courses and other courses that force acts in the net force, the centripetal force, acts in the same direction as the acceleration, or the acceleration acts in the same direction as the net force. What we can sort of understand is that if the net force is acting towards the center, so you have your net force acting towards the center, what that means is that you will have an acceleration in this direction as well. So you'll have an acceleration, which we're calling the centripetal acceleration. You will have that in this direction as well, so towards the center as well. And in fact, if that net force is 90 degrees to your velocity direction, guess what else will be at 90 degrees with that velocity direction? It's going to be the centripetal acceleration. Reason for that being that it's in the same direction as the net force, and therefore if net force is 90 degrees to the velocity, acceleration is 90 degrees to the velocity. So these are the three properties you should know. The velocity acts tangential to the centripetal path. Number two is the velocity is 90 degrees to the net force direction, or in this case, we're calling that the centripetal force, 90 degrees to the centripetal force direction. And the third one is that if your centripetal force acts towards the center, that's exactly where your centripetal acceleration acts as well. Okay, let's look at this next problem. So let's look at this next scenario. So right now, we're just building intuition for circular motion problems and whatnot. We're over here, we have Earth and the Sun. So we do know that if it's at, let's say, Earth is going clockwise, anti-clockwise or counterclockwise around the Sun. So at this point, if somebody asks me to draw the velocity direction, what I can do is I can just take this first dashed line and I can draw a straight velocity vector going out, and I can say, well, that's my velocity direction for Earth. If it were going clockwise, if it were going if it were going clockwise, so clockwise would be in that direction. And then somebody asked me to draw the velocity vector, then I would just sort of take this dashed line and I would be like, well, that would be my direction of this Earth going around the Sun. Now, what about the centripetal force? So the centripetal force will be acting towards the center. So that right there, that's the direction of my centripetal force, Fc, or my net force, Fn. And what about the centripetal acceleration? Well, centripetal acceleration will also be in this direction of the centripetal force, because centripetal force causes the centripetal acceleration. So that's the properties of circular motion applies to this scenario as well. Now, here's what we need to sort of think about. In this particular scenario of Earth and the Sun, we don't have a rope that's pulling the Earth around the Sun. The Sun doesn't have a rope attached to it, and it's not spinning the Earth around itself. Rather, there's a force that you cannot see. That's what causes the centripetal force. It's the source of the centripetal force in this example. So if I draw the free body diagram for the Earth, again, free body diagrams are really useful. Free body diagrams allow you to figure out what is the source of the centripetal force and where that centripetal force is coming from. Because again, centripetal force isn't a thing of its own. It's the resultant force that you get when you sort of cancel out or add forces together. So if I draw the free body diagram for Earth, so it's in isolated space. There is no normal force acting on the Earth. There are no other forces acting on the Earth, but there is gravitational force. So there is gravitational force acting on the Earth due to the sun. So we can call it the gravitational force Fg. That's the gravity. Now, there are no other forces because it's an isolated space. There's nothing else that's supposed to be, there's no other force that's acting on the Earth. So apparently this would be the only force in this particular example. So what I can say, and it's, of course, if you look at it, it's this right here is your center, and this right here would be the central direction. So if I make an equation for this central direction, I would say, hey, my F net is equal to this Fg, which is acting towards the center, and there are no other forces, so I don't have to add anything over here. So it's just this one force Fg. So I can say that Fg is what's giving me my resultant force, or it's what's giving me my net force. And therefore, since for the case of circular motion, I'm giving this net force a special name, I can say that my centripetal force Fc is equal to that gravitational force Fg. So Fg is what's causing, or it's what's providing me that centripetal force. It's the source of my centripetal force in this particular situation, and therefore this force will be acting towards the center, which is the sun, and it's going to pull the Earth into its circular motion. So notice how we initially said that centripetal force is the entire reason for circular motion. Notice how in the first example of the rope and the ball, we had forces that were providing us the centripetal force, and in the second example we have this gravitational force that's providing us the centripetal force. Again, if you don't have centripetal force, you will not have circular motion. So that's really the essence of circular motion. The centripetal force is really the essence of circular motion. So in this case, it's being provided by the gravitational force, the pull of the sun onto the Earth. Again, the velocity vector will be 90 degrees from this, so we can just, if you draw 90 degrees sort of like this, that's where your velocity vector will be. Somewhat like that. Lucky for the example of the Earth and the sun, if you draw the Earth over here, it will have only Fg acting in this direction. If you draw it over here, it will have Fg acting in this direction. If you draw it over here, it will only have Fg acting in this direction. However, that was not the case for when we were talking about the rope and the object, because in that particular situation, you were dealing with two forces. You were dealing with a weight as well as the tension. In this particular situation, since Earth is in isolated space, you're only dealing with one force, that's the gravitational force, and it's always going to be acting in the center. So it makes understanding and calculation a whole lot easier. Okay, talking about this second example. So we have an electron going around a nucleus of an atom. Nucleus is positive due to the protons it contains. The electron is negative due to the, well, it's just negative. There's no reason. How about in this particular situation, what provides the centripetal force? So we know that if, in order for this electron to go around this circular path, there must be some force that acts towards the center. There must be some centripetal force. So the idea is, what provides that centripetal force? What's the source of that centripetal force in this particular situation? And it's the electrostatic force of attraction between positive and negative. So positive attracts negative, and that's why they have a force between them. It works somewhat the same like gravity does. You can't see it, but it's there. It's real. It's sort of like magnets. When you have North Pole and the South Pole, you bring them together, there's a force of attraction. So positive charge attracts this negative charge. And so what's going to happen is there's going to be this electrostatic force, which I can call Fe. That's my electrostatic force. And let's say the atom is over here at this position. Over here, you will also have Fe over here. And then you would have Fe when this goes to this position, you will have Fe over here. And some of you may argue that they may be like, well, what if this atom, well, let's say this is Earth. So let's say this is the surface of the Earth. And some of you may ask, well, what if the atom is over here, right? What if this atom is over here? Now, an atom is a really tiny particle, and we have its electron at this position, right? So wouldn't we have an electric force over here and the weight of the electron pulling it down? Well, somewhat, but not exactly. An electron is a really really tiny particle, and so its weight is so tiny that you can almost say that it has no weight. You can almost say that it has no weight. You can sort of neglect that. So therefore, then the only force that you're really talking about is this electrostatic force that exists between this nucleus and the electron. So this electric force. And therefore, if I have to write my equation now for the net force, so F net, well, what's providing that net force? Well, there's only one force, which is the electrostatic force. That's providing the F net. There are no other forces that are pulling this electron from any different sides. And therefore, in the case of circular motion, we give this force a special name. We start calling it Fc. And therefore, we can say that the centripetal force is being provided by the electrostatic force of attraction that exists between the positively charged proton and the negatively charged electron. What about a car doing donuts? Let's talk about this. This is actually a really good example of what's providing the centripetal force, because it's almost not obvious as to what would be providing the centripetal force in this particular situation. So you have a car, it's going around this central path and it's doing donuts. It's the central point. Let's say on a road you have this center point and you mark it, and you X mark it, and then you have your car, you're doing donuts around that central mark. What's happening is that in order for you to do that circular motion, you already know that if you're doing circular motion, you have to have a centripetal force. The only idea that's sort of hard to catch is it's not obvious as to what would be providing that centripetal force in this particular situation. In fact, it's the gravitational force. So if you look at, oh, sorry, it's not the gravitational force, my bad, it's the centripetal force. So a car doing donuts, there's this frictional force. I'm going to call it F and then small f for frictional force. There exists a frictional force between the road and the tires, and that's what sort of that frictional force act towards the center of that circular path, and it's what keeps the car going in that circular motion. Yeah, obviously, car will also have its weight acting downwards. So let's say this is the road, so the weight would be acting downwards. But then if the car is on the road, then the road is going to provide a normal force. And so those are going to be two forces that are acting as well. But you can see that's the vertical direction. We're concerned about the central or the circular direction. That's this direction right over here. So we don't have any other force apart from that frictional force that's acting towards the center. So we can sort of ignore these two forces in the vertical direction for now. Now, the car is going around this central point, and friction between the road and the tires is what's sort of pushing it in the center. Now, you may sort of not agree with me on that. You may sort of think, well, no, that's not the case. I don't think that is true. Here's what I want you guys to imagine. Imagine if this was an icy road. Icy road. Would you be able to do donuts on that if you put a cross mark on that icy surface and then you try and do donuts around it? Would you be able to do would you be able to do a donut around on that icy road? You wouldn't. And you would basically, when you try to do donuts, the car will basically sort of slip away. So why is it slipping away? Why is it not able to do the donuts? Because icy roads reduce friction. If there is no friction, you cannot stay in that donut path. You cannot stay in that circular path. Therefore, that is proof that when you have the force of friction, you're able to do a donut, but when you don't, you're not able to do a donut. Therefore, what does that mean? That means that frictional force is what provides the centripetal force in the case of a car going around a circular path. So in fact, if I make the equation for the central direction for this car, that would be F net equals this frictional force. F. And of course, this Fn, this net force, I'm giving this a special name in the case of circular motions, calling it centripetal force. And therefore, my centripetal force is being provided by this friction between the car and the road. Now, of course, again, you could also make an equation for the vertical direction, which would include the normal force from the road onto the car and the weight, but that will not be, this equation will not be for the central direction. So you can have an equation that your normal force F capital N equals to your weight of the car, which would be Fn equals to Fw. But this equation is for the vertical direction. I'm strictly talking about this equation is for the central direction. So we're strictly talking about the central directions right now. We're concerned with the circular path, and the circular path is concerned only with the circular direction. So we can sort of ignore that vertical aspect of this for now. I'm going to ignore that vertical aspect right now. Okay, what about this plane? Now this plane is sort of going around this central point, and what in the case of a plane, what provides the centripetal force is essentially there's this lift vector, or this lift force vector, that's sort of going in this direction. Call it capital L, and then you can divide this into two components. So you can divide it into a component over here, and you can divide it into a component over here. And then, of course, this also has a weight. So I can say the weight of this plane X in that downwards direction. So, well, there's two directions again in this particular situation. There, you would have this vertical direction, and then you would have this central direction. So if you're trying to make an equation for the vertical direction, then that would simply be FL, and the lift component, or we can just call it the y component of the lift. So Ly, which is the y component of the lift, is equal to the weight of the plane. That's what balances out the weight with the y component of the lift. And then, so this is the equation for the vertical direction. Now, if you want to do the same for the central direction, you can see that the F net in this particular situation would be provided by that x component of the lift force. Okay, and that, since in the case of circular motion, we have a special name for this guy, we're calling it the centripetal force. We can say that the centripetal force is being provided by this x component of the lift. Right, what about banked roads? So banked road is a bit complicated. I don't want to get into this right now. We can get on into this later. But just to give you guys an example, let's say if my particle or my car was over here, and its velocity vector would be there. So let me just draw out the circular motion for this car. It would be something like this. And so what's happening is if I sort of take out this chunk of this banked road, take out this chunk, you can see that it basically somewhat solves into an incline problem. So this would be 90 degrees, this would be some angle theta, and then you would have a force of weight acting downwards. Over here you would have a normal force over here, and in fact if you break that normal force into its two components over here and over here, let's say this is so this would be the y component of that normal force, this would be that x component of the normal force. The particle is going around that circular motion like this in the banked road. So this x component of that normal force is what will provide that centripetal force. There is this vertical direction over here as well. We're not concerned with that. We're concerned with the central direction. So you can say that the net force is provided by the x component of the normal force. And since we have a special name for the net force in case of circular motion, we can just call it the centripetal force. It's provided by the x component of the normal force. Now, all of these examples are, you can see that we initially, when we were starting off, we said that in order for us to have circular motion, there must be a centripetal force. And you can see in all of these examples, we have that centripetal force. Some weird force is providing that centripetal force. Centripetal force isn't something on its own. It's a net force that's provided by, well, resolving other forces. When you solve out other forces, make equations, make free bodies, you find out what's the force that's providing the centripetal force. Again, what was the centripetal force? It was the net force that acts towards the center. So we're mainly concerned with the central direction. We're looking at the central direction. Now there's another example that I could give you guys as well. So let's say that would be a car, let's say, or a motorcycle. So going around a loop. So let's say we have a circular loop like this, circular loop like this. So somewhere over there we would have the center point of the circular loop. And let's say you have a car going around the circular loop. So you have a car going around the circular loop. Now here's the thing. If I sort of zoom this in, I can zoom this loop in. Okay, so it's something like this and something like that. When the car is, let's say, over here at this position, what's providing that centripetal force is the normal force. So this car is in contact with this road. Whenever you're in contact, or this track, whenever you're in contact with something, you have to think about, that's why free bodies are so important. So I'm just thinking about the free bodies over here. I'm just thinking about, okay, what would be the free body of this car? So of course it would have its weight acting downwards, and it would have a force in the centripetal direction, because it's moving in a circular motion, it's going in a circular motion. So there has to be a net force that acts towards the center. So the next question is, okay, what provides that net force? Well, if you look at this car, it's in contact with that road. So when you're in contact with something, you feel a contact force, a normal force. And therefore, in this particular situation, so this would be F capital N means the normal force. It would be the normal force that acts in the center. Let's say this car goes over here at this position. So at the top, if you draw the free body again for this car, you will find out that, it actually has two forces now that are acting towards the center. So one of those would be the Fn, which is the normal force that this car has when it's in contact with that road, and the second force would be its weight. So if you want to find the F net right now, you would make an equation for F net. F net would be the normal force, which is F capital N, and plus the weight, because weight is also acting in the center. So then Fn would simply be equal to the sum of these two things. And in the case of circular motion, we're calling Fn our net force, our centripetal force. You can just say that centripetal force is coming from Fn plus that weight component. Okay, so again, this is, you can see that since this car is going in a circular motion, it also has something or some force that provides the centripetal force. Without centripetal force, you would not have a circular motion. All of these examples have a centripetal force. That's why they're able to go in that circular motion. Now, we know in what direction the velocity acts. We know it acts tangential to the circular path. We know that the velocity direction is also 90 degrees to the centripetal force direction. We know that the velocity vector is 90 degrees to the centripetal acceleration as well, because the centripetal acceleration is in the same direction as the centripetal force. Now, here's one thing that I would like you guys to know. So I'm going to just sort of go over this with a general example, and it's going to apply to all of these problems up here. So imagine you have a particle, okay, right over here. So you have a particle that's sort of moving around a center point. And this could be anything. This could be an object that's attached to a tension, that's attached to a rope. You're sort of spinning it around. This could be for a car going around a center point doing donuts. This could be for a planet going around its sun. This could be for an electron going around its nucleus. Imagine it's at this point, so it has a velocity vector in that direction. And it has some forces, some net force in the central direction. Some net force. And if you can call this the centripetal force or the net force. They're the same thing in the context of the circular motion. What if this suddenly disappeared? What happens if this suddenly disappeared? So in case of a ball and a string, imagine if suddenly what happened was the rope broke, okay? Or in the case of Earth and Sun, imagine if gravity suddenly vanished, or there was no gravity anymore. Or imagine in the case of this plane, since it was generating lift, and one of that components of lift was this one, Lx. This was providing the centripetal force. Imagine if lift disappeared all of a sudden, if the engines failed and the lift disappeared. If the lift disappears, this component also disappears. So imagine what would happen if the centripetal force or the net force or the force that's acting towards the center, it disappears all of a sudden for any of these particular cases. If that happens, this particular particle, it will go flying off in the direction of this velocity. So if the velocity vector was in that direction at this particular instant, and the net force disappeared, the centripetal force disappeared, it would continue to fly off in that direction. So the motion, the subsequent motion, or the motion that you will see after the net force has disappeared, it will be this motion. So it will just fly off in that direction. So whatever the direction of the velocity vector was before the net force or the centripetal force disappeared, that's where it's going to go flying off in. So if, let's say, if this particle was at this point, and it had a velocity vector directed in this direction, and let's say its centripetal force or its net force acting in the center just disappeared, it suddenly vanished, what it's going to do is it's going to go flying off in this direction. So that's also a property of the circular motion. If your centripetal force suddenly disappears, and you may have noticed this when you're spinning the object attached to a rope. If you suddenly release the rope, all you've done is you know the rope won't have tensions once you've released it. And so what happens is that ball or that object, it sort of goes flying off straight into that direction. So whenever you have a circular motion, and at an instant its centripetal force or the net force disappears, it goes flying off straight into the direction of its velocity, and it's going to go straight into that direction. So that's another property of circular motion. Having done the intuition for circular motion, we will now be looking at some formulas, and you will be using these formulas to solve all of your circular motion problems. So here's the idea. Whenever you're doing a circular motion problem, you will be using this Newton's equation, F net equals ma. And why are you using this equation? Well, because see, if this is a circular motion and you have something like an object going in a circular motion around the center, what you can sort of understand is that there's this resultant force or this net force that always acts in the center. So that must mean that whenever we're doing sort of these circular motion problems, the key idea is using this Newton's equation for the resultant force that acts in the center. Now, we in the previous sort of part of this video, we understood that, or we sort of declared that when we're dealing with circular motion, what we'll do is, instead of calling this F net, we'll give it a new name. We will call this net force the centripetal force. So we put a tiny subscript c to denote that this is a centripetal force and we have a circular motion over here. And therefore, what we do is we take this acceleration and we put a tiny c next to it, the subscript c. And what this subscript tells you is that we have a circular motion, and this acceleration is the circular acceleration of that circular motion. Right. So this is the equation that you're going to be using a lot. Now, so this is what is this equation? It's just Newton's second law. So it's Newton's second law equation. Right. Now, sort of, you've probably studied this for when you have an object and it's traveling in straight lines. So let's say something like this and it's going in that direction, or maybe there's this horizontal path and you have like an object going in that horizontal path. You've sort of learned this equation or seen this equation for acceleration for straight lines, and that equation is basically final velocity minus initial velocity divided by time taken. Now, this equation is for when you have straight line motion. Now we're talking about circular motion. So in fact, circular motion also has its own acceleration equation. And if I just write the circular acceleration, let's put acceleration in a tiny subscript c to basically denote that I'm talking about the circular acceleration. What this equation is equal to is it's equal to v squared over r. So what is v squared and what is r? So v is basically the speed of this object. So it's speed of this guy. And what's r? R is the radius of the circle. So this circle is going to have some radius. Let's call it r. So it's the radius of that circle. And so this equation is something that you also need to know. And then, well, you can sort of take this equation right over here, this acceleration equation. So you can take this, and you can take this guy, the second law for circular motion, and you can combine these two. And what I mean by combine these two is you can take this acceleration and substitute it over here for this acceleration. And so you get this formula: centripetal acceleration equals m v squared over r. And this is the holy equation, or the sacred equation for circular motion. This equation, you will almost be using this equation in any sort of problem that you're solving. So this is, if you want to take away one thing from all of this, take away this equation right over here. So you need to learn this equation. Centripetal force equals mv squared over r. Okay, so that's the main equation that you're going to be using. You're going to be using this equation in every single problem. And here's what I want you guys to know. So when you're solving problems, this will be your first equation, and your second equation will basically come from the free body diagram. So this equation comes from Newton's second law, and then one equation will come from your centripetal, the free body diagram that you're going to draw. So for example, if I just draw a path over here, and let's say somebody has a rope that is attached to a ball and they're spinning it around. If I draw the free body diagram for this ball, so two things are happening. This ball is for this particular position right over here at the top. If I draw the free body, well, there's the tension from the rope pulling it downwards, and there is the weight of this ball, mg, that's pulling this ball downwards. Those are the two forces that are acting on this ball. Therefore, the free body diagram, the FBD also gives me an equation for the centripetal force. So the centripetal force, which we just have been studying, is essentially the net force. The net force, or the centripetal force, is just going to be the tension T plus the weight mg. So this is going to be the second equation that you will have to use. Now, of course, this equation will change for every single scenario. It's not going to be the same. For example, let's say I have let me think about an example. Let's say I have a planet. I have a planet. So let's say this is Sun, and this is Earth, and Earth is going around the Sun. So in this case, there's only one force acting on the Earth. That is the gravitational force. Let's call it Fg. So in this case, your centripetal force, or your net force, is basically just that Fg. So in this case, you will have a different free body diagram equation. So in this case, this would be your second equation. So free body diagram equations are going to change for every single problem that you're doing. It's unique for every problem. But this first equation, the second law equation for circular motion, this is going to stay the same. Okay, so you're going to be using two equations. And see, when you find your centripetal force, so this right here is your centripetal force, and this right here is your centripetal force. What you can do is, let's say I take that first equation, which is the second law equation, I can go ahead and I can combine it with the free body diagram equation. So Fc equals T plus mg. This is the free body equation. And then the second equation would be the Newton's second law equation. So that would be Fc equals mv squared over r. So what I can do, so this is the second law equation. What I can do is I can combine both of these because they both have Fc, and therefore what I can do is I can take this value of Fc, substitute it in that equation, and so I'll get T plus mg equals mv squared over r. So you've basically merged, so now this is the merged equation. You've combined the FBD and second law equation. So whenever you're doing circular motion problems, these two equations are going to be really important. You're going to want to have a free body diagram equation, and you're going to want to have this second law circular motion equation. These are really going to be the key equations that will allow you to do any circular motion problem. Okay, so here we are, and let's look at some problems. So over here we have a mass that is attached to a light thread, which is fixed at x. The mass is moving at a constant speed in a horizontal circle with a center O. Which of the following is the correct free body diagram for this mass? So I want you guys to pause this video, try it out yourself, and then play the video again and see if you got it right or not. Okay, so if we think about it, there's a particle attached to this point. Let's say we have a hook here. That hook has a particle attached to it, and it's going in a circular motion around the center O. So this is a center O. Right, now think about what's happening. There are sort of two forces that are acting on this particle. Now, one of the force is going to be weight mg, because everything has its weight. Now, this is obviously w, which is the weight, but we know that w is equal to mg, so instead of writing the weight, you can write mg. And it's better that you write mg, or if you want, you can write w as well, but that's up to you. I prefer writing mg. Here's the idea. So this ball is being there's this weight of this ball, because obviously everything has a weight. So this ball is going to have a weight that's going to pull it downwards, and then since it's attached to a rope, it's going to experience a tension force in that direction. So that's, remember, tension force always acts away from the object. So if the object is right here, tension force will act away from it. So that would be the tension force. And so option A wouldn't be correct, because option A just has this force. And some of you may, be like, well, that's the centripetal force. I know my ball is moving in a circular motion, so it needs to have a centripetal force or a net force in the center. And yes, your idea is correct. It does have a force in the center. But here's what I want you guys to know. If you divide this tension into its components, this would be this x component tx. This would be the y component ty. And so in fact, what that centripetal force is a component of the tension force. It's the x component of that tension force. Now, when you're drawing free body diagram, see this, the question says draw the correct free body force diagram. In the free body force diagram, you don't represent the net forces, or you don't represent the components of forces. Okay, so you represent the actual forces that are being applied. You can go ahead and divide this tension force into its x and y components, but if you don't divide it into its components, what are the actual forces? So the actual tension force is in this direction, the actual mg force is in this direction. So yes, it's true that you can divide it into its components, but that's not the correct free body diagram. The reason we divide forces into their components is that as humans, it would make it easier for us to solve problems. But that doesn't make it the correct free body diagram forces. When sort of you're looking at this ball in real life, Earth or the universe or the world, it doesn't divide this tension force into these components for you. It doesn't say this is ty and this is tx. It just has that tension force. You as a human go ahead and divide it into two components. So when you're doing these problems, they ask you for the correct free body force diagram, you have to basically choose an answer that is as it is in the real world, okay, without the components. You're not going to divide it into its components. So the two forces are tension and mg. It is correct that there is going to be a centripetal force, but that centripetal force is going to be coming from a component of this tension force. It's not going to be its own force. So the forces that are resultant, or that are net forces, or that are components, we don't actually put them in the free body diagram. We just use the free body diagram to find those things out. Okay, so A would not be the correct answer. C would not be the correct answer either, because there is no force in this direction. There is this tension force, and you can divide this tension force into tx and ty, but in this direction, there's no real force that's acting in that direction. In the same way, this one is completely wrong as well. There's no force that's pulling this ball in that direction towards the right. So that just leaves us with this option B, and so that's going to be correct. We're going to go with option B. Okay, moving on to this other problem. It says a humpback bridge are sometimes found in country areas. The road surface is curved, describing an arc of a circle. What is an arc of a circle? It's basically, you can say it's part of a circle. It's a tiny piece of a circle. If cars cross the bridge at too high a speed, there is a danger they will lose contact with the force. So what they're saying is there's a bridge that looks something like this, and if you have a car that's going too fast, what's going to happen is it's going to lose contact with the force, which you may have experienced if you go over a speed bump. If you go over a speed breaker or a bump on the road too fast, you actually feel yourself, flying off of the ground. The car or the motorcycle or the bicycle, it sort of lifts off from the ground when you're going too fast. So that's what they're talking about over here. The responsibility for setting speed limits on many roads on which humpback bridges are found rests with the local traffic authority. So what the local traffic authority has to do is, if there's a speed bump right over here, and you are gonna go over that speed bump, then the traffic authority must put a sign over here that tells you the speed limit. So you decrease your speed such that when you're on the speed bump, you don't go flying over this thing. Okay, you don't lose contact with the bridge. That's what they're saying. One local traffic authority suggests that a speed limit of 25 miles per hour is appropriate for a humpback bridge with a radius of curvature 10 meters. So what does this mean? Let me just simplify this for you guys. So what they're saying is if I bring that situation back, what they're saying is if I put a, if the bridge, so this bridge is obviously, so they give us an example over here of what this bridge is going to look like. So let's say this is a circle. So let's create a circle. Let me create a circle over here. So let's say I create a circle, and this humpback bridge is sort of a part of that circle right there. Okay, and this isn't a semicircle. Okay, it's an arc. This, if this was a semicircle, they would have told you that it's a semicircle. Well, it doesn't matter if it is a semicircle or an arc. But yeah, never mind. Okay, so imagine this is a humpback bridge. Okay, and it's part. The humpback bridge is a part of this green circle over here. Okay, and what they say is that this circle has a radius. So the radius of curvature basically means the radius of the circle. So they're saying that it has a radius of 10 meters. Now here's what they're saying. They're saying that the traffic police should put up a sign that 25 miles per hour is the speed limit. Meaning, if you go faster than 25 miles per hour, you're basically going to fly over this bridge. You're not going to be in contact for all the time that you're going over this bridge. Okay, so what we have to do is it says assess the suitability of a speed limit of 25 miles per hour for this bridge. And then they tell us that 10 miles per hour is equal to 4.5 meters per second. Right, so what we have to do is here's what the question is saying. The question is saying assess and find out whether this is actually the speed limit that will allow you to go over this bridge without losing contact. Without losing contact. If you lose contact, if you're sort of flying over this bridge, then that means that 25 miles per hour is not the safe speed limit. Now, here's what they do. So we can't use miles per hour. So we can't use miles per hour in our equations. We use meters per second. That's the units of speed that we use. So what they do tell us is they tell us this conversion over here. So they tell us how can we go from miles per hour to meters per second. So I'm just going to first convert my speed from miles per hour into meters per second, and I basically would do this the following way. There's something called a ratio method. I don't know if you guys are sort of aware of this method, but essentially what you do is you take this known relationship and then you find, so we don't know what this is going to be in meters per second. So you take the known relationship and from that you find the unknown. Here's how you do it. So you put the known relationship over here. This is 10 miles per hour is 4.5 meters per second. So this is miles per hour. This is miles per hour. This is meters per second. And then inside this miles per hour, this is the known relationship. And we're going to use this to find the unknown. So the unknown will be, so miles per hour, 25. We have to find how much this is in meters per second. So we don't know how much it is, so we just put a variable v over here. V means the speed in meters per second. That's what I'm trying to find out. Once you've once you've made a table like this, all you want to do is you want to cross multiply these two. So and you want to put them equal to each other. So 10, you're going to multiply 10 with v, so that's going to be 10 v, and you're going to multiply 25 with 4.5. So that's going to give you 25 times 4.5 is 112.5, and you put these equal to each other. And so you're going to make this v the subject, you're going to divide this 10 to the other side, and so 112.5 divided by 10 is going to give you 11.25 meters per second. So we just use the ratio method to find out how much 25 miles per hour is in meters per second. Now we have this speed in our SI units, so now we can start doing this problem. Now how do we actually start doing this? How do we find out if this 25 miles per hour is the safe speed limit so that I don't lose contact? This is so much words. This is so tricky. How do I do this? Now remember what I told you guys in a few minutes back. I basically told you guys that whenever we're dealing with circular motion, what you're going to want to do is you're going to want to think about two equations. Okay, remember that? You're going to think about one, the free body diagram equation, and the second law equation. So the reason we've studied those equations is to use them. And we don't know how we're going to solve this problem right now, but we're going to use those equations, and those equations are going to tell us themselves how we can sort of solve this problem. So let's get our first equation, which is the second law equation. So the centripetal force is going to equal mv squared over r. Okay, now what do we have to do? So this is the second law equation. Second law equation. Now we need the free body equation, so the free body diagram equation. Now here's the idea. If you think about it, so here's what happens when you're on a bumpy road. This car is at this position, right over here, as they give you in the problem example. What happens is sort of, think about it like this. So I'm going to actually make some room over here. You have this road, and it's doing something like this. First of all, understand this. So this part requires intuition. Let's say you're entering this humpback bridge at a certain speed. Now, what happens is you don't lose contact for half of this journey. So while you're on this much path, you won't lose contact. What happens is when you reach the top of this bridge and you have a high enough speed, what happens is your car sort of just flies down over here on this position. So it doesn't actually go over this part. Okay, so this understanding is really important, and it comes from intuition. It comes from, you know, experiencing this happen in real life. So for the first part, for the red part, you are in contact with this bridge. For the next part, if you're going fast enough, if you're not at a safe speed, you sort of fly off the next part and you just hit the road. Here's the idea. When you're at the top, so when you're at the top, that's when all the problems happen. If you're at the top and you're not going at the safe speed, you lose contact with the road, with the bridge, and you go flying. Okay? If you're going at a safe speed and you're at the top position, what happens is you just go along this green part. So that top position is really important, and that top position, we're going to basically be taking that as a reference point when we're going to be solving this problem. Now, you guys probably still don't know how to solve this problem, but as I said, you know, just go with the free body diagram, go with the second law, and it will work. So here's what you need to understand. You're going to draw the free body diagram for the top position. The top position is where you either lose contact with the road or you stay in contact with the road. So the top position is where all of that stuff is happening. Because for this first part, you will be in contact with the first part no matter whatever speed you're going at. Okay, that's just the way it works. But if you're going with a high enough speed and you reach this top position, what happens is that this next part, you just sort of go flying over this next part and fall onto the road. So this part actually doesn't care about what your speed is. Now, the top part, that's why if you look at this diagram, they give you the top part over here as well. So that's what we're going to do. So we're going to make the free body diagram for the top part. So basically, if you look at this over here, your car is going to be at this position on top. And if you're going fast enough, it's not going to be in contact with this part, and instead it's just going to fall somewhere over here. Okay, so let's draw the free body diagram for the top part. So we're going to draw the free body diagram for the top part. So it's part of a circle. I'm just going to draw that circle. So it's right over here. And then if you want, you can extend the circle down over here as well, but you don't really need to do that. So that's your car up there. Now, what are the two forces? So this over here would be the center of this circular motion. Now, think about it. What are going to be the forces acting on this car? What are going to be, how do we draw out the forces? Think about that. So obviously it's on some planet. Maybe that planet is Earth. When you're on a planet, you have a weight. Your weight is the way the planet pulls you down towards itself. So this car is going to have some weight mg over here. So that's one of the forces. What's the other force that it can have? It can have an upward force. Why? Because it's on the road. If it's on the road, if you're on a surface, you're in contact with something, you have a contact force, a normal force, okay, a reaction force. All of those are the same thing. So it must have a reaction force. It's in contact with something. So it has a normal force. It has a normal force up there. Right. I have a weight. I have a normal force. What other forces can there be? Now, maybe the engine is providing some horizontal force. Okay, so the engine could be providing a horizontal force that we call a driving force. Maybe there's friction between the tires and the road. There could be a frictional force in the backwards direction. But we are not concerned with this direction. That's not the circular motion direction. We're concerned about the motion. We're concerned about the direction that is in the center. It's either towards the center or away from the center. So that's this direction right over here. That's what we're concerned with. That's what we're going to use. When we're talking about the circular motion, we're mainly concerned with the circular motion direction. Therefore, we can say that the net force or the centripetal force is going to be that mg minus that normal force, Now, here's the idea. So you sort of get this FBD and you make an equation over here. FC equals, which is your net force. FC is basically your net force. And you're going to find that when you subtract these two forces. So now this right over here, this mg, this is what your weight is, right? But I know that W is equal to mg. So instead of writing W, I can simply write mg over here. Okay. Now, let's talk about okay, so we have these two equations. You can see we have these two equations. One of the equations comes straight from the second law. One of the equations comes from the force body diagram equation, or the force body diagram. So you still may not know, how do you answer this question? How do you assess whether 25 miles per hour, or we just found out how much this is in meters per second, and it was 11.25 meters per second. We still don't know if this is enough. We still don't know if this is safe. We still don't know if this is safe for this bridge, which has a radius of 10 meters. Okay, 10 meters. We don't know if we have this speed, our car will sort of jump over this or not. So how do we find that out? How do we figure that out? okay, here's the idea. You still may not, you may be like, well, I found out my second law equation, I found out my FBD equation, I still have no idea what to do. And that's fine, that's fine. What I would want you guys to do is I'd want you to just first take these two equations and merge them, or maybe not even merge them right now. Okay, you don't have to merge them right now. You have two equations, you found out two equations, you completely have no idea what to do with it. You don't know if you should put 10, so you don't know if you should put the radius that you found out, which was 10, in place of radius, or this v in place of this velocity. You have no idea what you need to do. So here's what I'm going to tell you guys. Here's where you need to use that intuition part. Remember the first part of the video, it was all about building intuition. What happens? What's going on with a car that's going over a hump? What happens to a ball that's attached to a string and it's at the top? What's happening to a plane that's rotating around a circle? All of that stuff. That's what we're gonna do right now. We're gonna think about some intuition. We're gonna do some thinking part. We're gonna leave this math, leave this physics, do some thinking part right now. Here's the thinking part. So we already do know that whether the car stays in this circular motion or not, that depends on whatever is happening at the top. Okay, so if it's too fast at the top, it's going to lose contact. If it's slow at the top, it's not going to lose contact. So whatever's happening is happening at that top position. Here's what you want to do. Here's where you're going to understand. You read the sentence and they say lose contact with the road surface. What does that mean? Try and think about that, and think about this normal force. What do these two things mean? What does it mean when I say you lose contact, and what does it imply for the normal force? So pause the video, try and think about it. Now here's the idea. If you lose contact with something, it means you are no longer touching it. What does that mean? That means if you lose contact at this, let's say you lose contact at this top position, your wheels are no longer on that top point. What does that mean? What does that mean when you've lost contact? What does that mean when you're no longer touching this road or this top position? That means what happens to your normal force? You don't have one. Your normal force is going to become 0 because you're not in contact anymore. Normal force happens when you're in contact with something. When you lose contact, that means that this normal force is going to become 0. And now it's going to start making more sense. So that means you only have one force over here. That's going to be your weight mg. So that must mean that this equation that I just formed over here, if I lose contact, this equation is going to simplify to Fc equals mg. That's what it means when they say I lose contact. Okay? Here's what they want me to do. They want me to figure out if this 11.25 is a safe speed or not. Here's what I'm going to do. I'm going to use this equation where my normal force is 0. So normal force is 0. And I am going to use this equation. I'm going to use this equation to find out my speed of the car. Now, what's going to happen? When I use this equation to find out the speed, guess what speed I'm going to get? I am going to get the speed. That makes me lose contact over here. Lose contact. This v that I'm going to get, that's going to be the v that, or that's going to be the speed that makes me lose contact. That makes my normal force go to 0. So that's what I'm doing. I tell my equation, this is my equation over here. I tell this equation that I'm trying to lose contact. So I tell this equation that I lose contact. What does that mean? That basically means that my normal force n disappears. It's going to be 0 when I lose contact. So I get this new equation, Fc equals mg. Now, if I use this equation right over here to find my speed, I'm going to get the speed that makes me lose contact. Make sense? So now I've used some intuition to figure out what's going on. How do I sort of use that piece of information? How do I sort of use this equation to find out speed? This equation doesn't have a speed. They don't tell me about the speed in this equation. So how do I find that speed out? Well, guess what? Remember why we were doing two equations in the first place? Because you're going to want to merge them. You're going to want to take these two equations, you're going to want to combine them. So I can basically take this Fc that I have over here, and I can put this Fc in this equation in place of this Fc. Here's what's going to happen. Fc, instead of that, I'm going to put this mg that I have over here, and then that is equal to this thing, which is mv squared over r. Now, I've combined the two equations. Here's where I'm going to find the speed from. Do you see this v? That's my speed. Here's where I'm going to find the speed from. I'm going to solve for the speed, and I'm going to see whether I get this 11.25 meters per second as my answer or not. If I do, then that means yes, this is the speed limit. This is the speed limit. People should not go faster than this. People should go slower than this. They should go slower than 11.25. If they go faster than this or at this speed, they're going to fly off the bridge. I don't want them to fly off the bridge. So I'm going to solve this equation for v, and I'm going to see whether I get 11.25 meters per second or not. That's what I'm doing. That's how I assess the stability. That's how I assess the stability of this bridge. Okay, so let's solve it out. Now, what's the value of g? The value of g is 9.81. What's the value of r? The value of r is 10. What's the value of v? I'm trying to find that. What's the value of the mass of the car? I don't know. I don't know. Here's why you don't know. They don't tell you because if you use a little bit of your brain, what you can do is this m is multiplying over here. Okay? If you take it to the other side, it's going to divide. It's going to divide. And so what's going to happen is what you can do is you can take this m to the other side of the equation. It's multiplying over here. So v squared over r. It's multiplying with this v squared over r. If you take it to the other side of the equation, it's going to divide. And then this m and m, they cancel each other out, and the m's disappear. And so this is the equation that you have left. Now remember, you're trying to find v, so you can make v the subject. So if I make v the subject, it's going to be r times g. So I take this r to the other side. That's going to be v squared, and I can take the square to the other side. That's going to be square root rg. And then I can basically put the value of r, which is 10, the value of g, which is 9.81, and I can find out what my value of v is. So I'm just going to use my calculator. Under root 10 times 9.81, that is 9 point, so this is equal to 9.90. So I can sort of simplify it to 9.9. So what is my answer? What answer do I get? I get 9.9 meters per second. What does that mean? That means this is the speed limit. This is the speed limit. The speed limit. If you go faster than this, you are going to lose contact with the road. You're going to lose contact with the bridge. This speed is higher than the speed limit. Higher than the speed limit. So I have assessed it, and this is not the safe speed limit. Safe speed limit. So the local traffic authority, they have to do a better job. 25 miles per hour, which in meters per second is this much, is not the safe speed. Okay, this right here is the safe speed. So you can go slower than this, and you won't lose contact with the bridge. Okay, then let's do the next problem. It says over here that the diagram shows the carriage of a roller coaster about to enter a vertical loop of diameter 17.0 meters. The carriage is initially at rest at height h above the bottom of the loop. So we have this carriage that is going to enter this roller coaster, and it's right over here. Its speed is equal to 0. It's at rest, and so it's going to start sort of going down this loop. The question says, so that a passenger remains in contact with their seat at the top of the ride, show that the minimum speed of the car at the top of the loop is 9.1 meters per second. What does that mean? Here's what that means. So this carriage is going to, of course, enter this loop, and I'm, for simplification purposes, going to draw a loop over here. It's going to enter the circular loop. Here would be where your center is. And then let's say it enters this loop, it sort of goes like this, and it reaches that top point right over there, this top point over here. So at the top, this right here, this right here is the top position. When your carriage is at this position, let's say there's a seat and there's a passenger sitting on that seat. So there's a passenger sitting on that seat. Now, what they're saying is they're saying that so that this person doesn't fall. What does it mean to say that the person should remain in contact with their seat? It basically means that the person needs to have their butt touching the seat. Okay, if their butt doesn't touch the seat, it means the person's gonna fall. They're not in contact with the seat anymore. Okay, so they want the person's butt to touch the seat. So what they're asking for is show that the minimum speed of the car at the top of the loop is 9.1 meters per second. So what I have to do is I have to basically make sure that this person doesn't fall. Okay, that's what I have to do. I have to find out what's the speed at which this person is going to fall. So here's what happens. I don't know if you've ever done this or not, but maybe try this out. So if you have, let's say this is your hand, and you have a rope which maybe attaches to a bottle over here, or let's say a bucket. So let's say this is a bucket, and the bucket has water over here. Now think about this. What happens if you move this bucket in a circle, but you move it slowly? What's going to happen at the top position? So it's going to go up top, and that water is going to fall onto you or on your head. So this water, all of this is going to fall down. What's going to happen if you rotate this bucket really, really, really fast? It's not going to fall down. It's going to stay, the water is going to stay in that bucket. It's not going to fall down. That exact situation is what's happening over here. You have a person that is, you can sort of understand the person as being the water in the bucket. You can understand the carriage as the bucket, the person as the water. If the carriage is slow, the person's going to fall down just like the water would fall out of the bucket. If the carriage is fast, the person will not fall down. The carriage is going to go really quick, and then the person's going to be seated. They're not going to lose contact. So this is the intuition part that we're understanding. Once we know the intuition part, then we can sort of start doing all of the math stuff and whatnot. So therefore, this person, in order for this person to be seated, what's important? That this carriage is super fast. That's why they ask you the minimum speed of the car at the top of the loop, because there's going to be a minimum speed. If you go faster than that, you are not going to fall down. But if you go slower than that, you're going to fall down. So what they're asking us to do is they're asking us to check and verify if 9.1 meters per second actually is that speed or if it's not that speed. So let's start to do this problem. Now, we don't know how to answer this problem as of now, but we know two things. We know that it's a circular motion problem, and we know that whenever we have a circular motion problem, we write down our equations. The first equation is the second law equation, so that's going to be Fc equals mv squared over r. This comes from the second law for circular motion, the second law. And then the second equation is going to come from the free body diagram. Now, again, we are concerned with whatever happens at the top of the loop. See, they even say, this time they even say it in the question statement. They say the word top of the loop. So what we have to understand is we can sort of make this top part over here. And there's this carriage at the top. The carriage has a seat. There's a person on this seat. And this right here is the center point. So let's draw the free body diagram for this person. So this person is obviously going to have their weight acting downwards, that's mg, and there's going to be some normal force that is being applied on their butt by the seat. So that's going to be the normal force, let's call it n. So the equation that we can therefore make from this free body diagram is basically going to be that the Fc, the centripetal force, is equal to this force mg, which is the weight, and this force n, that is the normal force. And since they're both acting in the same direction, we can add them together. In the previous example, if you go and check it out over here, the normal force was acting upwards because the car was not in contact at this position, but at that position. So the normal force acted in that direction. Over here, they're both acting in the same direction. So what we can do is we can add those two forces up. Now, see, here's what you need to understand. We want the person to not fall. We want the person to not lose contact. So what we can do is we can basically find out that when this, so what we can do is, here's what I'm going to do. I'm going to, if I erase this and I zoom into that position, zoom into that person. So that's the seat right over there. That's the person over here. What I can do is I can basically put this person just a little bit away from this seat, meaning this person is almost falling at this instant. What I can do is I can find out what's the speed when this person is falling, when this person has, or in other words, lost contact with the seat, And using this idea, I can find out what's the speed at which this person loses contact. So that's going to be my minimum speed v. If I go faster than that, I won't lose contact. If I go slower than that, then yes, I will fall. Okay? So how do I take all of this idea to math and then find out a value for v? We're going to do it in the following way. So first of all, remember what we're trying to do. Here's the plan, okay? We are seeing what happens when this person loses contact with the seat and they're falling. What will be the speed when this particular situation happens? So what does it mean when we say a person has lost contact? Just like in the previous example, it meant that you are not in contact with something anymore. What happens is your normal force is 0. You don't have a normal force because you're not in contact. And so I put n equals to 0 over here. And when I do that, my equation simplifies to Fc equals mg. Okay, or actually I'm going to write n over here, but when n goes through when n goes through lose contact, my new equation becomes Fc equals mg. So here's what I've done. I've done this first part. Now I've made my person fall. The way I make them fall is I make this n equal to 0. And now what do I do? I basically use this fall equation and find out my speed based on it. So I use this equation, but this doesn't have a speed variable inside of it. So how do I find the speed? Well, guess what? I have another equation for centripetal force, which does have a speed variable inside of it. So I just combine this equation, the free body one, and that second law equation. So that's going to be Fc equals, and instead of Fc, I can put this thing, mg, and then I can put mv squared r over here. Okay, you can write it mv squared over r like this, or you can write it like this, m times v squared over r. It's the same thing. It's not two different things. Okay. Now I need to make this v the subject. I need to find out what my speed is. Here's what I want you guys to understand. I'm going to make my v the subject. I'm going to find the value for it. Do I know my r? I probably do. If you look at this loop, is my r 17? If you said yes, you are wrong. If you said no, you are correct. This is going to be the center of the circle. So r is going to be half of this distance right over here. Half of this distance. So you can find that out if you divide 17 by 2, which is 8.5. So this is 8.5 meters. That's the value of r. So I know r, that's 8.5. Speed is what I'm trying to find. G is what I know, that's 9.81. M is something I don't know. Why do I not know M? The reason they don't tell you M is because you can cancel the M's out. You can take this M over there, it's going to divide, and it's going to cancel out the M on that side. So the M's will just disappear. Okay, now the equation I have is G equals V squared over R. I can rearrange this for V. This is going to be GR equals V squared. Take the square to the other side, it becomes a square root. GR is equal to V. Now what I can do is I can put in the values for G, which is 9.81 times 8.5, and I can solve this in my calculator, and I will get a value for V. So 9.81 times 8.5, and we underroot that. That is going to be 9.13. So we can round that off to 9.1 meters per second, just like they've done in the problem statement, 9.1. Therefore, they said, show, this is what the question said, remember, the question said, show that the minimum speed of the car at the top of the loop is 9.81, and this was so that a passenger remains in contact. That's what I just found out. This speed is the minimum speed, is that minimum speed. If you go faster than this, faster, you don't lose contact. You don't lose contact. So this is the minimum speed that is required for the person to stay in contact. If you don't go at this minimum speed, you go lower than this, then you fall. So again, how did I find out this minimum speed? Well, all of the trick lies in this part, this idea right over here, this idea. I've set my equation to basically make this person fall, and the way I do that is I take this normal force, I put it equal to 0, that's when my person falls, and then using this idea of the fall, I basically find the speed at which the person will fall, and therefore the speed at which the person will fall is 9.81. So that's the minimum speed that you should have, and you need speeds greater than that. If you don't want to lose contact, if you don't want to fall, you need to go faster than that. If you go at this speed or lower than this speed, then what's going to happen is that you're basically going to fall. Okay, it's the exact same way we did this first problem. So you can see past paper problems actually repeat. It was a different problem. In this case, you had a car going on the top of this path. Over here, you had a carriage going at the bottom of this path. But in both situations, the idea was exactly the same. We're trying to make them lose contact, not be in contact anymore, put the normal force equal to 0, and basically then using that idea, find out the equation for or the value of speed. Okay. Let's do another problem, and this is going to be the final problem for this section. We have a boy who weighs 37 kilograms, and the boy is going around a merry-go-round of a radius 1.8 meters. Part A says, what force provides the centripetal force for the boy? Part B says, find the centripetal force for the boy if he's going around the merry-go-round at an RPM of 20. So what's RPM? We're going to talk about that in a second. Let's first answer part A. Part A says, what force provides the centripetal force for the boy? So the boy is essentially, here's this merry-go-round. The boy is sitting over here. Okay, that would be the center of the merry-go-round. This is the radius. So I'm going to draw the radius over here because I'm going to draw something else with a boy. So this is the radius, 1.8 meters. What's happening is this boy is going around this merry-go-round like this. Now, here's the idea. What's the force that provides the centripetal force? So the centripetal force, we know what that is. That's a net force that is going to be acting towards the center. What's going to be providing that force? Is it going to be the gravity? Is it going to be tension? Is it going to be electrostatic force? What force is it going to be? So it's going to be the frictional force between this boy's butt and this merry-go-round, because he's sitting on the merry-go-round. There's, of course, you don't see a rope attached to this boy, so it cannot be tension. So the force that's basically allowing this boy to sort of go around this merry-go-round is the frictional force between its butt, between this boy's butt and the surface of this merry-go-round. If you don't believe me, think about what would happen if this was an icy merry-go-round. What would happen? If this was a slippery merry-go-round instead, this boy would simply go flying off. So that means if it's not slippery, then this boy stays on this surface. If it is slippery, that means this boy goes off the surface. What's slipperiness? Slipperiness is basically how much friction you have between two surfaces. Therefore, if it's slippery, if it has no friction, you go flying off it. If it has friction, you go around a circle, which means you have a centripetal force, and therefore the friction must be providing that centripetal force. So that is the part A. Part A, we can sort of answer that as friction is what provides the centripetal force in this particular situation. Now, there are two more forces acting on the boy, his weight mg and the normal force from this merry-go-round onto this boy, which is going to be acting in the upwards direction. But since those two forces are in the vertical direction, we're not really concerned with those. So we can erase them right now. We are concerned with the forces that are acting in this central direction, either away from the center or towards the center. So that's only this one particular force, which is going to be the frictional force. Okay, part B says find the centripetal force for the boy if he is going around the merry-go-round. So from the free body diagram, we basically find out our first part, which is that the centripetal force is basically the frictional force. Okay, from the second part, so this is our first equation, and we have obviously our second equation, which comes from the second law. So that is basically this equation Fc equals mv squared over r. This is our second equation. We have to find the centripetal force. Okay, so we just need the centripetal force. Do we have the radius? We do have the radius. We have the radius as 1.8 meters. We have the mass as 37 kilograms, and we actually have the speed. This 20 RPM is the speed. You may not know it now, but whenever you have RPM, that's basically the speed. We don't actually even need the free body diagram for this particular problem. We can simply just use the second law equation and we can find out the value for our centripetal force. And since centripetal force is equal to the frictional force, if you find out the centripetal force value, that's going to be how much friction you have between the boy's butt and the surface of the merry-go-round. Okay, how do we know that this 20 RPM is the speed? So what does an RPM mean? RPM means how many revolutions you're covering in 1 minute. So RPM is literally revolutions per minute, And revolution is basically starting at one position at a circle and going around that complete circle. That's one revolution. So this boy is doing 20 revolutions per minute, okay? We don't want this. So this is a speed. I want you guys to understand that revolutions per minute is a speed. But we don't want the speed in revolutions per minute. We want the speed to be in meters per second. So meters per second. So here's what you guys can do. Here's how you do this conversion. So you convert revolutions to, so it's revolutions per minutes, right? What you do is you convert revolutions to meters, and you convert minutes to seconds. And then this right here would basically be your speed. So here's how we can do that. So revolutions, basically if you have 20 revolutions happening for this particular merry-go-round, then that means this boy is going around this, this, what do you call it, this merry-go-round 20 times. So I'm trying to convert that revolutions into meters, correct? How do I do that? You basically do that by using the idea of circumference of a circle. So if this circle has a radius, this merry-go-round has a radius of 1.8 meters, what I can do is I can find out its circumference, because circumference is equal to 2 pi r. Okay, so circumference is going to be 2 pi and r is 1.8. So this is going to be 2 times 1.8, 2 times 1.8, that's going to be 18 over 5, or 3.6 pi, 3.6 pi meters. And you can, of course, multiply 3.6 and pi, and then you can get a decimal answer. You can round it off, but I'm not going to round it off right now. I'm going to round it off at the end because I'm trying to be more accurate with my answer. So right now, my circumference, like one distance around the circle, all of this distance around the circle, this is equal to 3.6 pi, okay? But I'm not covering one distance around the circle. I'm covering 20 revolutions or 20 circumferences around the circle. So what I can do is I can take this 3.6 pi and I can multiply this with 20. So that's just going to be 3.6 times 20. That's going to be 72 pi meters. So that's my revolutions converted to meters. Now I'm going to convert my minutes to seconds. So if I have 20 revolutions happening in 1 minute, how many seconds are there in 1 minute? Everybody knows 60 seconds. Okay, so I've converted my minutes to seconds. I've converted my revolutions to meters. All I can do right now is I can write 72 pi meters over 60 seconds. So do you see how I get meters and seconds over here? Now I can just simplify this to find out what my speed is going to be. So you do this in your calculator. You put in 72 pi divided by 60, and you are going to get 6 over 5 pi, which you can round off to 3.77 meters per second. That right there would be your speed. So that's the reason why I wasn't rounding the pi off over here, because I rounded it off in the final step. So that makes my answer more accurate. Okay, so that's my speed. I told you guys we have the speed. So we have the radius, we had the weight, we have the speed. That's 3.77 meters per second. We were trying to find the centripetal force. That's pretty simple. We can do Fc equals mass is 37, speed is 3.77, square that, radius is 1.8. Let me just check if that's the equation. Yep. So you put this in your calculator, 37 times 3.77 squared divided by 1.8. So you do this and you get the centripetal force to be 292.15 newtons. Now that, ladies and gentlemen, is the centripetal force of the boy. And since this centripetal force was basically the frictional force, which we found from the free body diagram, this right here is also your frictional force. we got another question over here. This is a string and a particle attached to a string. So let's read the question. It says a particle of mass 2 kilograms is attached to one end of a light inextensible string. This is important. This word means that this is not a stretchy string. So basically, if you find some length of this string, it's not going to change because there won't be any extension in the string. That's what the light extensible part means. It says the other end is attached to a fixed point O. So we have this rope attached to this fixed point O, and at the other end there's that tiny particle of mass 2 kilograms. The particle is set into motion so that it describes a horizontal circle of radius 0.6 meters with a string at an angle of 30 degrees to the vertical. So what does that mean? That basically means that you have a point O right here, and you have a string that is attached to this particle, and the particle is set in movement in such a way that it's basically making a horizontal circle somewhat like this. So it's moving like this, and let's say this right here is a vertical line. So you can sort of think about this vertical line such that it passes through the center of this horizontal circle. That this is the center. Let's call that C, or let's call that X. Let's call that I don't know. Let's not call it anything. So that point right there would be the center, and they're telling you that the radius of this horizontal circle is 0.6 meters. And this angle right over here that this rope makes with this vertical part, that guy right there is 30 degrees. Okay, so part A says show that the tension in the string is 22.6 newtons. Correct the 3 significant figures. Part 2 says find the speed of the particle. Now again, you look at this problem, you have no idea how to answer these things. You have no idea how to find the tension out because they didn't mention the tension anywhere in the question statement. So of course you have to find it out. You have no idea how to find that out, and you have no idea how to find the speed out. But you do know one thing. You do know that this is a centripetal. This is a circular, not a centripetal. This is a circular motion. Circular motion. And just like you use the equations of, you use the kinematic equations or the equations for constant acceleration in straight line paths, when you have a circular motion, you use the circular equations. Well, we have 2 of them. So one of them is the second law equation. So the second law equation, this guy is the centripetal force equals mv squared over r. And then the other equation comes from your free body diagram. So let's make a free body diagram for this particle. This particle is right over here, and it's doing something like this. So it has a force of tension right there. That's the tension force, and this right here would be its weight. We can call that mg. So that right there is the weight. Okay. What I can do is I can see that this this tension force is a diagonal force. So I can break it down into its 2 components. Okay. So one of them would be like this. One of them would be tx, and the other one would be ty. So I could put the ty over here. So tx and ty. So now I don't need this anymore. So instead of having that tension force, I will draw it in as a dotted line. So a dotted line means I had a tension force and I divided it into its 2 components, tx and ty. Okay, here's what I have to do. See, part 1 says, so I'm not even going to look at part 1 for now. I'm just looking at the 2 equations that I have for circular motion, because every problem that we do, we always start with these 2 equations, and then we figure out what we're trying to find and how we can sort of find that out. So we sort of play around with these equations a little bit. Now here's what I can see. So right now, I want you guys to not look at this tension force that I've drawn in the dotted line. Okay, this force doesn't exist anymore. I've just drawn it over there because, well, I want to tell you guys, or I want to show you guys, that this tension force was a force that initially it was a force that I've divided into its 2 components right now. Okay, so we can sort of ignore that dashed line for t. We've divided that t into tx and ty, so we're going to only take a look at those equations right now. We have 2 things happening over here. We have this central, so this particle is, of course, moving in a circle, right? So if I draw a circle for this particle, it's going to be something like this. It's going to be something like this. So this right here is the circle. You can have your center somewhere over here. I'm going to draw a square over here. That square is the center of the circle. I have this central direction. So this central direction right over here. And I have this vertical direction right over here. And you may be like, well, I don't really care about the vertical direction, so I can just erase that because this is a circular motion problem. I'm just concerned with that horizontal direction. And before you do that, I want to tell you guys, just give me a second. You shouldn't always remove the vertical direction. In this case, it's actually useful because it helps us answer a part of the question. So see how we want to find that tension force? That tension force right there, we want to show that it's 22.6. Also, so this tension force that they're talking about, this is the tension in the wire. This is the force. This is the force T, okay? This is this T over here. It's not Tx or Ty. When they say tension in the question, they don't mean the components of tension. Components are not real forces. We break down the real force into its components. But they're trying to ask for the real force, which is the tension force. So here's what's happening. You have that T, that's what they're trying to find. I've simplified my free body diagram into component forces because that way it's easier for me to solve and do math on it. I have to find this T over here. So here's what I can do. See, here's what I can do. I have to find the speed of the particle, and I have to find the tension T. Now, how do I find the tension T? Now, you're actually gonna use this vertical direction to find that tension Ty, and you're gonna use this horizontal direction to find the speed. And this may not be obvious as of now, but give me a second and it will be obvious. So let's first talk about what this Ty and Tx even are. So this thing that they give you over here, this picture over here, this picture is actually really, really useful. I'll show you guys why. So if you take this image and you sort of pop it out over here, you get something like this. So you get a triangle. I don't know if you guys see it or not, but you get a triangle that looks something like this. Okay, and so this right here is your tension force, correct? This right here is your tension force. Now, what you can sort of think about it is, well, you have one component, of the tension force over here, which is the Tx, and you have one component over here, which is the Ty component. What you can actually do is, since these are vectors, you can take this component, you can take this component, drag it all the way over here. Boom, put it over there. So this would be your Ty. Trying to grab this Ty, hold on. Or I can just put my Ty over here. We can erase that part. So now this angle becomes that 30-degree angle. Okay, so all I've done is I've done tip to tail vector addition over here. So this was the tension T, and I've said, well, I can divide it into its two components, which are Tx and Ty, and now I get a triangle, and that is a 90-degree triangle. So you do some trigonometry on this, and you find out that Tx, and remember, this is a 90-degree triangle. You find out that Tx is just going to be, or T. Yes, you do some trigonometry, you can do some SOHCAHTOA on this, and you will find out that Tx is equal to T sine of 30, and you will find out that Ty equals T cosine of 30. So you do some trigonometry, and you find out this relationship. You find out that you have a x component, which is T sine 30, you have a y component, which is T cosine of 30. Now, here's what's happening. And you can go over here, and instead of writing Tx, you can write T sine of 30. So this is the x component. And for the y component, you can write this is T cosine of 30. Okay? And so now it will be really obvious how you can find that tension force T. You could also just let this be Tx, if that's easier for you, and I'll show you guys how you can find the tension force T in that case. So what you can actually do over here is you can take this stuff, this vertical direction, and you can make an equation for the vertical direction, which will be Ty equals mg. How do I know that these two forces are equal? Think about it like this. This particle is not going up or down, correct? It's just moving in that circular motion. If they don't mention about this particle going up or down. Therefore, that means these two forces must be perfectly balanced with each other, and that's why the particle is stationary in its vertical direction. It's not moving up or down. So these forces have to perfectly cancel each other out. Okay, now what I can do is, see, I'm not trying to find Ty, right? I'm not trying to find a component of Ty. I'm trying to find this tension force T over here. So what do? Well, what I can do is, instead of writing Ty, I can write this thing over here. I know that Ty is just T cosine of 30, and I'm trying to find that T. I'm not trying to find Ty. So I can, instead of writing Ty, I can write T cosine of 30, because I'm trying to find this T, not that Ty. That's the tension force. This right here is the tension force that I'm trying to find. That's a component of the tension force. They want the tension force, not a component. So I can do T equals mg over cosine 30. And see, I know the mass, I know the gravitational acceleration. The mass of this particle was 2 kilograms. So it's going to be 2 times 9.81 over cosine of 30. So this is going to be 2 times 9.81 divided by cosine of 30. So that is equal to a weird answer. Hold on, let me check if I did this correctly. So interesting. Okay, wait, I have my calculator in radian mode. Let me get it in degrees mode. Okay, so I have 2 times 9.81 divided by cosine of 30. So I get 22.6. Okay, I get 20, and you can check this on your calculator. You get 22.6 newtons. Now some of you may be like, well, how did you know to use this vertical direction to find the tension force and not this not this horizontal direction. How did I know that? Well, we can try that out. You will figure out that you can't really find out the tension force using the horizontal direction. If you make an equation for the horizontal direction, you find out that your Tx is simply your centripetal force, because there is no other force. So Tx is your centripetal force, and you're not trying to find Tx, right? You're trying to find that tension T. So if you put your tension T over here, so you know what Tx is? Tx is basically all of this. Tx is T sine of 30. If you put that in here, T sine of 30, and then instead of Fc, if you put mv squared over r, you'll realize you don't have all of the information to find T, because you don't know the speed. You do know the mass. So you do know the mass, you do know the radius, but you don't know the speed, and you wouldn't have the T. Okay, you wouldn't have the T. So I found the T using this vertical equation. That's why I know what T is. But imagine if you didn't do all of this step and you didn't know this, then you would not be able to use this horizontal equation to find the T variable, because you would have your speed as your unknown, and you would have that tension as your unknown. So you wouldn't be able to solve an equation for two unknowns. However, now that I do know this guy right over here, this 22.6, I can simply put it in place of that tension. So 22.6 over here in place of this tension. I can put sine 30 over here. I can put my mass value, which is 2 kilograms, v squared, and r is 0.6, I believe. 0.6, yes. We can put 0.6 over here, 0.6 over here. So all I'm trying to find is this speed variable. So I can rearrange this equation. So this is going to be, this 0.6 is dividing over here. It's going to go over there and multiply. And this 2 is multiplying over here. It's going to go there and divide. So I'm going to have v squared equals 0.6 times 22.6 times sine of 30 divided by 2. And I then can take the square to the other side. So it's going to become a square root. Now I have a square root, and therefore I can now solve this. So this is going to be 0.6 times 22.6 sine of 30 divided by 2. So this is going to give me 1.84. It's going to be 1.84 meters per second, and that right there is your speed. So for some problems, you have to be careful. You cannot just dismiss this vertical component, because that vertical component may be giving you some answer. It may be helping you find some variable, and you can only sort of figure this out once you start doing these problems, experiment with things a little bit, and then see how it sort of works out. You sort of make free bodies, and you sort of think about what's going on, and then you sort of understand if some vertical direction or horizontal direction or central direction is important or is relevant to the question, or if it's not relevant. Okay, so now we have a problem on an airplane, and what we have to do is we have to find the angle that this plane makes with the horizontal. They give us some information in the problem statement. They tell us that the plane has a speed of 75 meters per second, and the radius that it's turning is 800 meters. Now, we already did a intuition sort of understanding on a plane that is banking. We sort of understood that it looks something like this, and so we're looking at it from the back, and as it's generating lift in that direction, that lift can be divided into two components, Ly and Lx. And of course, the plane has its weight, mg. So these two forces are in the vertical direction, and this lift component x is in the horizontal direction. And when the plane is in sort of this arrangement, it can turn in a circle. It can bank in a circle. And they tell us that if this is the center, this circle is, I believe, 800 meters. Yes, so they tell us that this is 800 meters. Okay, here's what we have to find out. We have to find out, so what angle are they basically talking about? So this is the plane, right? This is the plane, something like this. So essentially, when a plane is horizontal, it's not in this orientation, but rather in this orientation, sort of like this when it's banking. So it basically moves an angle of theta into that banking position. So what they're asking for is they're asking for this angle of theta. So this is the horizontal line it should be at, but it's not at that horizontal line because it's banking, and so they're trying to ask us for that value of theta. Now, we don't know how to find that value, but we do know this is a circular motion problem, and whenever we have a circular motion problem, we use the circular motion equations. We use the second law equation, we use the free body equation. So we're going to do just that. So we're going to have our second law equation, which is going to be Fc equals mv squared over r. So this comes from the second law, and then we have the FBD equation, which is going to look something like this. Here's what I want you to do. If you sort of notice that this plane looks something like this plane, I don't know if you guys can tell or not, but it looks something, so this plane is going to have its center of gravity somewhere over here, okay, at its center somewhere over here. If you notice, this plane actually looks like an object. I just draw the center of gravity of the plane. It looks like an object on an inclined surface, okay? And so if you look at it like this, it becomes a whole lot simpler. It's so easy to understand how you're going to solve this problem. Now, I would recommend you guys to look at it like an inclined plane problem, because you guys are definitely more familiar with that. Okay, so what we're trying to do is we have a particle over here. This particle is basically our airplane, and then all of this right over here is basically the body of the airplane, but you can sort of understand it as and you can understand it like an inclined plane, basically. So if you sort of draw the free body diagram, you will have the weight mg acting perfectly downwards, and you would have, well, in an inclined plane, you would have a force in that direction, which you would call a normal force, but in this case, it's not a normal force, it's this lift force. Okay, because remember, this isn't actually an inclined plane problem, this is an airplane flying in air, so it's not in contact with something. So instead, that right there is the lift force. So this right over here is the lift force. And then I can break that lift force down into two components. So I can break it down into its y component. So this would be Ly. And I could break it down into its x component, which would be Lx. And I can erase this over here, and I can sort of draw this with a dashed line to basically denote that this was a real force, and I've broken it down into its components. I don't have to do that, but you guys, it'll make it easier for you guys to understand what's going on over here. Now I'm trying to find that angle theta. So what you can do is, if you use some geometry, what you can figure out is that this right over here, so this right over here, this piece would basically make alternate angles. This would be, this is basically making a z. I don't know if you guys can sort of notice it or not, but this basically makes a z. So due to this fact that it makes a z, if the angle theta is in one corner of that z, the other corner of the z will also have an angle theta. Okay, and so what I can do is I can basically put an angle theta over here. Okay, and therefore, we can basically think about it like this. So what we can do is, I'm trying to use some more geometry, and you guys will understand why I'm trying to use some geometry over here to figure that point out. Give me a second. So if I split this weight component into its two parts, like we do with inclined planes, we realize that this angle is theta. Okay, and this angle is vertically opposite with this angle, so this angle is also theta. Okay, so just use some simple vertical angle properties over there, and I got that angle to be theta. Why is this useful? It will make sense in a bit. Why? So in fact, none of these angles are useful. Just that theta is useful. Why is that useful? It will make sense in just a second. Give me a second, and it will make sense. Why do I need that angle theta? So basically, what I'm trying to find is, I'm trying to find the value of that theta. Correct? How do I find the value of that theta? I have no idea. I just know this is a circular motion problem, and I can use both of these equations. Do I know speed? Let's first answer this. Do I know speed? Let's see. Do I know speed? Yes, I do know speed. Do I know my mass? No, I don't know my mass. So I don't know how much the plane weighs. What happens when you don't know the mass? We have seen in previous problems that sometimes when you are not given the masses usually end up canceling each other out. So maybe we don't need the mass. Okay, who knows? We do have the speed. We do have the radius. We don't know the mass. What's FC? What's providing FC? This is the direction of the circular motion. It's the circular direction, right? Because the plane is going to go something like this in a circle. That right there is going to be the center. Therefore, Lx is what is directed in the center, and therefore Lx is what's providing the centripetal force. So I can write Lx, which is the x component of my lift. This is my centripetal force, and therefore I can say Lx equals mv squared over r. Okay, that's really good. What else can I do over here? So you might want to neglect this part, but you actually shouldn't, because it's actually going to give you some meaningful results in this case. So let's see what this tells us. So this vertical direction, so this is obviously the central direction, or the horizontal direction, whatever you want to call it. It gives us this equation, and then the vertical direction would give us the following equation. So Ly equals mg. Why are these two equal? Well, because they don't say that the plane is going up or down. They just say that the plane is going around in a horizontal turn. It's making a horizontal turn. If the plane was going up or down, one of these forces would be greater or less than the other one. But since that's not happening, they have to be perfectly balanced with each other. They have to be equal to each other. Okay, so now I have all of this. These are the equations that I have. If you think about it, these equations don't have theta inside of them. So I want to find that theta. That's what I'm trying to find. Do any of these equations? So if you think about it, you cannot make more equations than the ones you've already had. You have exhausted all of your possible options for the equations you could make. You cannot make more equations from this second law and this free body diagram. So this right here is your final equation, and this right here is your final equation. So no more equations from these two ideas. Therefore, do they have a theta? No, they don't. That's what I'm trying to find. My angle with the horizontal. That's what the question told me to do. None of these equations have theta. So my task now is, how do I find an equation that has theta, or how do I do that? So if you think about it, you divided this lift component. So you had this lift component L, you divided it into its y part, and you divided it into its x part. Whenever you divide something into its components, you know from trigonometry that you need to have angles. You use trigonometry to divide a force into its components. Therefore, that's why it was so important for me to basically find out this angle theta at the start, because using this angle theta, I can now figure out that, hey, look, so if I just drag this Lx vector, I can put this over here, and I get a triangle. Wait, if I grab this LX vector and I put it over here, I basically get a 90 degrees triangle. So this is the X component of my lift. This right here is 90 degrees. Check this out. Check this out. I have basically found out that my LX, you use some trigonometry and you'll find out that your LX is basically lift times sine of 30. Oh, sorry, we don't know if that's 30 or not. We know it's theta, sine of theta. And if you do some trigonometry, you will find out that Ly is equal to L of cosine theta. Great, now you have equations that have theta inside of them. Okay, but here's the problem. If you look at these equations, you can't really find thetas using these equations, can you? Think about it. Think about it. You don't have this L. You don't know this Lx. If you're trying to find theta using this equation, you cannot do that. You don't have any known in this equation. If you do the same with the next equation, this right here is an unknown, this right here is an unknown. So you can't use either of these equations. What are you going to do? Well, guess what? You know stuff in this equation and you know stuff in this equation. But those equations don't have a theta. Well, guess what they do have? They have Ly, and they have Lx, and they have Lx. Guess what you have in these other equations? You have Ly and you have Lx. Isn't that just great? So what can you do? What can you do? You can basically substitute equations. You can substitute this guy into this guy and this guy into this guy. Okay? And then basically what's going to happen is once you do that, let me just do that and I'll show you something that happens. So this would be L sine of theta is equal to mv squared over r, and this would be L cosine of theta times mg. Guess what happened? Guess what just happened? Now you have two equations that have thetas inside of them. Isn't that perfect? Here's what you did. So initially you started your problem off. Okay, now I want you guys to know this. Nobody knows when they're solving a new problem for the first time. Nobody knows how you're going to find theta. Nobody knows how you're going to find the unknown. But what you do know is you know the first principles. You know that you're using circular motion, so you have to apply the free body and the second law. Once you do that, you also know that if you're breaking a force down into its components, you're going to apply trigonometry. So you start from first principles. You start from those ideas. You start from first principles. You keep on playing with the equations you get, and you sort of somehow arrive at this conclusion. And at this conclusion, it's really obvious. Okay, now I know how I'm going to find my answer. So when you read this problem, there's no way you can figure out what to do. If this is a new problem, there's no way you can figure out what's going to happen in this problem. But if you start from first principles, start doing the problem, don't forget that you're doing a circular motion problem, so you can use the second law, you can use the free body diagram, keep those rules in your mind, keep this idea of trigonometry in your mind. You can come up to this conclusion at which things are really obvious. And maybe they're not obvious to you even right now, but they will be in just a second. Okay, so I have equations that have thetas inside of them. And guess what? I know this V, I know this R. I know this, I don't actually know this M. I don't know this M, but I know G. G is always 9.81. Okay, what do I not know? I don't know this L. I don't know this M. I don't know this L over here, and I don't know this M over here. The theta is what I'm trying to find out. Guess what? The things that you don't know. So this is the same L in both of the equations because it's the lift, and this is the mass, same mass because it's the mass of the airplane. Guess what? Sometimes they don't give you variables because those variables will cancel out when you're trying to solve and get an answer. These variables are going to cancel out again, and I'll show you how you can do that. So here's what I'm going to do that. This equation has L, this equation has L. What I'm going to do is I'm going to basically substitute one of these equations into the other equation, and I'll show you guys how I can do that. So when I do that, I will basically get rid of this L variable and basically get rid of this L variable over here. I'm going to get rid of this M as well, but first I'm going to get rid of this L. Let me show you guys how I can do that. So you can pick any of these equations. You can pick the first one, you can pick the second one. I'm just going to go with the second one. And I'm going to make L the subject. So L is going to be mg cosine of theta. Okay, and so what I can do now, when I have L is equal to mg cosine of theta, what I can do now is I can basically take this new equation that I've just rearranged over here. I mean, it's not the new equation, it's still this equation. I just rearranged it, made L the subject. I can now substitute this L in this L over here, and then my equation won't have any L's. So instead of this L, I can now write mg cosine of theta sine of theta equals mv squared over r. Good news. No more L variables. Isn't that perfect? So let's sort of simplify this a little bit. This is going to be mg sine of theta cosine of theta equals mv squared over r. No more L variables. Do you see that? Do you see how we just got rid of the L variables? Guess what? We can get rid of the M variables as well. So you can take any of these M's. So let's say you take this one. You take it to the other side of the equation. It's going to divide because it's multiplying on this side. You take it to the other side of the equation. It's going to divide. And guess what? Boom, boom. Cancel those two guys out. Now I just get g sine of theta cosine of theta equals v squared over r. I know v, I know r, I know g. I'm going to send the g on the other side. So this is going to be sine of theta over cosine of theta equals v squared over rg. So the g was multiplying on this side. When I send it to the other side, it's going to divide. Okay, but now I have a problem. I have sine theta over cosine theta. How do I solve this out? If this was just sine theta, I could have, and if this was just sine theta equals v squared over RT, or just cosine squared theta, what I could have done is I could have sent that sine term to the other side, turn it into a sine inverse, and I could have solved that out. But unfortunately, it's a sine squared over cosine squared. It's a sine theta over cosine theta. I've never seen that. How do I solve this out? And well, if you guys are taking math, then there's this identity, which is basically sine theta over tan theta. Sine theta over cosine theta. And this identity basically solves out to give you tan theta. Now, of course, this is for you math guys out there. You guys probably won't get this. You guys probably won't get a problem like this in your physics exam because it requires you to take math. But some of you are taking physics but are not taking math, so A-levels probably won't give you such a problem in your physics paper. But just for the sake of solving this and just for the sake of improving our problem-solving abilities, I've included this problem in this video. And it's a useful identity to know. Sine divided by cosine gives you tan. So guess what? Instead of writing this guy, you can now write tan. And it's so easy right now. So easy right now. All you have to do is you have to take that tan to the other side. It becomes a tan inverse v squared over rg. You know v, you know g, you know r. Guess what? You can solve this problem. Now let's try and solve this out, see what we get. So theta is going to be tan inverse. What's we? We, I believe, was 75. So we was 75 squared over what's r? R was 800 times 9.81. That's the value of g. Let's solve this out in our calculator. So tan inverse 75 squared divided by 800 times 9.81. We solve this out and we get 35.6 degrees. Theta is equal to 35.6 degrees. That right there, ladies and gentlemen, is your answer for this particular question. Now, imagine you have a circle. So you have a circle, and let's say it has a radius r. Now, r could be anything. R could be 1, it could be 2, it could be 3, it could be 4, 5, 10, 1 billion. It could be anything. You have a circle with a particular radius. What you do is you basically, this right here, this is called the circumference of a circle, all of this length that goes around the circle. It's called a circumference. What you do is you select part of that length. So let's say I select part of it over here. So part of it over here, starting from here, ending till here. And this part has a length of r as well. So basically, if you have a circle of radius 10, I'm selecting a part or some length on its circumference, which is also equal to 10. So that part that I select, I intentionally make that part equal to the radius of that circle. Now, once you select this, well, what is this called? This is called this length. It has a special name. It's called the arc length. Okay. If you have an arc length that has the same magnitude as the radius of that circle, what you can do is you can basically extend out that arc length from its endpoints all the way to the center of the circle, and you basically get an angle. So you get an angle which we can call theta over here. Now this angle has a specific value. This angle, or let's not call it anything for now. This angle will have a specific value. It has the value which we call 1 radian. 1 radian. If you're wondering how much this is in degrees, it's around 57, I believe, or 52 something degrees. I'm not sure exactly. You can do the conversion yourself. The way that works is you can take this 1 rad and you can multiply it with 180 divided by pi. And that's going to tell you how much this 1 radian is in degrees. So you're basically going to get some angle over here. And that angle is what we call 1 radian. So the condition to make that angle, the condition to get that angle, is you have a circle of radius r, and you select a arc length on that circle, which is also equal in length to that radius. And then you take the endpoints of that arc, you join them to the center of the circle, and you get this angle. That angle is called a radian. It has a special definition, so it's called the angle formed at the center of a circle of radius r, when an arc length of radius r is subtended from its endpoints to the center of the circle, And this is the official definition that you will be writing in the exam. So all of this basically just means all of what I've explained over here in this picture. Okay, so that's what a radian is. Now, how do we convert from a radian to degrees, and how do we go from degrees to radians? So radians, let's say this is radians, and let's say this is degrees. So if you want to go from radians to degrees, let's say you want to go from radians to degrees, what you do is you multiply with 180 over pi. So you multiply the value you have in radians with this fraction 180 over pi, or it could be it could also be 360 over 2 pi. But this would simplify to 180 over pi because this 2 times 1 is 2, 2 times 180 is 360, so it simplifies. And if you're going from degrees to radians, you keep the fraction the same. So it's the same fraction, but it's flipped. So pi is in the numerator, 180 is in the denominator. So still the same fraction, but stuff is flipped. Okay, so going from radians to degrees, 180 over pi, you multiply with that. Going from degrees to radians, multiply it with pi over 180. Okay, so that's how you can convert from degrees to radians and radians to degrees. Now we know what a radian is, we know how to convert. Let's get on into this formula. So there's this formula, basically, so the way we define a radian is we basically use the idea of a radius, we use this idea of an arc length, and then we say, hey, when we get a radius and we get an arc length, and we basically subtend the arc length, we're getting this angle. So there's actually an equation that combines that radius, that arc length, as well as that angle. So basically, the angle, the equation that combines all of this is S, or let's call it, let's call it S. Or maybe we can call it A. So we can call it A for arc length equals r theta. So what's A in this equation? A is the arc length. A is the arc length. R is the radius of the circle. Or, it could be the radius of a circle, could be the radius of half a circle if you have half a circle. Theta is the angle formed by the arc, and this theta is always going to be in radians. So if you use this equation to find theta, you're going to get the value of theta in radians. Theta is the angle that that arc will be forming. I'm just going to explain that in a second. If you use this equation, let's say you have the arc length and the radius, and you use it to find theta, that theta is going to be in radians. Okay. If you are using, let's say, this theta and this radius r to find the arc length, then you need to make sure that the angle theta you're putting into this equation is in radians. Otherwise, it won't work. Okay. Let's talk about what an arc is. So if I draw a circle over here, and let's say you could have, let's say this is the center. You could have a part on sort of a length on the circumference, let's say this much. And it's not necessarily equal to the radius. It could be, let's say, even bigger than a radius. So I'm going to call this A. So there's some arc, right? And what I can do is I can basically join the endpoints of this arc to the center of the circle. And what I have right now is a pizza slice. Now, what I can also do is, let's say I take this part on the circumference of the circle. So all of this remaining part, I take this on the surface or on the circumference of the circle. And now when I sort of join this part to the center, I get sort of something that looks like a Pac-Man. So both of these things, both of these shapes, they are called sectors of a circle. So this would also be a sector, and this would also be a sector. You can call them pizza slice or Pac-Man, but more formally they're called sectors. Okay, so both of these sectors are going to have their own angle theta. So this sector is going to have some angle theta over here, and this arc length over here is going to have some angle of theta. The way we can find that theta, or the way we can find the radius of the circle, or the way we can find the length of the arc length, is basically by using this formula. So if you know any two things, you can find the third one. If you know the arc length and the radius, you can find the angle. If you know the angle and the arc length, you can find the radius. If you know the if you know the angle and the radius, you can find the arc length. But remember, the angle has to be in radians. That's really important for this equation. Okay, so we now know what a radian is. We now know how to convert a angle in radians to degrees and vice versa. We know how sectors work and what's the equation that can allow us to find, say, radius, or say theta, or say arc length using this formula we just did. Here's what this formula also lets us, this formula sort of gives us in sort of this new equation when we divide it by time. So we have this equation, which is A equals r theta. So this is some value for arc length. This is basically, it could be in meters, could be in centimeters, could be in different magnitudes. This right here, this radius would also be in centimeters, meters, inches, feet, could be in units. This theta, we know this right here is going to be in radians. So basically what you can sort of do is you can divide this equation. So you can divide this equation by time. So you divide this equation by time. And what that's going to do is basically you're going to get this new equation, which is going to be this arc length over time equals this r theta over time. And watch this. So A is basically some distance, right? It's basically some length. A length is basically a distance. So in fact, A over t, or arc length over time, is basically another way of saying some distance divided by time. And if that rings a bell, what this is it's basically a speed. Okay, if you have some distance if you have some distance and you divide it by time, that is basically equal to speed. So what is arc length? Arc length is basically some distance. If you divide it by time, you get the speed. What about this theta over t? Now this is something that is new. This theta are basically the angles you cover, the angles a body can cover. Okay, so let's say if you are in a circular path, let's say you're over here, let's say you go all the way to this new position right over here. So if this is the center of the circle, well, you've covered some angle. So you started off at that position and you ended at that position. So you basically covered some angle theta over here. So theta are the angles you cover when you're doing a circular motion. And when you divide it by time, you are now getting the angular speed. So this speed, this distance over time, is your linear speed, basically. You can call it your linear speed. It's the speed at which you cover distance. Okay? This thing right over here, theta over time, is your angular speed. It's the speed at which you cover angles. So in fact, what I can do is instead of writing theta over v, I can then instead write this new variable, which we're going to call omega. Omega means the angular speed. It's the symbol for angular speed. So let me just write it over here. So theta over t is basically the angular speed omega. So you get this new equation, and this equation is really, really, really important. Let's talk about the units of omega. So this is your linear speed. This will obviously be in the SI units meter per second. The radius will maybe also be in its SI units, which would be meters. And then omega, the angular speed. Let's talk about the units of this. So theta is in radians. Time is in seconds. So omega is simply radians per second or rads per second, or it's just per second. Okay, so you don't have to sometimes write radians. It's not necessary to write radians. You can just write per second. Okay, but more specifically, it's radian per second. Again, writing radians is not necessary, but yeah, it's you can write it if you want to be more specific. Okay, so omega is radians per second. That's the units of omega. Or again, you can also write per second. Simply, you could write per second. Those are just fine. Okay, so let's sort of, we've done a lot of math over here, and again, you do need to remember this equation. V equals r omega is a really important equation. A equals r theta is a really important equation. You do need to remember both of these equations. Let's sort of see what these quantities even mean. What velocity, sorry, what this linear speed, what this angular speed, what all of this stuff even means. If I draw a circle over here, so that's my circle. Let's say I have an object right over here, and it covers some, let's say it sort of travels and ends at this final position. Imagine this is the center of the circle. So if I draw two lines to the start and to the end, this person or this body has covered this angle theta. Okay, this is the angular distance. We call this theta the angular distance that the object has covered. And then it has covered some linear distance as well. So that would be this arc length over here, this arc length in red up there. This is called the arc length or the linear distance the body has covered. So the arc length it covers is called the linear distance. The angles it covers is called the angular distance. So let's say you have an object over here, and it covers all of this distance, gets all the way to this position. So it would have this angle that it covered right here, theta, and this linear distance that it would cover over here, which I can call a. Okay, here's the important stuff that I want you guys to know. Imagine there are two circles. So imagine, I'm just going to erase this. Imagine there are two circles. So it's a circle over here and that outer circle. And here's what's happening. So I'm going to select this, I'm going to put this in here. And both of these circles have a same center, have a common center over here. Now, you have a particle over here, which travels from the starting position to that ending position. So I'm just going to put an arrow to denote their direction of motion. And then I have a particle, and a different particle over here that starts at this position, ends at that position. And I'm just going to denote the direction of motion by an arrow over here as well. Goes over there. So I want you guys to check this out. If you join this part to the center, here's what you guys should look at. Both of these objects cover the same angle theta from their starting position to their ending position. But check this out. The arc length or the linear distance of the object in the smaller circle is clearly less than that of the one in the larger circle. Isn't that interesting? They're both covering the same angular distance. They're both covering the same theta. But due to the radius of their circles being different, they both end up covering different arc lengths. So it comes straight from this formula S equals R theta. So theta is the same for both of these circles. So we can say theta is basically constant. The angle theta they cover is constant. And so the relationship between the arc length, my bad, this instead of writing S, I should have written A over here. Whoa. So this is A. This is the arc length A. The relationship between the arc length and radius is directly proportional, given that theta is constant for both the objects. They're both traveling the same angular distance. So basically, if you have a greater radius, you're going to have a greater arc length. You're going to cover a greater linear distance. That's what's happening. So since the smaller circle has a smaller radius, it covers less linear distance for the same angle theta, whereas that larger circle, the object covers more linear distance in that larger circle because it has a larger radius for the same angle theta. This is really important. So what's going to be interesting over here is that both of these objects, so let's say both of these, both of them start their journey at 0 seconds. So this is the starting, these are the starting positions and these are the ending positions. So both of these particles or objects start their journey at 0 seconds and they end their journey at 10 seconds. So the time it took would be 10 seconds. Here's the interesting part. In 10 seconds, they both covered the same angular distance. They both covered the same theta. So let's say theta is equal to some angle. Okay, I'm not going to write it, but let's assume theta is some angle. They both are covering the same angular distance in a time of 10 seconds. So therefore, they both will have the same. So both have same angular speed. Both have same omega, the same angular speed. But since both are covering different linear distances in time 10 seconds, this particle, let's call this P, let's call this Q. Since P covers a greater distance in the same time, it will have a higher linear speed, or the normal speed, if you want to call it that, than particle Q, because particle Q covers less distance in the same amount of time. So both will have different linear speeds, or if you want to call it that's what we can call it. So that's really interesting. For the same time, particle P covers more distance, and so it has a greater linear speed than the particle Q. But they both have the same angular speed. Now that's a really interesting coincidence. And again, it sort of comes straight out from this formula, V equals R omega. If you're keeping R constant, because if you're saying they're both covering the same angles, you can say the relationship between V and R is a direct relationship, and therefore if you have a greater R, you will be covering, you will have a greater speed, given that omega is constant. Okay, so this information is really important. So sometimes what can happen, the conceptual understanding behind this is really important. Two particles can have the same angular speed, but they can have different linear speeds. This understanding is really important. Okay, let's talk about this idea of what this implies for centripetal acceleration and centripetal force. So again, considering both of these particles, I can draw a new figure over here. Okay, so let's say this right here is my center. That right there is my particle. Let's call it particle P. So particle P is now moving in this circular path, and of course, since it's moving in a circular path, it should have a centripetal acceleration and it should have a centripetal force. Now, we've done this equation for the centripetal acceleration, which is v squared over r, and we've done this equation for the centripetal force, which is mv squared over r. Here's the new equation in terms of the angular speed. Okay, so these are the equations for centripetal motion in terms of linear speed. Now the new equations for centripetal acceleration and for centripetal force that we're going to be deriving in angular speed, we're going to take a look at those. So here's what we know. We know that omega is equal to the angular distance divided by time, and we know that angular speed is equal to radius times the angular speed. So the linear speed v is equal to the radius of the circle times the angular speed of a particle covering distance in that circle. What we can do is we can basically use this equation right over here, and we can chug it into this equation, and we can chug it into this equation, and we'll see some cool things happen. So the centripetal acceleration is going to be, instead of v, I can write r omega, so it would be r omega squared. Instead of v squared, it would be r omega squared. So I just replaced v instead of r omega. I have an r at the bottom, and so this is going to get me r squared omega squared over r. Now, the r cancels out with that square, and so this new equation that I get is equal to omega r, or r omega, if that's what you want to call it. Sorry, my bad. It's omega squared times r, okay? Or r omega squared, whatever. The order doesn't matter. The centripetal force, what about this one? So again, see, this is going to be m v squared over r, and we now have m, instead of v squared, we can write omega squared r squared Okay, so what I did is I just put this value of v in here and then squared the omega and r. So I get this new equation, and I can simplify this, cancel out this r with that square, and I now get the centripetal force is equal to m omega squared r. Okay, so these are the equations 1 and 2 for when you have the linear speed. Now, when you are given the angular speed, the equations are then going to be AC is equal to omega squared r, and FC is going to be equal to m omega squared r. This right over here is your first equation. This right over here is your second equation. Now, these equations for the angular speed, if you want to learn something from all of this, remember this equation and remember this equation. That's all you need to remember. You don't need to know how to derive them, but if you do know how to derive them, that's going to be good. Okay, so when we were given the linear speed, we were using these different equations that were in terms of linear speed. Now, when we will be given the angular speed, we will be using these different equations that are going to be in terms of angular speed. Right. Let's talk about, now since we're done with this, let's talk a little about the frequency and the time period. So what's a time period? Let's talk about that. So a time period, it has a really specific definition, and I'm denoting it with capital T to differentiate it from small t, which is my variable for time. So time period is the time it takes for a particle to complete one full rotation. So if you have, let's say, a circle right over here, and this particle starts at this position, goes all the way around a circle, and ends back at this position, the time it would take is what we call the time period. Okay? If, let's say, the circle goes around, so let's say they tell you that this particle goes around this circle three times, it goes around the circle fully three times in, let's say, 30 seconds. If you want to find out time period, you use its definition. So time period is the time it takes for a particle to complete one full rotation. So if three rotations are taking 30 seconds, we are trying to find how much does one rotation take. So we can do, well, how much does one rotation take? So that would be, let's call it some time. So let's call it, it's capital T. So let's call it capital T because that's the time period. So we're trying to find the time period. And so what you can do is you can basically use the ratio. I'm basically using the ratio method over here. So this is the ratio method. You can use any other equation that you know to find the time for one rotation. I'm using the ratio method. So that would be 3t equals 30 seconds, or I'm just going to write 30 for now. And then what I can do is I can do t is equals to 30 over 3. So t would be times 1 is 3, 10 is 30, so it would take 10 seconds for the particle to complete one rotation, and therefore its time period would be 1. And sometimes you can have this situation where instead of just directly telling you the time period, they make it confusing for you and they give you this mumbo-jumbo equation, and so you have to work with this thing. Okay, so there's that. Let's talk about frequency and time period and what their relationships are. So frequency is basically is the, and let's put the symbol over here as well. So we'll put F over here. This is the amount of complete rotations, or the number of complete rotations or revolutions happening in 1 second. Or more specifically, this is properly written as per unit time. Per unit time means in 1 second. Here's the difference between time period and frequency. So time period, if I draw a circle, time period asks the question of, you go around the circle, how much time did you take? That's what time period asks. Here's what frequency asks. Frequency says, in a time span of 1 second, how many times did you go around a circle? So let's say a particle starts and only ends up at this position, or let's say ends up at this position after 1 second. So the frequency would only be 3/4 of a circle, okay, or 3/4 of a circle. So it only traveled 3/4 in 1 second, okay. So time period, and maybe a circle, maybe a particle starts over here. So let me just draw the circle over here. I have a particle over here, and let's say in 1 second it manages to go around the circle 2 times. So the frequency would be 2. So time period asks the question of, how long does one rotation take? And frequency asks the question of, how many rotations are happening in 1 second? So that's really important. They're both not the same thing. They're really different from each other. And there's actually an equation connecting the two. If I draw that, I write that equation over here. Its frequency is equal to 1 over time period, or if you make time period the subject, it's basically time period equals 1 over frequency. So they're both the same thing. So what are the units of frequency? Well, frequency is 1 over time. So time is in seconds. 1 doesn't have a unit. So the units would basically be s minus 1. And it actually has the same units as the angular speed. Okay. What about time t? So time t is basically t equals 1 over f. That time just has the units of seconds. Okay. Time period is it's about the time that you take in order to complete one rotation. So the time is in seconds. Okay. That's what's going on. So this equation is really important. Now, there's one more equation that I would like you guys to know. And if you want to take away something from all of this, take away this and do at least, if you don't remember the definitions of a time period and frequency, at least do keep their concept in your mind. Let's talk about the equation that I want to talk about. It's basically an equation for, let's say, the centripetal force if you're given frequency and you're trying to find the centripetal force, or if you're given the time period and you're trying to find the centripetal force. You can actually do that, and you don't need to learn these equations. So I'm just going to draw sort of a line over here. You don't need to learn what I'm about to show you, but you do need to see what's going on. These equations are going to be really important. You don't need to know how to derive them. You don't need to learn them, but you do need to know what are the steps and how you get those equations, because there are going to be problems where you're going to be using those equations. So here's what I want to tell you guys. So let's say you have a circular path again, and you have, let's say, this equation for centripetal force, which is, and I'm taking the one that is in terms of linear speed, mv squared over r. And what I'm going to do is let's take this equation, mv squared over r. And what I'm going to do is I'm going to draw a particle over here, and I'm going to make this particle go all the way around the circle, and that it's going to take some time, which is of course going to be the time period t, and it's going to cover a distance which is basically the circumference of the circle, because it's going around the circle one full rotation, and we can find the circumference using this formula 2 pi r. So that's the distance it goes around the circle, and in time period t, because one rotation around the circle is basically a special time that we call the time period. Now what you can do is you can basically see that what's v is the linear speed, right? So v would basically be the speed would basically be the distance covered in a particular amount of time. What's the distance that you're covering in this case? Well, it's the entire circumference of the circle. So the distance would be 2 pi r, and your time would be the time period, capital T. Okay, and so what you can do is you can go into that FC equation and you can put in mv squared over r. And for a second, I'm going to write this. I'm going to separate the r and the m, and I'm going to write v squared like this. And then what I'm going to do is, instead of v, I'm going to write 2 pi r over t. Okay, so this equation comes from the fact that I'm making the particle go one way around the circle, one complete rotation. That's going to be in time period t, and I've then substituted that into my FC equation. Now remember, there was a square on v as well, so you put the square over there. So FC is basically going to be m over r. You square this fraction, you are going to get 4 pi squared r squared over t squared. Okay, and what you can do is you can basically cancel the r's over here. So you can do m over r times 4 pi squared r squared over t squared. You can basically cancel this r with that squared r, and this would give you the following equation. FC is equal to 4 pi squared mr. Okay, 4 pi squared mr over time period t. Now this equation, this t is the time period. Okay, so it's not just some random time. You cannot use this equation for, let's say, when you have a circle and your particle has traveled half the distance, and in some time t, and you chug that time t in here. That wouldn't work. This equation, when you were making this equation, you basically made it for the time period capital T. So you're going to be using that time period capital T in this equation. Okay, now this is the first equation. The second equation would then be, if you use this relationship, that is time period is equal to 1 over frequency f. And using this relationship, what you can do is, if you substitute that relationship into this equation, you can get this new equation. So I'm going to write it like this. I'm going to write it 4 pi squared mr divided by t. Okay, I'm going to, instead of writing it as a fraction, I'm going to write it out as divided by t. And then what I can do is I can basically substitute the frequency equation for time period. That is basically time period is 1 over frequency, and therefore what I can do is, if I change that division to a multiplication and take the reciprocal, this is what I get. And f divided by 1 is just going to be f. And so if I multiply this stuff, I basically get 4 pi squared mrf. And this is the other equation that you can have for centripetal force. So these equations are also really important. And in the same way, I encourage you to do something. I encourage you to sort of figure out the equations for centripetal acceleration. Yeah, figure out the equations for centripetal acceleration using this idea of this idea. If you want to take something away from this video, take away this idea, sending your particle one complete revolution around the circle, taking away this idea that, okay, if I do that, my velocity is going to be 2 pi r over t, and then taking away this idea that time period is equal to 1 over f. If you take away these three ideas, what you can do is, you know that acceleration, centripetal acceleration, is basically equal to v squared over r. What I want you guys to do is I want you guys to use these three ideas, okay, substitute in the value for v, and then what I want you guys to do is come up with an equation that has time period, come up with an equation for centripetal acceleration that has time period, and come up with an acceleration for centripetal acceleration that has frequency. Okay, do these two things. It's going to be a really good exercise. Okay, so let's understand some common angles that you will be seeing in radians. Now, these angles will have pi in them, so the number pi in them. And you may go crazy. You may go like, where the hell does a pi come from? We were doing radians. We know what a radian is, but I don't know why radians is supposed to be measured in pi. Why can it be 1, 2, 3 radians? Why is it 2 pi radian? Where the hell does this come from? Because you're going to be seeing this a lot. So that's what we're going to be understanding right now. And so if you take a circle, I'm just going to draw a circle over here. So that's my circle. Let's say it has some radius r, and r could be anything. Now, here's the thing. So you've done your formula for the arc length, which is S equals r theta. And now here's the thing. So imagine you're going around, you're taking this entire circle. So basically, you're taking all of this length. You're taking its circumference, basically. So here's what happens. When you take its circumference, what you're essentially saying is that the length is going to be 2 pi r, because that's the formula for the circumference. And if that's your value for the circumference, that's the arc length that you're considering. This S, oh, my bad, this was not S, this was A. A was the arc length. Sorry, I'm so sorry. A equals r theta, A being the arc length. I learned it as S equals r theta, so I keep on sort of putting an S there. So if I'm taking the entire circle, my arc length is going to be 2 pi r. That's going to be the length of my arc, or the length of my circumference. So I can take this as 2 pi r, and then I have r theta over here on this side. Now, what you can do is you can make theta the subject. So if I make theta the subject, what I can do is I can divide this r over there on that side, and when I do that, I'm basically going to get 2 pi. And this 2 pi is going to be in radians, because I told you guys that when you use this formula to find the theta, you will always get the value in radians. So this bad boy right here, this is 2 pi radians. Now, what is 2 pi radians? 2 pi radians is basically this entire angle theta, because you took this entire length, you took this entire arc length, you took this entire length, whatever you want to call it. Since you're considering that entire length, your theta is equal to 2 pi. Okay, and in other words, if this was degrees, if you considered all of this length, your theta would be equal to 360 degrees. So in other words, what we're really saying is that 2 pi radians is basically the radian equivalent of 360 degrees. Okay, so it's the radiant equivalent of 360 degrees. So you travel 2 pi radians or you travel 360 degrees, it means the same thing. It means you're going one full rotation around the circle. And so 2 pi 360 degrees is 2 pi radians. 2 pi radians is the same idea as going 360 degrees around the circle. And therefore, imagine if you go half a circle, right? So imagine if you only go half a circle. So what you can do is you can basically, instead of getting the full angle theta, you're now going to get the half angle theta. And so what you can do is you can basically divide this pi radians by 2, and you will end up with pi radians. So you will end up with pi radians. And therefore, what you can say is that pi radians is basically the radian equivalent of 180 degrees. All right. And then you can sort of imagine if you went half of that, so you only go half of that, that would be this part. In degrees, this would be 90 degrees, but in radians, you can divide this thing by 2, and basically that would give you pi by 2 radians. Pi by 2 radians. So this would be the radian equivalent of 90 degrees. Okay, what about 270 degrees? Now that's an important angle as well. So all of this right over here, you start from over here and at that position, that would be 270 degrees. And how do you write that? You write that as 3 pi by 2 radians. And this is equal to 270 degrees. The other angles, you don't have to remember them. I mean, you don't have to remember these one either, because if you want to go from radian to degrees, what you can simply do is you can simply just multiply with 180 over pi. So here's why we take radian value. Here's why you will see radian values in pi. The reason is because, well, you start using this formula, the arc length formula, and since you're using the circumference to find this theta, the circumference contains a pi, and therefore the value that you get for theta also contains a pi. And since you use this pi to find all of these values, therefore these values also contain pi. So that's where the pi comes from, if you guys are wondering. That's why we're sort of measuring some of the radian values in pi. We're starting off with some past paper questions, and the first one is right here in front of us. Part A says, with reference to velocity and acceleration, describe uniform circular motion. So you have to use ideas about velocity as well as acceleration. Now, a key thing that happens in a circular motion is that the velocity or I can write it over here, in fact. So the answer is velocity and acceleration are perpendicular. And I'm just going to put the symbol. You can write the entire thing. This means the symbol basically means perpendicular. And since it's a uniform circular motion, what uniform means is that the speed does not change. The magnitude of velocity does not change. So the speed or the magnitude of velocity does not change. Velocity is constant. You can also write it like that. So the first part was referencing to velocity and acceleration and sort of giving an idea of what a circular motion is. And then uniform is the part where the velocity is held constant. Okay, part B says two cars are moving around a horizontal circular track. One car follows path X, the other follows path Y as shown in figure 1.1. The radius of path X is 318 meters. Path Y is parallel to and 27 meters outside path X. Both cars have the mass 790 kilograms. And the next part says the maximum lateral, which means sideways, frictional force that the cars can experience without sliding is the same for both cars. Now, those are a lot of words. Let me just break down what it says. So if you read the first line, it says two cars are moving in a horizontal track. One car is on path X and one car is on path Y. As we can see, if you look at the diagram, you sort of have these two dotted lines. One is for path X, one is for path Y. Two cars are sort of moving in these two paths. One is on X, one is on Y. The next line says radius of X is 318, as you can see in the diagram. They say Y is parallel to and 27 meters outside path X. So basically what that means is path Y would be 318. All of this distance is up till path X, and then this distance is going to be the distance to path Y. How do you find that? You do 318 plus 27. So radius of X is equal to 318 meters. Radius of Y is going to be 318 plus 27. That's going to be 345 meters. 345 meters. Okay, they both have the same mass, and the maximum lateral friction that they can experience without sliding is the same for both cars. So that basically means they're both going to experience the same frictional force. Now, when we were doing the intuition of circular motions, we basically understood that cars moving in horizontal circular paths, or that are sort of drifting or racing, what provides the centripetal force is the friction between the tire and the roads. So they're basically talking about that frictional force, that they're both experiencing the same frictional force. Okay, part one, so the first part of the question says the maximum speed at which the car on X can move around the track without sliding is 94 meters per second. Calculate F. Now again, it's a circular motion problem, and I've sort of drilled this into you guys. Whenever you see a circular motion problem, you use two ideas. You use the second law for circular motion, and you use the free body diagram. So the second law would simply be the centripetal force Fc equals mv squared over r. That's the second law. And then the free body diagram would be, so if I draw this path X over here, and you have car, let's call this car X over here, call car small x for this car small x, and big X would then be for the path X. And then let's say this right here is the center point right over here, center point. So right over here, car X is experiencing a frictional force. We are supposed to find that frictional force F. How do I know that F is the frictional force? Well, if you go back to the problem statement, they tell us that frictional force is represented by the symbol capital F. So over here, they're asking for us to calculate that frictional force. We don't know how to do that right now, but as we're sort of doing this second law and free body diagram, we eventually will find out how to do it. Okay, so Fc equals mv squared over r. From the free body diagram, we can draw out the forces. So the frictional force is going to be acting over here. I'm just going to write that with capital F because they're representing frictional force with capital F. That's one force going in. There's no other forces that are being applied in the central direction. If you think about it, there is going to be a normal force as well as a weight that is acting on the car, but we're not concerned about that. We're only looking at the central direction right now. Okay, so this right here is the free body. Now the free body tells us that the net force is basically the centripetal force. Sorry, the net force is basically the frictional force F because there's no other force in the central direction. And for circular motion, we know that we call the net force as the centripetal force, so we can just write Fc equals to that F. Therefore, what we can do from the free body diagram, we now have this information. We know that the centripetal force is equal to the force of friction. So what we can do is we already know how to find the centripetal force thanks to this equation. And since we know that centripetal force is equal to the frictional force, instead of writing Fc over here, we can just write capital F for frictional force because that is the centripetal force, and that is what we're trying to find out. And this would be mv squared over r. So this would simply be the mass, which is 790 kilograms, the velocity, which is 94 squared, and the radius of this car small x, which is going to be, we can scroll up over here, and we have the radius for x, which is 318 meters. So we can put that in here, and we can try and solve this out on our calculator. So let me just do that. It's 790 times 94 squared divided by 318. That is 21,000 So let me just write that over here. 21,951.1. Okay, that's good enough. Right. Moving on to part number 2, says both cars move around the track. Each car has the maximum speed at which it can move without sliding. This bit is important. Each car has the maximum speed at which it can move without sliding. Why is that important to us? That basically tells us, let's see if you look at this statement over here, where is the statement? So the maximum lateral friction that the cars can experience without sliding is the same for both cars. That is important. Now they tell us that the cars are not going to slide. So they're not going to slide, and they're both at their maximum speeds. So they're not sliding, and they both have the same frictional force that they can go at without sliding. That's basically a fancy way of saying that they're both experiencing the same frictional force, which is the one we found in this last part, 21,951.1 newtons. How do I know that this is the maximum frictional force? Well, because see, this car X was going at its maximum speed without sliding. Okay, and so if it's not sliding, that means that this force is going to be 21951. And they say that the maximum force without sliding is the same for both the cars. So this 21951.1 newtons is basically going to be the same for both the cars. Okay, so now what I have to do is I have to complete this table by placing a tick in each row to indicate how the quantities indicated for the car on path Y compared to that on car X. So I have to compare certain quantities of car Y to car X. The first one is centripetal acceleration. Second one is maximum speed. Third one is time taken for one lap of the track. Now, when you have these kinds of questions, what you want to do is you always want to make use of your equations, okay? And you always want to make use of your equations, and you want to think about what's happening. Now, each quantity will require you to use different equation. Let me just show you the first one. So for the first one, I'm trying to find out centripetal acceleration. I'm trying to compare centripetal acceleration. Now, what's an equation for centripetal acceleration? So there are two equations. So this one, v squared over r, and there's this other equation, which is the centripetal force equals mass times centripetal acceleration. Which one do you use, okay? So you're trying to compare stuff. Which equation should you use? Now, ideally, you want to use an equation where where you know what's happening with the quantities. For example, what do I mean by that? Let me just take equation 2, for example, over here. Do I know the radius of car 1 and car 2? Well, yes, I do know the radius. So I know that if I go over here, I know that ry has a bigger radius than rx. Do I know their maximum speeds? I don't know that. Yes, I know the maximum speed for car X, which is 94 meters per second, as they sort of give me that in the question, but I don't know the maximum speed of car Y. If I did, maybe I could just sort of use this formula for both the cars, find out their centripetal acceleration, and therefore just tick one of these options. But I don't know the velocity for car Y, and maybe you think about some way using which you can find that velocity. But I have another method over here to sort of figure out what box to tick over here, and that is go with this other equation, FC equals MAC. How do I use this equation? So you rearrange this equation for A, and that is going to give you FC over M. Now check this out. FC is constant for both the cars. M is constant for both the cars. How do I know that? See, they use the statement. If you read the question statement for part 2, they say each car has the maximum speed at which it can move without sliding. So they are at their maximum speeds, and at their maximum speeds, they are not sliding. They're at the maximum speed at which they do not slide. If they go over that speed, they are going to slide. The friction will not be sufficient to hold them in a circular motion. However, that is not the case. They're at the top speed at which friction is sufficient to hold them in that circular motion. Now, this previous part tells us that the force that they can experience, the maximum force, the maximum frictional force that they can experience without sliding is the same for both the cars. That means that FC will be a constant for both car X as well as car Y. How do I know that the mass is constant? If you read the problem statement right over here, this is where they say that the mass of both cars is 790 kilograms. That means the centripetal force is constant, the mass is constant for both the cars, therefore the acceleration must be the same for both the cars, because it cannot be different. If they have the same value of FC, the same value of M, then this fraction will solve out to give you only one answer. Therefore, we tick this box right over here. Now, see how we didn't have to even do any calculations? You can simply use an equation, and just by looking at the algebra, you can understand a lot from it. Okay, moving on to maximum speed. How do we find out if the maximum speed of y is going to be greater than y, equal to y, greater than x, equal to x, or less than x? Now you use a different equation. So what are the equations that involve the velocity? Now, one of those equations would again be this one right over here, and it would be, again, this equation FC equals MAC, another form of it, where instead of writing that acceleration, you just write mv squared over r. Okay, which equation do you use? That's up to you, but I'm going to use this one right over here because I know that their acceleration is not changing. You can go ahead use this one if you want. I'm just going to use this one right now. For this one, the second law equation, it's the exact same process, the exact same thinking steps. I'm going to use the second one because it's just more simpler and it has less variables to worry about. So the equation is centripetal acceleration equals v squared over r. Now, how do you, in this equation, it's not as simple as in the last step where two things were constant and I just go ahead and tick the box that y is the same as x because everything else is the same. In fact, two things are varying. The v is going to vary. The radius is going to vary. Why is the radius going to vary? Well, because we just know that from the question. Path y is larger than path x. Why is the velocity going to vary? The velocity is going to vary because, well, if you're on a bigger path, you may have a different speed than if you're on a smaller path. If you both cover this, let's say in time 10 seconds, car x, so let's say car x and y start over here at this position, and at time t equals 10 seconds, they end up at this position, then car y would have covered more distance because it's moving on a different path. And so it for the same amount of time, car y would have a greater speed. It covered more distance in the same amount of time. So I don't know what their speed is. I don't know what their v is, but I do know what their r is. But I do know what both of their r is. I do know what both of their radius is. But again, radius is different. Radius is not the same for both the cars. It's not the same as the last problem where I can say, look, my force is constant, my mass is constant, and so this quantity must not change. So I have two quantities that are changing, one quantity that is not changing. What do I do in this particular situation? Well, in this particular situation, what you do is you rearrange the equation to see how this thing changes with respect to this thing. So you're basically trying to see how one varying quantity changes with another varying quantity. So you get them on different sides of the equation. So if I do that, it's going to look something like this. V squared equals RAC. Okay, or I can even write it like this. It's the same thing, but I'm just changing the format a little bit. V squared equals the centripetal acceleration times the radius r. Now, here's the important thing. Acceleration is constant. I know that this term is constant. How do I know that? Well, because I've checked this box right here. That's what I figured out in the first box, right? I figured out that acceleration is constant. Now, if this rings a bell, doesn't this look something to the form where you have one quantity, let's say y, and you have kx, and x, and then this k is a constant term, and therefore this is a mathematical thing to do, but what you can therefore say is you can say that, hey, look, y is directly proportional to x. So if you have a constant term, you can sort of take that constant term and this equal sign, make them disappear, get a proportionality sign instead of it, and sort of look at how those two terms are comparing with each other. If this was like this, 1 over x, then you would say, well, now they're inversely proportional to each other, not in direct proportionality. But in this case, what's happening is this a is constant, and so you can make this equal and that ac disappear, and you just get v squared is directly proportional to r, and now you can see that these two things have a direct relationship with each other. If you increase r, your velocity will increase. If you decrease r, your velocity will decrease. So I know that the radius of y is greater than the radius of x. Obviously, we know that from over here. So ry is 345, rx is just 318. If we know that ry is greater, we know that the velocity or the maximum speed will be greater for car y. It's in a greater radius, it will have more speed. Therefore, we check the last box. Y is greater than x. Okay, so we just used a simple equation, basically saw proportionalities and then figured what was going on out. Now we're going to do the exact same thing for the last part. Time taken for one lap of the car. And what does this mean? This is basically, they're talking about the time period. Time period. What is time taken? What's the definition of a time period? It's the time taken for one object to complete one lap or one circular revolution in a circular path. So that's exactly what they're asking for over here. They're saying time taken for one lap of the track. And we do have an equation for this. That equation is basically, we just found that out in a while ago, and that was the centripetal force is 4 pi squared m times r over t squared. Now, there is another equation as well that you can use, which would be, or rather, just use this equation for now, because this is the main equation that we highlighted in the previous steps. Let me just go back over here. Where was I? Where did we find that out? So it was right over here. Right over here. And of course, I forgot a square on this t. Let me put that square back. So it was this equation that we derived. That's the equation we're going to use in this part. It's the time period equation, and we need to find out if the time period is going to be different or the same. Now, again, see, it's not as simple as the first box, because you have some quantities that are varying and some quantities that are not varying, that are constant. So let me just show you the constant ones first. So constant ones are going to be with green, and then the varying ones are going to be with red. Okay, so constant, let's talk about that. Centripetal force is constant because we know they're both experiencing the same friction. The number 4 is constant, it does not change. Pi is a constant number, it's 3.142. When you square that number, you're also going to get a constant. That's not going to change. M over here is also a constant. M does not change. Okay, M is 790 for both the cars, as they tell us in the question statement. And so the only quantities that are varying are this radius r and this time period t squared. Okay, I want to sort of do the exact same thing that I did over here. Whenever you have constant terms and varying terms, you basically want to do the same thing. You want to get the constant term, you want to get the varying terms, the terms that are varying on different sides of the equations, then turn the constant terms and the equal sign into a proportionality symbol, and then figure out what the relationship is between the varying quantities. What do I mean by that? You guys will see in a second. So I'm just going to split this 4 pi squared m from the rest of this. So now it's just 4 pi squared m times r over t squared. R over t squared. Let me just collect all of these constant terms on one side of the equation. Fc over 4 pi squared m. And now I have, this is equal to r over t squared. So I have the constant terms on one side. Now let's get my variables on different sides of the equation. So I have two variables, r is varying, t squared is varying, because obviously the time period, when the time period is going to vary, the square of it is also going to vary. So let me just get these terms on different side. So t squared times f over 4 pi squared m is equal to r. And now here's what I want you to notice. This constant, we can sort of write all of this is a constant, so it sort of acts like a k term, which is a constant term that you've probably seen a lot of times in your math class or in your physics class, and therefore we can make this constant and this equal disappear, and we can sort of just write t squared is directly proportional to r. Now, what can we notice? If you have a greater radius, that means you will have a greater time period. If you have a smaller radius, that means you will have a smaller time period. Why? Because they're in direct relation to each other. They are directly proportional to each other. If they were inversely proportional, then the situation would be different. An increase in one would cause a decrease in the other one. So what we can sort of see is that since ry has a greater radius, it will also have a greater time period than x. So we can go over here and we can check the last box, the time period of y is greater than x. Now you could have done the same thing intuitively. Let me just explain it to you guys how you could have done this intuitively, but you don't want to do that because sometimes intuition can lead to confusion. So the first thing is centripetal acceleration. Why would it be the same for both of them? Well, because again, they have the same mass, they have the same frictional force, therefore their acceleration must be the same. What about maximum speed? Well, car y was going in a greater circle than car x, therefore car y would have a greater maximum speed than car x. And so if you're moving in a greater circle, obviously it's going to take more time for the car to cover the distance, and therefore that's why the time taken for one lap for y is greater than for car x. We're on the next problem. Part 1 says, state what is meant by centripetal acceleration. And this is exactly like the problem we did before. So what is a centripetal acceleration? Well, it's the acceleration that is perpendicular to the velocity. So such an acceleration is basically known as your centripetal acceleration. Moving on to part B, says an unpowered toy car moves freely along a smooth track that is initially horizontal. So it's basically saying that this car is unpowered, meaning it has no engine. So if there were frictional forces, which I don't see they mentioned any, if there were frictional forces, this car would essentially lose its velocity. It doesn't have an engine that's continuously sort of maintaining a velocity. Around which, so and this track is initially horizontal. It's perfectly horizontal up till this point, after which it loops. So the track contains a vertical circular loop around which the car travels, as shown in figure 1.1. Now this loop right over here that they give us, this is a vertical loop. So what's the radius and what's the diameter of it? They give us the diameter of the loop from this one edge all the way to that other edge. That is 62 centimeters. And in fact, if you read the next line, the mass of the car is 230 grams and the diameter of the loop is 62 centimeters, then we know that the diameter of this loop is 62 centimeters. Assume that the resistive forces acting on the car are negligible. So there is no frictional force. Also, let's figure out the radius. And let's first figure out the diameter. So the diameter right now is given to us in centimeters. You never want to do things in centimeters. You always want to convert things into meters, into their SI units. And so the first thing we're going to do is we are going to convert this into meters. So this 0.63 is in fact 0.62 meters, right? If you convert from centimeters to meters, this is going to be 0.62 meters. And therefore the radius will just be 0.62 divided by 2. So that is just 0.31 meters. That's going to be the radius of this loop. Now, this mass, that's in grams. You do not want that. So you're going to divide this by 1,000 and you get 0.23 kilograms. SI units, super important. Now, let's read the first part. State what happens to the magnitude of the centripetal acceleration as of the car as it moves around the loop from x to y. X is the bottom position, y is the top position. What's happening to the acceleration? Look at it like this. So think about it like this. Acceleration has the formula v squared over r. Okay, here's what's happening. So you have this car going in a loop, and as it sort of goes in a loop, obviously what's going to happen is it's going to go at this point, it's going to go at this point, it's going to go at this point. What's happening? It's slowing down. Gravity is pulling it down. Gravity is trying to slow it down. Gravity is trying to pull the speed out of this car. So what happens is that the centripetal acceleration decreases. Why? Because think about it like this. R is constant. R isn't changing. R isn't varying. So what we can do is we know that the only two things that are changing are centripetal acceleration and v squared. They're on different sides of the equation. Let's take this r to the different side as well. It's going to be v squared equals r times ac. R times AC. Now R can be thought to be as a constant, then we can get rid of this equal sign. Now we get something like this. Okay, so V is decreasing. What do you think is happening to your acceleration? That's going to be decreasing as well. So as you go from x to y, what happens is your centripetal acceleration actually decreases. Decreases. And that's due to gravity, okay? That's due to gravity. Gravity sort of slows it down, slows it down, slows it down, and then it decreases this car. If this car sort of had an engine, if it had some built-in mechanism that kept its speed constant, then of course the centripetal acceleration would not change. Moving on to part number 2. Explain if the car remains in contact with the track, why the centripetal acceleration of the car at point Y must be greater than 9.8 meters per second squared. This would require you to actually draw out the free body diagram and think about this in terms of the free body diagram. Check it out. Here's the other. So this was the first equation for centripetal acceleration. This right over here would be the second equation for centripetal acceleration. Fc equals m times ac. This is the equation that you get from the second law. And to figure out this 9.8 meters per second square part, you also need to look at, and of course, going back to this first part, you could have also sort of figured this out using Fc equals MAC equation, but this would be slightly more trickier. This would not be as simple as, or you know what, I'm going to go into that as well. So first part, if you're trying to answer it using the second law equation, how would that look like? Second law equation. Second law equation itself is not sufficient to answer this problem. Second law equation goes hand in hand with the free body diagram equation. So let's make the free body diagram for this car as it moves from point X to Y. Now, of course, there will be many points. There will be 1 point over here, 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 and I've just drawn 3 points, this, this, and this. There are actually as many points as you want. You can draw them out as you go from position X to position Y. But if I'm just going to draw it for the free body diagram for position X and position Y. So looking at that, at position X, the car is at the bottom of the circular loop, right over here. So the forces acting on it are going to be mg, the normal force n. Now, what's going to be the centripetal force? So Fc is going to be the normal force minus mg. Normal force has to not only counteract this weight component, but it also has to sort of provide some net centripetal force into that center of this loop, such that the car can sort of go around this loop. Okay, so this would be Fc equals n minus mg, and in this case we know that the normal force has to be greater than the mg, or the weight of this car. What about at the top? Of course, this is what's happening at the position X. What about what's happening at position Y? So at position Y, the car is at the top part. Now, see, here's the problem with this. You don't know if the car is going to be in contact with the surface or not. The reason for that is because, see, gravity was pulling on the car. So as the car was going from X to Y, that's Y, this is X. As it was sort of going all of these directions, gravity was slowing it down. Gravity was trying to pull it downwards, reduce its speed. And so what happens is it may be possible that maybe the car didn't even get at the top, but at some point over here, it was so slow that it got at rest, lost contact with the wall, and then fell downwards. That's a possibility. We don't know if that happens or not. Okay, so that's why I wouldn't recommend you guys to actually go ahead and use the second law equation for this particular problem, and rather just use this equation because it's really simple to understand what's going on. Okay, so you probably see why the free body diagram sort of makes an issue, because at point X, it's really easy to understand what's going on. At point Y, maybe you're in contact with the, if you're in contact, so there's two things that can happen. If you're in contact, then this would be your following equation. So it would be Fc equals some normal force that's going to act on this car, as well as its weight mg. So that's going to be n plus mg
It could also be that the car is not in contact. Okay, let's say it sort of goes over this position. It has enough speed to go over y, but it's that speed is so low that it almost for a split second, for a tiny second, it loses contact with this part. Okay, and then it maybe it doesn't cover all of this further sort of path that's given over here and just falls down at the top position. If that's happening, then if you're not in contact, then what's happening is you would get this equation: Fc equals just the mg. Okay, you wouldn't have a normal force because you're not in contact. So that's why you can see that it's really hard to sort of understand. You know, you're going to combine this free body diagram as well as this to this Fc equals mac to figure out what's happening to that centripetal acceleration. It's so much work, so much guessing stuff. Rather just use this equation. So rather just use this one. That's the reason why I didn't go for the centripetal motion equation for part 1. For part 2, you don't have an option. You cannot just look at the first equation, AC equals V squared over R. The reason for that is because, well, how would you figure that out? How does this equation tell you why your centripetal force must be 9.8? But if you can sort of think about it, this 9.8 hints you to something. This 9.8 sort of hints you to the fact that you're supposed to talk about the weight. Why? Because 9.8 is actually g. It's the gravitational acceleration. And if you think about it, these contact forces, these free body diagrams, they do have g in here. So this is actually the part where you use F equals ma with the free body diagram. Okay, now thinking about this second part, says explain if the car remains in contact. That's the key thing. It says it remains in contact. So I think I did it the other way around. Okay, no, I did it correctly. So if you're in contact means we're using this equation right over here. Now, here's the idea. If I'm not in contact, so let me just combine the second line, the free body. So no contact at the top position y. And of course, this is all for y, because see, if you go back to the problem statement, it says for point y. So we're doing all of this for point y. So no contact and contact. Those are the two scenarios. Check this out. For no contact, you have the following equation: Fc equals mg, and then you can combine this with a second law equation, which is Fc equals mv squared over r. So you combine these two equations, mv squared over r equals mg. You can see the m's are the same on both sides. You can cancel those out, and your equation becomes v squared over r equals g. Here's what I want you guys to check out. This g, so what is this v squared over r? This is basically your centripetal acceleration AC that you are trying to find out. So in fact, you could have just wrote Fc equals mac over here, because you don't really care about the velocity or the radius. You're trying to find out what's happening to that centripetal acceleration. So rather, in fact, just don't write this over here at all. So don't write this over here at all. So you can see what's the centripetal acceleration. If you are in no contact, if you're not in contact, then it's just equal to g. Then AC is just equal to 9.8. Okay, but that's why they tell you explain if the car remains in contact why the centripetal acceleration of the car at point y must be greater than 9.8. Because see, 9.8 meters per second. This is the acceleration for no contact. Acceleration for no contact. So in order for the car to be in contact, or the toy to be in contact, AC must be greater than 9.8 meters per second. Now, how can you explain this? Well, you just show this no contact equation, that this no contact equation ends up giving you this thing, AC equals G, and you have to say, well, if you want to be in contact, then this acceleration must be greater. And then some of you may be dumb enough to ask the question of, well, why not be smaller than 9.81? So for that, I'm actually going to solve out this contact part, and hopefully that will make sense. So for the contact part, I have the equation Fc equals normal force plus mg, and I can then combine this with the second law equation, Fc equals mac. So that would just be mac equals n plus mg. And you can see now the masses don't cancel out. Why? Because, well, this term right over here doesn't have a mass, so you cannot just cancel masses out. What you can do instead is you can make AC the subject and send this mass over there to the other side, and you are going to get the equation AC equals n plus mg over m. And then you can sort of simplify this a little bit. So this will be AC over n over m plus mg over m, and these m's can cancel out, and then AC will be n over m plus g. So check this out. In order for the contact situation, what you need to have is you do need to have this 9.81, or your 9.8, but you also have to add another, whatever this quantity will be, n over m, this fraction, whatever value this fraction will have, you have to add that fraction into this 9.81 and get a higher value for the centripetal acceleration. So therefore, in order for the contact situation to be true, your AC must be greater than 9.81. The reason for that is because 9.8 is the acceleration required for no contact. In order for you to have contact, you need to have acceleration greater than that. So that's your reason. Moving on to part C, it says the initial speed at which the car in part B moves along the track. So what's part B? Okay, so part B is that is 3.8 meters per second. Determine whether the car is in contact with the track at point Y. Show you're working. So they basically tell us that this car is moving with a speed of 3.8 meters per second. We need to find out whether at point Y it's going to be in contact or not. Now there's a bunch of ways you can do this. This problem doesn't have one strict answer. I'm going to show you two ways using which you can solve this problem out. Oops, what happened to my screen? Okay, and we're going to go over that. So here's the first thing you can do. So the first thing you can do is you can take, I'm going to actually make some room over here or maybe to this side. So the first thing you can do is you can think about it like this. So you have your car, and your car is sort of moving in this loop, and it's going to go to that top position. So you can find out what is the frictional force at the top position required for the contact situation, okay? So basically what you're doing is you are trying to somehow figure out what is that FC at the top. What is that centripetal force at the top in the case of no contact, okay? Do that instead. Let's say you do a no contact. No contact. So for no contact, you sort of know that FC is going to be equal to mg, okay? And this comes from this no contact equation over here. This right over here, FC equals mg. And then you can combine it with that second law equation, which is FC equals MAC. And then when you merge these two equations, you get MAC equals mg, cancel out the m's, you get AC equals g. And here's what you're trying to do. See, they're talking about a speed. They're talking about the initial speed. You are trying to find out if this initial speed is enough or not. So what you can sort of do is you can bring speed into this equation, and the way you do that is you know that AC is equal to v squared over r. So you get this thing, and then you could make v the subject. So you're going to get v squared equals rg, and then you can send that square to the other side, it becomes the square root rg, and you get this equation, which is v is equal to under root rg. And here's what you want to do. You want to basically find out what the value of this v is. So you're going to find out, you can find that out by basically chugging in the values for r, and the values for r is the value for r is 0.31 meters, 0.31 meters, 0.31 times 9.81. So you can actually solve this in your calculator. I'm just going to do it over here. It's 0.31 times 9.81. That's going to be 1.74. 1 v equals 1.74 meters per second. This is the speed at which you lose contact. This is the no contact speed. It's the speed at which your normal force is basically equal to 0. Okay? So you need in order for you to not lose contact at the top position y, your velocity must be greater than 1.74 meters per second. Now, some of you may say, well, my velocity is 3.8 meters per second. That means I've solved the problem. Well, you haven't solved the problem because that 3.8 is the initial velocity. So when the car starts off over here, its initial velocity is 3.8. As it sort of moves up to that point y, its velocity is decreasing because of gravity. So it may not have 3.8 meters per second, or it will not have 3.8 meters per second at the top position y. So you will have to find out what your velocity will be at that top position, and you will have to see if it's greater than 1.74 or if it's not greater than 1.74. If it is, then you can make the claim that, hey, look, in order for no contact, this must be my velocity, and since I have a velocity that is greater than 1.74, that means the car will be in contact. However, there's an easier way to do this. That easier way is basically they tell you this thing in the second part, that in order for the car to remain in contact with the track at position y, the acceleration must be greater than 9.8 meters per second. And you can actually use that idea. What are you going to do? You're basically going to use this equation. So car is right over here. It's going over here. It's going to go all the way up there at point y. What you are going to do is you're first going to find out what the speed is going to be at point y. So you're going to find out whatever v is. And then what you're going to do is you're going to use this equation, AC equals v squared over r. You are going to put in that value of v, you are going to put in the value of r, and you are going to find out whether your AC is greater than 9.81 or not. So they already tell you in the problem statement that, hey, look, if your acceleration is greater than 9.81, then the car remains in contact with the track. That's what they tell you in point 2. Okay, so you don't have to do anything. You just have to find out if you get an acceleration greater than 9.81 or not. And so what you can do for that is you need, well, 1, you need that velocity, and 2, you need that radius. Now you could also use maybe this equation, FC equals MAC, and you can try to find out maybe some way you can get the value of centripetal acceleration out of this equation, but that will not be possible, again, for this reason that we talked about over here. Your centripetal force will constantly be changing. You don't even know if you reach that top position or if you fall down over here. So how are you even going to make a free body diagram? You're going to have two situations, one when you're in contact, one when you're not in contact. It's just way more confusing to use the free body method and the second law method, and it's way simpler to just use this simple equation for centripetal acceleration. Now, how do we find out this v? That's the problem. We do have the radius over here. How do we find out this v? That's the problem. But that v, you can basically find out using an energy method. So this is not just a circular motion problem. This is where past paper problems get real. They don't just test centripetal motion knowledge, but they test knowledge from other topics as well. Over here, they're testing your energy method. So as you go from this bottom position, where you have your speed as 3.8, to that top position where you don't know what your speed is, you're basically going to use change in KE is equal to change in GPE. So you're covering up some height. You're basically gaining some height h, and after you gain that height h, you've lost some KE, and basically you can use this equation to find out what your velocity is going to be at that top position. So here's how you do it. So you're going to find your GPE. So GPE is going to be mgh. And how do I know that how do I know that height? Well, because that height is the diameter of this loop. The diameter of this loop is from that top position all the way to this bottom position, right? The height between x and y. That is 0.62 meters. I know what g is, so mass of this car is, let's see, how much is the mass? It's 0.23 kilograms. So the mass is 0.23 times 9.81 times the height is 0.62. So we do that, and we are going to get 0.23 times 9.81 times 0.62. So this is going to be equal to, I'm not going to round this off, it's going to be 1.398906. I'm not going to round it off right now because I don't want to lose my accuracy. This is what my gravitational potential energy is. Now I can basically say that my KE, so my KE, my change in KE is equal to my change in GPE. And I'm basically, what kind of, so I gained GPE, that's why this right over here is a positive, but I'm going to lose KE. So this change in GPE is going to be the same for the change in the kinetic energy, because the changes are the same, but the gain in one is the loss in the other one. So what I can do, therefore, is I can write 1.398906, and since this is loss in KE, I can put a negative sign next to this. So the negative sign denotes that this is a loss. Now, how does this help me find my final speed at position y? That's still not obvious. It's going to be obvious in just a second. So loss in KE is basically going to be however much final KE you had minus your initial KE. And therefore, this is going to be equal to negative 1.398906 joules. And the way I can basically do this is I can write 1 by 2 mv squared, and this v squared is, I'm going to write a tiny subscript f next to it, just to denote that this is final velocity, minus 1 by 2 mv squared, and I'm going to write a subscript I to denote this is initial velocity, is equal to negative 1.398906 joules. And therefore, what I can do is I can take this 1 by 2 and mass out as common, because it's the same car, so they both have the same mass, and 1 by 2, they both have 1 by 2, so I can take that out as common. This is 1 by 2m times v squared final minus v squared initial, equals negative 1.398906 joules. And therefore, what we can sort of do is we can send this 1 by 2m to the other side. So it's going to be vf squared minus v squared I equals, this is going to be, so I can write it like this, m over 2. This is going to go over there, and it's going to flip, so 1.398906 times 2 over m. Okay, and then what do I have? So I'm trying to find out what my final velocity is, so I can make that subject. So this is going to be negative 1.398906 times 2 over m. This negative vi squared is going to become positive vi squared, and then this square, I can send this to the other side, it's going to become a square root. So now we can chug in the values of m, which is 0.23, and we can chug in the values for vi, which is the initial velocity, which is 3.8. Now you solve all of this in your calculator, and it's going to be negative 1.398906 398,906 times 2 over 0.23, and then you have to add 3.8 squared. That's going to give you 1.51 meters per second. So that's your velocity up top. Now you can find out what your centripetal acceleration is going to be. So you can just square 1.51 squared over the radius. The radius is 0.31 meters. So you do this, and it's going to be, so answer squared divided by the radius, which is 0.31. This is 7.34. Acceleration is equal to 7.34 meters per second squared. Now, this guy right here is less than 9.8 meters per second square. Therefore, the car will not be in contact. Car will not be in contact at y. And you could have also figured this out. So you just figured out that the velocity at position y is 1.51 meters per second. If you go back, I told you guys we can do this another way, and that was we find the minimum speed at which you will lose contact, and you would need a speed greater than this to stay in contact. That's, oh sorry, not this one. It was this one. It was 1.74 meters per second. Instead, the speed we got was 1.51 meters per second. So that is not happening. The car is not going to stay in contact. It does not have the required minimum speed to stay in contact, and therefore this will fail to keep the car in contact. It's too slow. It's going to fall down. Now, that's part C. Let's try and answer part D. Part D says suggest with a reason but without calculation whether your conclusion in C, our conclusion in C is that the car is not in contact. That's our conclusion. In part D, we have to sort of tell them that would this conclusion be different for a car of mass 460 grams, which is basically going to be 0.46 kilograms, moving with the same initial speed, so it has a speed of 3.8 meters per second. We have to figure out if it will also not be in contact. Will it be in contact, or what's going to happen? So all that has changed in this equation is that the mass, the car has gotten heavier. All of the other stuff remains the same. The radius of the loop remains the same. The speed remains the same, yada, yada. So here's how you can think about this. If you go back to part 2, they basically tell you that the key thing that is required for the car to stay in contact is for it to have an acceleration greater than 9.8. Okay, and you can also sort of think about it like this. You can think about it in terms of velocity, where it needs to have a velocity greater than 1.74. Now, what is the acceleration? What is even this acceleration? What is this centripetal acceleration? Centripetal acceleration is basically v squared over r, correct? And what's the formula for this velocity that we found out? So we derived a formula for this velocity, which is v equals under root rg. So it's v equals under root rg. So this is the velocity at top, or velocity at top, or velocity at y. This is the formula for the velocity at top. Now, here's the thing. In both of these equations, do you see a mass quantity? They don't have a mass quantity. That means your speed at the top position, whether it's going to be greater than 1.74 or not, depends on if the radius of the loop changes or if the gravity of the planet changes. In the same way, whether your centripetal acceleration is greater than 9.8 depends on whether the radius of the loop changes or the velocity of the car changes. If you look at both of these examples, they do not include mass, okay? And since they do not include mass, it means that the rest of the things remain the same. And so, the car wouldn't experience any difference. It wouldn't experience any change in this conclusion. So the fact that the car remains in contact or not in contact depends not on mass, but the radius, the velocity, and over here on the gravity of the planet. It doesn't depend on the mass. So my conclusion was that the car will not stay in contact. So the conclusion stays the same because you can say the centripetal acceleration does not depend on mass, but instead speed and radius. And since those are the same for the heavier car, it will experience the same fate. Let's go down. The same fate as the lighter car. And that is it for question 2. So we're on our third question, and the first thing we have to do is we have to define what a radian is. And the definition you can write over here is basically a radian is the angle subtended at the center of a circle by an arc
that is equal to the radius of that circle. So if you didn't catch that, you can go back 10 seconds, slow the video down, and write it as the definition of the radian. In part 2, it says we have a small mass that is attached to a string. The mass is rotating about a fixed point P. So this right here would be a center point P, and then we have this mass attached to a string that rotates around this fixed point P. What we have to do is we have to explain what is meant by the angular speed about point P of the mass. So what is angular speed? Angular speed is the amount of angles you cover per unit time. So let's say if this circle, this mass sort of goes to this new position and covers an angle, let's say 30 degrees. Well, it's not in degrees, it's in radians, but for the sake of explanation, I'm just going to write 30 degrees, and it does so in 10 seconds, then its speed would just be the amount of angles it covers divided by the time. Of course, the angle, again, would not be 30 degrees, but rather in radians. So what is meant by angular speed? Angular speed is angles covered per unit time, by the mass, about point P, about point P. Okay, let's move on to the next part. Part B says a horizontal flat plate is free to rotate about a vertical axis through its center, as shown in figure 1.2. So basically, what this means is you have a center, sort of an axis going through this plate like this, and the plate is then rotating in this fashion about that central vertical axis. So what we have to do is it says a small mass m is placed on the plate, a distance d from the axis of rotation. So since the axis of rotation is passing from the center of the plate, what d is basically the distance the mass is away from the center, or you can sort of understand it as the radius of rotation for mass m. So the next line says the speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. So basically, they keep on increasing the speed of this plate. At first, it's at rest. They slowly increase it and increase it more, up to the point where the force of this plate and this mass is not sufficient to hold the mass onto the plate anymore, and it sort of flies off or slides off the plate. And of course, that force is going to be friction. There's going to be some frictional force between this mass m, which is sitting on this plate. The maximum frictional force F, so they're denoting the maximum frictional force with the letter capital F. The maximum frictional force, capital F, between the plate and the mass is given by the expression F is equal to 0.72. So they tell us that, hey, look, there's a frictional force between this mass and the plate, and the frictional force has an equation 0.72 times W. We don't know what W is, but if you read the next line, they say where W is the weight of the mass m. So W is the weight of the mass, and the weight of the mass times 0.72 will basically give you your value for the maximum frictional force that is possible between the mass m and the plate. The next line says the distance d is 35 centimeters. Now, we don't like our quantities in centimeters, so we're just going to convert that into meters, and that's going to be 0.35 meters. Also, instead of d, I'm going to write r for radius, and radius is basically the distance the mass m is away from that center point. So what we have to do is we have to determine the maximum number of revolutions of the plate per minute for the mass m to remain on the plate. And then we have to explain our working, which basically means we need to show the steps for it. It says over here the maximum number of revolutions per minute. What does that mean? That means we have to find the RPM. RPM, you can sort of understand it as the speed of something. It's how fast does this thing rotate, or how many rotations it's doing in each minute. And of course, the faster it rotates, the more revolutions it's going to do every minute. So it's sort of RPM is sort of something like a speed. You can sort of understand it like that. And we have to find the maximum number of RPM. Now, why do they say the maximum number of RPM? So if you read the full question, it says for the mass m to remain on the plate. So the reason they say maximum is because the number of revolutions that are possible for mass m so that it remains on the plate are determined by this maximum frictional force. Okay, so there's only a certain amount of frictional force that this plate can provide to this mass. If you go faster than a particular speed, the maximum frictional force will not be sufficient to hold the mass onto the plate. And so the mass is sort of going to fly off. Therefore, the reason they say the maximum number of revolutions of the plate for the mass m to remain on the plate, the entire reason they say maximum number of revolutions for it to remain on the plate is because we need to take this thing into account. We need to take this thing into consideration. This is what enables that mass to stay on the plate. This maximum friction is what enables that mass to stay on the plate. Now, this maximum friction will have some corresponding RPM. Okay, so
if you go faster than that particular RPM, this frictional force will not be enough to keep the mass onto the plate. Meaning if you go faster than a certain amount, faster than a certain speed, faster than a certain RPM, that piece of mass will fly off because the frictional force will not be enough to hold it in place. So what we have to do is we have to find out that number of RPM, and we are given the frictional force, we are given this radius r, and we are given, what else are we given? So we're not given anything else. So we're supposed to somehow use this idea and find out that RPM. How do we do that? Well, first of all, I tell you guys this all the time, use the second law. If it's a circular motion problem, you don't know what to do, you use the circular, for the circular motion, you use the second law equation, you use the free body diagram, and you use those things to figure out how you're going to find what you're trying to find. So we don't know what to do in this case, but we do know that if we do the second law, if we do the free body diagram, we're sort of going to figure out how to solve this. So here's what's going to happen. I'm going to put in the second law equation over here. So the second law equation would be Fc equals mv squared over r. And then for the free body diagram, we are going to have the equation. So this right here is the center point. That right there is the mass m. I'm not going to draw its free body in the vertical direction, just the central direction. And in that direction, we only have this particular force, which is the frictional force denoted by capital F. Okay, and it's they tell us that this capital F is equal to 0.72 times W. Now, this is the only force that acts in the central direction. There's no other force that's acting in the central direction, so we only get this one equation, which is this frictional force is equal to 0.72 times W. Now, from this free body diagram, we can see that since this is the only force that is acting on this piece of mass, we can sort of say that, hey, look, the centripetal force is going to be coming from this frictional force. And since this frictional force is equal to 0.72 W, that means Fc is equal to 0.72 W. Now, this is just me doing my working on this free body diagram. And I come up with this conclusion that, hey, look, my centripetal force is going to be equal to 0.72 W. Now, I can sort of use this right over here, and I can put that sort of value for centripetal force into this equation, which will be 0.72 W. And I can write is equal to mv squared over r. Now, here's what you can do. There are different versions of the second law, so let me just write some of them over here. So one of the versions is m omega squared r. Another version is mv squared over r. Then we did these other versions that included time period and frequency. So those were for time period. We have it over here, I believe. So it was 4 pi squared mr over t squared. So it was 4 pi squared mr over t squared. And then we had this other equation, which was Fc equals 4 pi squared mr frequency squared. Okay. Here's the thing. If you know which version of the equation you need to use, it makes stuff a whole lot easier. But before we even get into this, let me just tell you how we're going to even find the RPM using what we're doing over here. Because right now we just made the free body diagram and we just did the second law. We have no idea how we're going to find the RPM, right? RPM is basically the speed. So technically, here's the idea. If you can find this speed v, now what is the speed v going to be in? The speed v is going to be in meters per second. If you find out the value for the speed, you can then convert it into revolutions per minute. Okay, that's a conversion. We've done that before. When we were sort of building up our knowledge of circular motion, there was a sort of a problem in which we did how to go from meters per second to revolutions per minute. So if you find the speed, it doesn't matter if you use this version of the second law. You can also use this version of the second law. So 0.72 W instead of mv squared over r. Imagine you use m omega squared over r. So over here, the speed you're trying to find is this angular speed, and this angular speed is rads per second. There is a way that you can sort of do this conversion and go to revolutions per minute. But here's the most easiest one. Here's where it's going to be the most easiest one for you to sort of do it. So imagine I use this equation instead. So I use 0.72 W instead of the Fc, and then I use this equation, the frequency equation. So that's going to be equal to 4 pi squared mr frequency squared. This equation is really, really helpful. Why? Because guess what? This right over here, this frequency, if I find this frequency out, what even is frequency? Going back to what we did in this page, we basically wrote the definition of frequency. And that was frequency is the amount of complete rotations happening in per unit time. So every second, the revolutions that take place. So this is basically going to be revs per second. Converting this into revs per minute is going to be the easiest conversion. So you can use these three equations. Any of them would work. But try and think about it like this. Which equation will allow me to find my RPM the easiest? Okay, and that will be the final equation, because one, you already have revolutions. You just have to convert the time from seconds to minutes. Okay, so once we figured this out, let's sort of take a step back and figure out what we just did. So we had an equation, and we were given some value. We were given this particular information, that the frictional force is 0.72 times W, and then we combined it with the second law. We know that once we sort of do this, we always figure out what we're supposed to do, and we sort of ended up over here, and we realized, oh hey, we just have to find the speed. We just have to find the speed. Once we find the speed, we can convert it to RPM. That's no difficult task. It's just a conversion from one speed to another kind of speed, from meters per second to revolutions per minute. And then we thought about it, and we were like, well, we could have applied the other formula as well. If then we would have had this angular speed, and we would have been converting from radians per second to revolutions per minute. And then we thought about it, where would it be the easiest? And that would be in this equation, the frequency equation. And the reason for that is because the conversion has already been done for you. You're already going to be dealing with revolutions. You will just have to go from seconds to minutes. And therefore, we decided to use the frequency equation because that was going to be the easiest. Now we sort of have an idea of what we're going to do. And some of you may be asking the question as to, well, I don't think I can solve this out because look, I have a variable W over here. I don't know what the mass, I don't know what the weight of this mass is, this piece of mass is, and I don't know what the mass of this piece of mass is. I don't know what the mass of this tiny particle is. I don't know what the weight of this tiny particle is. So how am I going to even solve this? If I use the other equations, I don't know the mass over here. I don't know the weight over here. I don't know the mass over here. I don't know the weight over here. How do I even solve these equations? Any of these equations? I can't do that. I know now how to find my RPM, but I have no idea what to do about these quantities that I don't have a value for. So how do I do this? And well, the reason they don't give you a value is because if you think about it, W is basically mg. W is basically mg. And so what you can do with this is, here's what you can do with this. The equation is 0.72. The equation that we're going to use is 0.72 times W equals 4 pi squared mrf squared. This is the equation that we're going to be using. If instead of W, I sort of write mg, then what I have is all of this. And what I can do is I can take these m's and I can divide them. So basically what I can do is I can take m from one side of the equation, take it to the other side of the equation, divide it, and they're basically going to cancel out. So this m cancel out with that m, and so the m's disappear. That's why you don't need m, and that's why you don't need w, because they are going to cancel out. Okay, so now we have this equation over here. We have 0.72g equals 4 pi squared r times f squared. We are trying to find that frequency f. So let's start to solve this. Let's rearrange this equation for f. So we're going to get 0.72g over 4 pi squared r equals f, and then we take the square to the other side, so it's going to become a square root, and we have this thing. Now we just have to chug in the values. So g is 9.81, 4 pi r, so that's going to be 4 pi squared. So pi squared is going to be 3.142 squared. You can do that on your calculator. And then r is going to be 0.35, and this is equal to our frequency f. So let me just check if r was 0.35. Yes, it was 0.35. Now let's chuck all of this in our calculator. So we're going to have 0.72 times 9.81, and then we're going to divide it by 4 pi squared times 0.35. And when we solve this out, we're going to get 0.715. So 0.715. So frequency is going to be 0.715. Now remember, this was revolutions per second. This is also written as 0.715 hertz. In this case, the hertz basically means revolutions per second. Okay, so now we know that the particle is doing 0.715 revolution in 1 second. In 1 second. We are trying to find out how much it's going to do in 1 minute. Okay, so if we know that in 1 second it's doing this much, then 1 minute basically means how much is it revving in 60 seconds. That's what 1 minute is, right? 1 minute is basically 60 seconds. So what you can do is you can basically do 0.715 times 60, and this would basically be, so 0.715 times 60, that's going to be 42.9. We can round it off to 43 revs every minute. That right there is going to be your answer. Okay, now we still have one part left. So part C says the plate in B, so B is this part right over here, is covered when stationary with mud. So when it's at rest, they cover the plate with mud. They then say, suggest and explain whether mud near the edge of the plate or near the center will leave the plate first as the angular speed of the plate is slowly increased. So again, remember, the frictional force will stay the same. The frictional force for the piece of mass and for the plate stays the same. So then we can sort of, and they give us the angular speed for a reason. So you can sort of think about it like this. Let me just draw a plate over here. So this right here is a plate. Let me erase this line. This right here is the center mark. And imagine you have two pieces of mud. So you have one piece of mud over here, and you have one piece of mud over here. And I know they're talking about sort of covering the entire plate with mud, but we don't need to sort of do that. We can sort of take two points, two tiny pieces of mud, and sort of understand what's going to happen just using these two pieces. One of those pieces of mud needs to be at the edge of the plate. The other needs to be at the center of the plate. So the green one is close to the center, and the blue one is close to the edge. Now, they tell us that the angular speed of the plate is slowly increased. Now they increase the speed, and let's say it reaches some certain value. Okay, let's say it reaches some value, 50 rads per second or 25 rads per second. Okay, they sort of increase it to the value they want to increase it to. Now here's the thing. Omega, the angular speed, will stay constant, okay, for all of the particles. You're like, it's not constant. They're telling us that it is slowly being increased. We're assuming that we've reached a point at which it has been increased to whatever amount they want to increase it to. So it's at its final amount. Now, omega at that final position will be constant. And what you can sort of do is you can sort of think about it like this. Since all particles, let's say these particles are in a straight line. Now imagine after a second later, this particle is over here. The blue particle is over there. They will have covered the same angular distance theta in whatever time we're talking about. But they will have different speeds, not angular speeds, but different linear speeds. The reason is because, well, blue is in a bigger radius than the green one. And so, therefore, the speed of blue will be greater than the speed of green. So we don't want to think about speeds right now. Whenever we have sort of a comparison, whenever we're trying to figure stuff out, we try and find out an equation where two things are varying and all of the other stuff is constant. That equation, the reason they mention angular speed over here is because you can use this equation, Fc equals m omega squared over omega squared times r. And in this equation, let's assume that the pieces of mass that we selected, so the green one and the blue one, let's say that they both have the same mass. So let's assume they both have same mass. They're both of the same size. Now they're both of the same size. They both will have the same angular speed. So same angular speed, given that we put them in the same line. So given that we basically, this was the point, and we put them sort of like this, they're both going to cover the same angular distance in a certain amount of time. It's just that their linear speed will be different. So now we have this equation where we have the Fc and we have the R that is varying. Now you may be like, well, Fc is constant. They already tell us that the maximum frictional force that you can have is constant. Yes, you're correct, it's constant. But right now it's just going to make sense in a second. So these two quantities are not changing. We can sort of assume them to be constant. This equal sign is, we can then remove it, and we can say Fc is directly proportional to R. That means that if your radius is higher, meaning if you are more further away from the center, you need a higher centripetal force. If your radius is smaller, you need a smaller centripetal force to keep you in that circular motion. So the further you are from the center, the greater Fc you need. The closer you are to the center, I forgot to put an R over here, the closer you are to the center, the less Fc you need. Now, what does this mean? What does this mean for us? So that means that, see, the blue particle is further away from the center. It's going to require more centripetal force. Let's imagine that all mud pieces have the same maximum centripetal force that they can experience. That means that since particle blue or mass blue is away from the center, it needs a higher frictional force to keep it in that circular motion. But it cannot get that frictional force because frictional force is limited. It's constant. And so due to that reason, the blue particle is more likely to fall off the edge first because it would require more centripetal force to keep it in that circular motion, but you cannot have more of it, and therefore it's more likely to fall off. Now, lucky for the green particle, it doesn't require as much frictional force. It's closer to the center, so it requires a relatively less centripetal force. And so the frictional force that exists may already be sufficient enough to keep it in the circular motion. Now, this was a bit tricky. You may be thinking, well, why didn't we use F equals mv squared over r equation? The problem with this is, see, you can assume this mass to be m to be constant, you can assume f to be constant, but then the problem would be that you cannot compare this radius quantity with this fc quantity because this v over here is varying. Okay, v depends on how far you are away from the center, and so each sort of mud piece is going to have a different v depending on where it's situated. Over here, this w, we can assume that to be constant because the angular velocity for all points on this plate will be the same, and we've gone over this in when we were building up knowledge for our circular motion. Another way you can sort of think about this without involving any equations, which you may find easier, is you can just think about this. If you're further away, you require more friction to keep you in motion, in that circular motion. The closer you are, you require less frictional force or centripetal force to keep you in motion. Therefore, since mud on the edge is further away from the center, it's going to require a much higher frictional force, and therefore it's much likely to slip off the edge of the plate. And therefore that's a really sort of simple understanding to this, and you can just sort of take that understanding, and this was a 2-mark problem, so you can just write that, or you can use equations, try and understand what's going on. Completely up to you, completely up to you whether you want to do it intuitively or you want to do it analytically using some equation. So that is it for question 3. Okay, so we're on to problem number 4. In this problem, we have a stone of weight 3 newtons that is fixed using glue to one end P of a rigid rod CP, as shown in figure 1.1. What does rigid rod CP mean? Rigid rod means this rod has a fixed length and its length will not be changing, meaning the radius of this circular motion will not be changing. They tell us that the rod is rotated about end C so that the stone moves in a vertical circle of radius 85 centimeters. Let's convert that into meters. We never want to go start our work with centimeters. So that's going to be 0.85 meters. You just divide the centimeters by 100 and you get the value in meters. The angular speed omega of the rod and the stone is gradually increased from 0 until the glue snaps. The glue fixing the stone snaps when the tension in it is 18 newtons. For the position of the stone at which the glue snaps, number 1, on the dotted circle of figure 1.1, mark with the letter S the position of the stone. So here's what we have to do. For the position of the stone at which the glue snaps, we have to mark a letter S at which the glue snaps. So we have this entire circle in figure 1.1. We have to sort of put an S at the position where the glue is going to snap and the mass is going to fall off. Now, where is that most likely to happen? That is most likely to happen at the position where tension in that glue is going to be the maximum. And in all of this circular motion, that happens at the bottom position. Let me just explain it to you guys why that is. So let me just draw a rough diagram for the bottom position. So this is the rod CP. This is the rod CP. What's happening is this rod has some glue. Okay, so some glue over here, something like this, and that glue is basically connected to the particle or to the object or to the mass. Now what happens is this glue obviously has some tension. It's pulling onto the ball. As you sort of move this ball in the circular motion, this ball sort of there's obviously some force trying to keep this this ball in the circular motion, and that force basically comes from tension that is produced within this glue, and that is told to us in the question. So they tell us that the glue fixing the stone snaps when the tension in it is 18 newtons. So they tell us that the glue has some tension which holds this ball in the circular motion. So basically that in this glue there's some tension that's being created. However, when that tension reaches 18 newtons, this glue is not strong enough to hold this ball, and so the glue snaps and the ball falls down. Now, why is that most likely to happen at the bottom position? Well, because at the bottom position, if you sort of make an equation for the circular motion, you basically, so there's obviously going, if I draw a free body over here for this ball, there is tension acting upwards, and this tension comes from the glue, so this is tension, and there's weight acting downwards, so there's weight mg acting in the downwards direction. That is what's happening in this downward position. If you make an equation over here, you basically get Fc equals tension T minus mg. So why is the glue most likely to snap at the bottom position? Because at the bottom position, tension is the highest. Tension not only has to, so this tension not only has to counteract this mg force, but it also has to have some extra component which is going to be providing this Fc. Because let's say tension is 19, mg is 9, so 19 minus 9 is going to give you Fc as 10 newtons. So see, this tension had enough enough magnitude to counteract all of this mg, and then to provide a net force of 10 newtons that in the central direction, so that the ball stays in that circular motion. So tension is the highest in the bottom position. You can go ahead and try and make sort of free body diagrams for other positions. So you can make it for the top position, for this position, for this position. I mean, the horizontal positions are going to be the same. You can make it for the bottom position, and what you'll sort of find out is at the bottom position, it's the strongest. If you ever if you've ever tied a ball to a string and tried to move it, try to spin it around, you may have sort of felt that when you sort of spin it around and you're passing through the bottom position, that's when the ball pulls on the rope the most. That's when the rope produces the most tension. Not only does it has to counteract the weight, but it has to have some extra force to provide that net component, or that centripetal component, that's going to keep the ball in the circular motion. So this was a little intuition behind what's going on. And so you are at the bottom position, that's where you're going to label an S. So that's the position where the ball is going to sort of break. The glue is sort of going to snap at the bottom position. Then part 2 says calculate the speed omega of the stone. And speed omega was the angular speed, which they tell us in the problem statement. So we're trying to find the omega for the stone. Now, what's the information that has been given to us? And again, they say for the position at which the glue snaps. So this bottom position, this position S, this is where we have to find the omega, the angular speed of the stone. Now, the way we do that is, again, whenever we have a circular motion problem, we don't know what to do. We basically use the second law equation, and we use the free body diagram. Now, we already have the free body diagram. The free body diagram is T minus mg. So FC is equal to T minus mg. And over here, from the second law, which one are we going to use? Which equation are we going to use? There's a bunch of second law equations. We're going to use the one that has omega in it. So that's going to be FC equals m omega squared r. Now, what we can do is we sort of, they already tell us the tension. They tell us that the tension is 18 newtons. So we can put in FC over here. FC is equal to 18 minus mg. Do we have the mass of this particle? No, we do not have the mass of this particle, but we have the weight of this particle, that is 3 newtons. Now, check this out. We can find out the mass, so we can do W equals mg. W is 3 divided by g. G is going to be 9.81. That's going to be equal to m. So let me just calculate that. 3 divided by 9.81, and that sort of tends to give me a huge decimal answer, and I don't want to round it off to significant figures, because then I'm going to lose some accuracy. So instead, I'm just going to write my mass as this fraction. So this many kilograms is basically what my mass is, and I'm just going to use this fraction in these equations. So this right here is my mass. 3 newtons is what my weight is. Now I can sort of start to do my work. Also, look at this mg. This mg, what is this mg? This mg is basically the weight, because W is equal to mg. So what I can do is I can do some simplification over here. Instead of writing mg, I can write 3, and so the centripetal force is going to be equal to 15 newtons. Now I have this over here. I have this equation over here. I merge these two equations. That's what we always do. So this is going to be 15 equals m omega squared r. Do we know r? Yes, we do know r. So it's going to be, but first let's rearrange this equation for omega. So this is going to be m and r will divide on the other side. When we take this square to the other side, it's going to become a square root. And now we can basically put in our values. 15 for m, I'm going to be using that fraction 3 over 9.81. And for r, I will be using the radius, which I believe was 0.85 meters. So 0.85 meters. And now I can solve this out. So I take my calculator and I do under root 15 divided by 3 over 9.81 times 0.85. So when I do this, I get an answer 7.596, and I can sort of round that off to 7.6 radians per second. So this right here is going to be my answer. Okay, so I believe this is the 4th question that we're on. Part A says, explain what is meant by a radian. And we've already done this before. A radian is the angle subtended at the center of a circle by an arc that is equal in magnitude to the radius of that circle. Part 2 says why one complete revolution is equivalent to an angular displacement of 2 pi radians. And for this, what you have to do is you have to basically show where the 2 pi radian comes from. And we've done this in the derivation of where the 2 pi radian comes from. So what you can sort of say is you can say, hey, look, we can use the formula for radians, and then there's only one formula that we studied for radians, and that formula was S equals R theta. And the way we sort of do this is we sort of say, hey, look, for one revolution, the arc length is basically the circumference of the circle, and the circumference of the circle is 2 pi r. And of course, my bad, you guys, I put a over here for you guys. So arc length. So I can say the arc length for one revolution is basically the circumference of the circle, and the circumference of the circle is 2 pi r. Therefore, what I can do is I can say if a is this thing and a is equal to r theta, then I can get 2 pi r
equals r theta, and then what I can do is I can basically cancel out the r terms from both sides, or you can think about it like this. You can divide this r on that side or that r on this side, and you basically get the value for theta, or the value for angular displacement, as 2 pi. Now this is for 1 revolution, because over here we sort of set this condition for 1 revolution. If you show this, then you can essentially say that the angular displacement of 1 revolution is equal to 2 pi radians, and this has the units of radians. Okay, so you can just put a radian over here. Part B says an elastic cord has an unextended length of 13 centimeters. Let's first change that to meters. So that's going to be 0.13 meters. One end of the cord is attached to a fixed point C. A small mass of weight 5 newtons is hung from the free end of the cord. The cord extends to a length of 14.8 centimeter as shown. Let's change this to meters, and I believe this would be 0.148 meters. So what they say is they basically say this is point C, this is where they sort of attach the string, and then to the other end they attach a mass. The mass, of course, has some weight, and so it pulls on the string, extending it to this new length of 0.148 meters. Now, what we can sort of do is we can find the extension of this cord, and we can sort of find the spring constant, or not spring constant, but rather the rope constant, or the cord constant for this cord, or this rope, assuming it obeys Hooke's law or proportionality law. That's essentially why they give you this. You see you have an unextended length, and you have a weight being attached to a cord, and then that cord sort of creates a new length. Whenever sort of this is happening, they're sort of hinting you, hey, use your information of Hooke's law, use your knowledge of Hooke's law, use your knowledge of the spring chapter. Now this isn't a spring, but Hooke's law could still apply to this. It may not be obvious right now, but as we go into the next steps, you will really sort of realize that the entire point of giving you this information is to find that extension and to find that spring constant, or this cord constant. Now again, see, this is a circular motion problem, but you're seeing cord in this cord in this circular motion problem, and the entire reason for that is because as you actually start doing past paper problems, they're not much about circular motion itself, but they're about your ability to combine knowledge from different topics and use them to solve a problem. So let's read the next part. It says the cord and mass are now made to rotate at a constant angular speed omega. This is important. Constant angular speed. So that means the angular speed will not change in a vertical plane about point C. So they basically have that mass, that small mass, and they're making it rotate about point C right now. When the cord is vertical and above C, its length is unextended. So the cord has no extension in it when it's above C. So it has an unextended length of 13 centimeters, which again is 0.13 meters. So it's unextended, 0.13 meters, as shown in figure 1.2. So what happens is they're making it rotate, and as the spring sort of goes at its top position, right above C, they're saying that the spring does not have an extension inside of it. Now, what does this mean? This means something really important. This means that the cord does not have any force inside of it. Now, and the cord is also not slagging. Slagging means it's not sort of doing something like this, and it's not compressing. That's basically what it means. So the cord is at its unextended length. Now, what that means is there's no force in this cord, in this rope. How do I know that? Well, because see, ropes have force. The way a rope works is you have a rope, and the way it works is if you pull, that means it has tension in it. Okay, but if it's unextended, or it's at its original length, that means there's no pull in the rope, and that means there is no tension in the rope. That's basically what it means. So all of this is basically telling you that as that cord is right above point C, there is no tension in that rope. Now, the next part says, show that the angular speed omega of the cord and the mass is 8.7 rads per second. So what we have to show is we have to find out the angular speed, and we have to show that it's equal to 8.7 rads per second. Right. So what can we do? How can we find that? So we know, first of all, we know it's a circular motion, right? The mass is moving in a circle. Therefore, what we can sort of do is we can apply the second law equation, and we can apply the free body, and we can combine those two to find out the angular speed. So what version of the second law are we going to use? We're going to use one that contains omega, because we're supposed to find omega. So it's going to be m omega squared r. Now, what about the free body diagram? So we have, do we make the free body diagram for this figure? Do we make the free body diagram for this figure? Do we make the free body diagram for this figure? If you think about it, in this figure 1.1, there is in fact no extension, no movement. The string is not rotated at this position. They had an unextended string, and they just attach a mass to it, and it's stationary right now. When they start mentioning things about rotation in the second part, So in this part, or in this text right over here. So what they're saying is they're saying that they make the mass and the string rotate around that point C, and they give you information for this diagram, figure 1.2, but they don't give you information for figure 1.3. They don't even talk about figure 1.3. At this point, you can see there has been no mention of figure 1.3. That's a good sign that you're not going to be using figure 1.3 to do anything as of now. Why are you not going to be using figure 1.1 again? Because it's not rotating. Figure 1.1 has no rotation in it. It's just at a stationary position. Figure 1.2, 1.3 are rotating, but there's no mention of figure 1.3. There's no information of 1.3 at this point, so we're not going to use it. We're going to use figure 1.2. Okay, now free body diagram for figure 1.2. Let's sort of make a free body diagram for it. So we have figure 1.2 over here. This is points, the center point C. I'm going to put a cross mark over here. This is C. This is the rope. Rope has the mass attached to it. Now, what are the forces acting on this? We have to make the free body, right? So is there a tension? No, there is no tension. We just figured that out. Unextended length means there is no pull. No pull means there is no tension. So there is no tension force. So the only force that is going to be acting on this mass right over here is the gravitational force that is due to its weight. And its weight was 5 newtons given to us in the problem statement right over here. Weight of 5 newtons. So that right there is its weight, W, or mg, whatever you want to call it. Okay, so that's the weight. That's in the free body diagram. That's the only force we have. Therefore, we know that Fc is equal to W. Right. Now, what we can do is we can basically combine this equation, the free body equation, with the second law equation, what we always do. And so we're going to get W is equal to m omega squared r. Now, you have the value for W, you have the value for r. So over here, the string is at its unextended length of 13 centimeters or 0.13 meters. We're going to use the SI units. So you know what r is. You are trying to find omega. You don't know what mass is. You can find mass because you know that weight is equal to 5, and so you can use the equation W is equal to mg. But I'm going to do something a bit smarter over here. I'm going to not find mass. What I'm going to do is I'm going to write W as mg, and then what I can do is I can basically cancel the mass terms on both sides of the equation. So I don't even have to find mass anymore. Now I'm going to get this new equation, which is going to be g equals omega squared r. I can rearrange this for omega, so this is going to be g over r. This is omega, and then you take the square to the other side, it's going to be a square root. So now I can put in the value of g, which is 9.81. Let me just solve this. So this is going to be 9.81 divided by 0.13, and I get 8.68, which I can round off to 8.7 rads per second. And that therefore I have proven that the angular velocity, or the angular speed, is basically 8.7 rads per second. So that's it for part 2. Now, the last part says the chord and the mass rotate so that the chord is vertically below C as shown in figure 1.3. So now they start to mention figure 1.3. Now they say that this mass is right below point C. Okay, and what we have to do is we have to calculate the length L of the chord, assuming it obeys Hooke's law. Now, this was a 4-mark question. Okay, so I'm just going to put that over here. This was a 4-mark question. Now, some of you may go ahead and say, well, I already know that it's going to be 0.148 meters or 14.8 centimeters. I already know that because they give me figure 1.1, and in figure 1.1 the mass is right below that center point C, and the length of the chord is 14.8 centimeters or 0.148 meters. Therefore, that must be the case for figure 1.3 as well. And I want to tell you guys that that is not in fact the case. The reason is because this is a stationary system. So this is a stationary system. It's a non-moving system. This is a circular motion system. Things that are true for the stationary system may not be true for the circular motion system. And in fact, in the circular motion system, the reason why the things are not the same is because check this out. So in a stationary system, this is your center point C, and you have, if you draw the free body diagram for this, you just have one force mg, and you have a tension force over here. So you have a tension force over here. And if you think about the resultant force in this particular situation, well, the resultant force is 0 because this system is stationary. It's not accelerating in any direction. It's not moving in any direction. It's a stationary system. So it's at rest. So it has no resultant force. F net is equal to 0. And that means that if F net is 0, then T minus mg must be equal to 0. The tension force minus the mg force must be equal to 0. There must be no net force. And therefore, that means that T must be equal to mg if you rearrange this equation and bring mg on this side. So it's a perfectly balanced system. Now, in the moving system, in the circular moving system, what's happening is you have a center over here, you have a mass over here, you have the force of tension over here, you have mg over here, in this particular situation, mg and tension force are not equal to each other. Why? Because a net force exists, right? This is a circular moving system. In a circular motion system, we always have a net force, a centripetal force. So that centripetal force exists. Now, what's the magnitude of that centripetal force? It's going to be the tension force, which is in the center, minus the weaker force, which is the weight force that is acting downwards. So you can see the equations happen to be different for both of these situations. Different forces are acting on these systems. Even though they're at the same position, in both scenarios, the mass is right below the center point C, the system isn't the same because the forces acting on the system are not the same. And due to that reason, the length may not be the same as well. Maybe more tension is acting in the moving system, and therefore it produces a greater extension, a greater extended length than in the rest situation. So ideally what can happen, and we do know that tension is greater than mg. So we do know over here that tension is greater than mg. And the reason for that is because in order for us to have a centripetal force Fc, tension must be greater. Tension must balance this mg force, and then it must have some extra component that is gonna be the source of this centripetal force. So tension is greater than mg. If tension was not greater in mg, then mg would have been the stronger force, and mg is not acting towards the center, it's acting away from the center. So we wouldn't have a circular motion in the first place. Make sense? And so what we can sort of extrapolate from this is that the tension acting over here is equal to mg, the tension acting over here is greater than mg. Now, what does that mean? That means that a greater tension will produce a greater extension. It will create a new extended length that is going to be greater than the extended length of the stationary system or the system at rest. So that's why it's not 0.48. It's probably going to be greater than 0.48 centimeters. Now, what our job is, we have to find what that extended length is. We don't know how to do that right now. No problem. What do we do when we don't know how to do problems? We start off with the second law. We start off with the free body diagram. So so we have the second law. What second law are we going to use? So check this out. We're going to use, we already know the angular speed, and some of you may argue that, well, we only found out the angular speed for when the mass was at the top. How do we know the same angular speed applies when the mass is at the bottom? And you can go over here in the question statement, and they say that they are rotating at a constant angular speed. So that means that the angular speed is not changing. The one you found at the top, you can use that at the bottom. Now you know the angular speed. You're trying to find the radius r. So what's the radius r? Radius r is basically going to be this new length, this length L that we're trying to find. Okay, because it's going to have some different value over here at the bottom position. That's what we're trying to find. So we know the omega. We're trying to find the r, which is this new length. We can find out the mass. We also know the mass. So the mass we can find out using this particular equation over here. We can use W equals mg. W is equal to 5, and then g is 9.81, so you can divide it on this side, and you get this equation for mass. Now, you can sort of round it off and find a decimal value, but that's going to make you lose accuracy. I don't want to lose accuracy, so I'm just going to write mass as that fraction, 5 over 9.81. Now, I know the mass, I know the angular speed, r is what I'm trying to find. If I can find out the Fc, so Fc, where's my pen? Fc equals m omega squared r. If I can find out my Fc, I already know my m, I already know my omega, I can then find out r. You would not want to use the equation m v squared over r, because see, then you would have to do the extra work of finding that v squared. You don't know what that v is. So rather just not use that equation over here. So this is the plan. I know that I'm trying to find that r. That r is basically what my new length L is. I can even write that over here. So that's what I'm trying to find out. So that's the second law equation. What about the free body diagram? Let's draw the free body for it. So the free body, and I've actually drawn this over here on the side. The free body diagram is basically Fc is equal to T minus mg. T is the stronger force minus the weaker force. So I have Fc is equal to the tension in the rope minus mg. Okay, so now I can sort of even simplify the free body equation further, or you can choose to not simplify further. It completely depends on you. But right now, see, I know that the tension in the rope is, do they tell me the tension? I don't think they tell me the tension. So at point 1.3, we are not given the tension. Okay, that's no problem. So we don't know the tension. That's fine. So we don't know the tension, but we know what mg is. So mg is basically what? Mg is equal to the weight, right? And what's the weight? The weight is basically 5 newtons for that object, right? For that piece of mass. So we can put 5 over here. Let me just check. I think they did tell us tension. Let me just see this again. Okay, no, I don't think they tell us what the tension is. Okay, so we're not given the tension. So we just have Fc equals T minus 5. So what we can sort of do now is we can just combine these equations, and then we can get, because you can't simplify this any more than what I already have. So that would just be T minus 5 equals to m omega squared L. Okay, T minus 5 equals m omega squared L. Here's the problem. I'm trying to find length L. I know everything except for this tension force T. But what do I do about this? What do I do when I do not know my tension force? I'm trying to find the new length L. Well, here's something you can do. So what is this tension? This is basically the tension in the rope, or the force in the rope, right? There's a rope. That rope has some force in it, and we call the forces in rope tensions. So this rope has some tension. Now there's a formula that you guys may have studied in your springs chapter. That is basically F equals KE. Now, you don't know what your F is, right? You don't know what your F is because what is F? In this case, F is tension, right? The force for a rope is what we call a tension. So you can replace the F with a T. You don't know what the tension is in this rope. Do you know what K is? Yes, you can find out K. How can you find out K? You go back over here to that first situation, to that figure 1.1, and I told you guys explicitly that the only reason they give you this situation is so you can find out K. And the way you can do that is you can do F equals KE, and so the force that was applied over here was just the mg, and so tension is over here. This is a stationary system, so tension is equal to mg. So you can put the tension in the rope is equal to ke, and the tension is going to be 5 because tension is equal to this mg. Mg is weight. Weight is 5 newtons, so tension is also equal to 5 newtons. You're trying to find out k. You know what the extension is because you can minus the new length and the old length. So that's going to be 0.018 meters. And what you can do is you can divide the extension to the other side, so you get 0.018. Now, I would not recommend you to go ahead and sort of try and convert this into decimals because, again, you are going to lose accuracy. We're going to use this k value in our next step, and if you convert this into decimals, then you may lose accuracy. Whether you convert it to 3 significant figures, 4 significant figures, you're still going to lose some accuracy. So just leave it as that fraction, and then when you're putting it in your calculator in the final step, just put in that entire fraction in your calculator. It's going to do the job for you. So I know what k is. So tension is equal to k. K is 5 over 0.018. I don't know what my extension is, right? If I go at this bottom position, I don't know what my extension is. So this, I probably know that this was some old length, which was 0.13. I don't know how much it extends. I don't know that extension. Well, guess what? You don't need to find that extension. Here's what you can do. So extension is basically the length L, which is the new length, minus the old length. And therefore, what you can do with that is instead of extension, you can simply write L minus 0.13. So now what you have is it may not be as obvious to you right now. It may not be clicking to you right now. But something over here that you can do is you basically have two equations. You have two equations. This is your first one. This is your second one. You have basically created a two equations, two unknown system. And this you can solve. You can solve by substituting one equation into the other, and that will do your trick. That will allow you to solve this equation. Now, one of these equations came from your knowledge of circular motion. The other equation came from your knowledge of the spring chapter, right? The spring chapter and the Hooke's law chapter. So what I'm going to do is I'm going to merge these equations and I'm going to find that value for L. Now, I don't want to find tension, right? In the question, they don't ask me to find the tension. They ask me to find the new length L. And therefore, what I can do is I can take this tension value, substitute into the first equation. And if I do that, I get 5 over 0.018 times L minus 0.13 minus the value of mg, which is 5, equals m, which is, I know the value for m, we found that out. So that was 5 divided by 9.81 right over here, 5 divided by 9.81. So that right there is 5 divided by 9.81. And I know the value for omega, that is 8.7 rads. I square that, and I have L over here. Now, see, I have one equation and I have one unknown. I have this L and this L, which I can get on one side of the equation, make it the subject, and then solve this equation out. So you can actually see how many different steps this question sort of involved. It wasn't just a circular motion problem. It was a Springs Hooke's law problem. It was understanding some intuition problem. Then it was creating a mathematical system of two equations, two unknowns problems. That's the math over there. And right now it's turned into a diabolical algebra problem. This is going to be a lot of algebra, and we're going to be doing that. So what can I do over here? So in fact, one thing I want to do is maybe let's let these stay as m omega squared. Now you can solve these out, but I don't want to involve numbers right now because solving in terms of variables allows you to make less mistakes. So I'm just going to let it be m omega squared. I'm going to solve out the left-hand side right now, and let's see what we get from that. So I get 5 over 0.018 L minus, so 5 times, what's 5 times, 5 divided by 0.018 times 0.13. So that gives me 325 over 9. 325 over 9. Again, I'm not sort of rounding anything off right now because I want to keep this as accurate as possible. And then this is going to be negative 5. And then this is going to be m omega squared L. And then what I can do is I can basically get the L terms on one side of the equation. First, I can solve this out. So this is going to be negative 325 divided by 9 minus 5. That's going to be negative 370 over 9. And so I can send this term to the other side because it has an L, so I can send it over to that side. So when I send it over here, I get m omega squared L minus this new term, which is 5 over 0.018 L. Okay, and what I can do is now you can basically substitute in the values for m and omega squared, and then you can sort of minus these two values because they both have L, or here's something else that you can do. And I'm going to do this because, again, I'm trying to keep as much accuracy as I can. So I am going to factor out this L, and therefore I'm going to be left with m omega squared minus 5 over 0.018. And then what you can do is you can divide all of this to that side of the equation. So it's going to be negative 370 over 9 divided by m omega squared minus 5 over 0.018 equals L. So now I'm going to use my calculator. I'm going to chuck in the values for m omega squared, see what I get. So this is negative 370 over 9 divided by, what's m? So m is 5 over 9.81, omega is 8.7 rads, and we square that minus 5 over 0.018. That gives us negative 239.1997961. Unfortunately, I didn't get a fraction for this value when I solved it out on my calculator, but sure, no problem. Okay, so now we have to divide negative 370 divided by 9, and we have to divide this number by negative 239.1997961. So when I do this, I get a value for L that I can round off to 3 significant figures. So that is going to be 0.172 meters. Okay, so I had everything converted into SI units when I was finding out L. So my final unit, I don't have to worry about it. It's going to be in meters as well. Okay, so that is my length L. That is the new length at the bottom position, length L. And you can actually see, so you can give this in centimeters or you can give this in meters, because in the question, see, they had the length in centimeters. So they gave you the unextended length as 13 centimeters, then they give you the extended length 14.8 centimeters. And now if you want to convert this length into centimeters, you can just multiply this with 100. So that will be L is equal to 17.2 centimeters. And you can actually see this length is greater than 14.8. And I told you guys, we predicted that. That's because tension in a moving system is greater than tension in a stationary system. And so more tension means you're going to have more extension. Now, we just proved this, and that is it for this question. I believe this is the 5th question that we're about to do, and let's just get into it. It says over here that a large bowl is made from part of a hollow sphere. A spherical ball is placed inside the bowl and is given a horizontal speed. The ball follows a horizontal circular path of constant radius as shown in figure 2.1. So basically we have a bowl, and inside of that bowl they're making a ball spin in a horizontal circle. And what they tell us is they tell us the radius of this horizontal circle. Let me just write that over here. That is 0.14 meters. We're just converting that into SI units right now. Okay. Next part says the forces acting on the ball are its weight W and the normal reaction force R of the bowl on the ball as shown in figure 2.1. So they say there are 2 forces that are acting on the ball. One of those forces are the normal reaction force R, and the other force is the weight force, which is W. The next part says the normal reaction force R is at an angle theta to the horizontal. By resolving the reaction force R into 2 perpendicular components, show that the resultant force F acting on the ball is given by the expression W equals F tan theta, where W is the weight of the ball as they tell us in the question statement. And we have to find out that the resultant force is basically, it has an equation where the weight is equal to that resultant force times tan theta. Now, I know that's a lot of stuff going on, and it's right now it may be just hard to sort of even think about it or sort of even begin to answer this question. Here's what I want you guys to do. Why don't we use some of the knowledge that we already have to sort of figure out the knowledge, sort of deduce the things we can from the knowledge available to us. So right now, see, one of the things that they tell us that the large ball is made out of a hollow sphere, and that the ball is placed inside the bowl and follows a horizontal path. So it's moving in a horizontal circular path. What does that mean? So that basically means, think about it like this. This ball is not sort of moving up the bowl, or it's not going down the bowl. It's staying at a constant level, sort of just moving around in this circular path. This piece of information is going to be important to us in just a second. The next part says, or basically gives us a free body diagram for the ball, and only 2 forces happen to act on the ball: the normal force and the weight force. Now see, since this ball is moving in a circular path, where would its resultant force be? So, or will it have a resultant force? And yes, it will. Why? Because it's moving in a circular path. When you're moving in a circular path, you have a resultant force acting in the center direction. Okay, so there is actually a force that is acting in the center direction, which we call the centripetal force. So in this case, what they're doing is they're actually calling that the force
F. Okay, so they don't say FC, they're just calling it F. That's the resultant force they're talking about. The resultant force that's going to make this ball rotate around in this circular path. Now, what do we have to do? We have to sort of give them an equation that is going to be W equals F tan theta. Now, you may be like, well, do I apply? I don't know what to do. So do I apply the second law, and do I apply the free body diagram equation? Well, you could do that, but then see, in this question, they already help you by telling you what you have to do. So look, read the phrase. What does it say? By resolving the reaction force R into two perpendicular components, what are going to be the two perpendicular components, the X component and the Y component, show that the resultant force F acting on the ball is given by this expression. Now, we don't know how to find that expression, but they already tell us how to find that expression. They're saying break the force down, break the normal component, break the normal reaction down into its two components. Here's how we can do that. So we have a ball. I'm sort of going to represent it with a point over here, and it has a weight. So I'm going to put its weight over here. This is mg. Now it has a force, a normal force, this guy right over here. So this is r. We can break r down into two components. So one of them is going to be this one, and the other one is going to be this one. Now, if you use some trigonometry, you will find out that if this angle is theta, this is going to be r tan theta. So this is the horizontal component of the what do you call it? So or let me just do it like this. The horizontal, or the x component, you'll find out that it's equal to r cosine of theta. And since you can sort of imagine the vertical component is right over here, and then what I can do is I can sort of pick it up from this position, and I bring it over here. Okay, I put it over there. So this component, this vertical component that I've drawn over here, is in fact a component over here that I've picked up, and then I've put it over here. So this side, what is this side going to be equal to? This, if you do some trigonometry, you will find out that this is going to be r sine of theta. So what I can write over here is I can basically write r y is equal to r sine of theta. Now, since I have sort of split my normal component r into my normal force r into its two components, I can sort of erase r. Its job is done. I don't need it anymore. So now I sort of just get this diagram over here. From this diagram, see, this is exactly what they tell you to do in the problem statement. If you read the problem statement, it literally says by resolving the reaction force component. We've resolved it into two perpendicular components. Perpendicular components basically means that these two components are 90 degrees to each other. The vertical is 90 degrees to the horizontal. Now, how do we do the next part? So for the next part, we have some equation. Now, we don't know how to get that equation, but basically we can get some equations from this diagram itself, from this free body itself. And the way we can do that is we basically, if we neglect the vertical direction, what we can see that in the central direction, because the ball is going to be moving in a circle like this, right? In a circle like this, and so the center is going to be somewhere over here. So if we think about the central direction, the resultant force that we have over here is going to be Fc equals Rx, and since Rx equals r cosine theta, I can just write r cosine theta, and I can say, hey, look, Fc is equal to the reaction force times cosine theta. Now, what do they call this F? They're not. What do they call this Fc? They're calling it F. If you look at the symbol over here, they don't call it Fc. They're just calling it F. Therefore, what I can do is I can just call this Fc F. So F is the resultant force, and F is equal to r cosine theta. Now that is basically an equation for the centripetal force. If you realize, this equation is not the equation they want us to show. They want us to show an equation that has weight, F, and tan theta. It does not have r, and it has tan theta instead of cosine theta, and it also has a w. I don't have any of that in my equation. I just have F equals r cosine theta. How do I bring w into this equation? How do I bring tan theta into this equation? How do I do any of that? See, for that reason, they made you split the r force into two components and not one. They want you to sort of focus on this other component as well. And what I can sort of do over here is instead of writing mg, usually we write mg, but in this case, what I want to do is I want to go ahead and I want to write w. Why? Because they say that the weight is given by this component, this letter w, and then in this equation, they have a w, not an mg. So what I'm going to do is I'm just going to write a w over here. There we go. Now, in the vertical direction, is there going to be a resultant force or not? So think about it. Read the statement, think about it. And there's actually going to be no resultant force. No resultant force. The reason for that is because if you read this line over here, oops, I was not supposed to do that. If you read this line over here, it says the ball follows a horizontal circular path, meaning it's not going up or down, it's at that position, and it's just sort of rotating around. So what does that mean? That basically means that if you don't have any movement in the vertical direction, that means there's no force, no resultant force that's causing any movement in the vertical direction. So there's, in fact, no resultant force in the vertical direction. Therefore, there is no movement in the vertical direction. And what can be deduced from that? What can we create from that? What can we express? How can we express that idea in math? So we can say that no resultant force no resultant force means the resultant force is equal to 0. And therefore, how do we even find a resultant force? The way we would find a resultant force is we can say, well, resultant force would be, let's say, ry minus w, or you can say rf is equal to w minus ry. It doesn't matter what you write and what you don't, because in a second you're going to see it's pointless, because the rf is 0, there is no rf, and so instead of rf I can write 0 over here, and then I get this equation, and if I rearrange it, I basically find out that weight is equal to that vertical component of the normal force. And that is exactly what we just said over here. There is no movement in the vertical direction. The ball doesn't go up or down. What does that mean in math? That means that the forces are perfectly balanced with each other. Forces are not greater or are not smaller, and so we get W equals Ry. Now, instead of writing Ry, I know what Ry is equal to. It's equal to R sine of theta, so I can bring in R sine of theta back over here. Here's what I want you guys to notice. You have two equations now. If you could just somehow link them together, what you could actually do is you could get an equation that includes W, that includes F, and isn't that what you want to do? Aren't you trying to get an equation that has W, that has F, and that has a tan theta? Now, how do you do that? You basically look at the fact that there is no R in this equation, and that's your entire hint. Since there's no R in that equation, you're supposed to use this R term to sort of combine these two equations together. They both have R, right? So what you're going to do is you can take this equation right over here, or you can take this one. It doesn't matter what equation you choose, and you can make R the subject. So over here, if I make R the subject, I get R equals F over cosine theta. And now I can get rid of this R by substituting its value into this equation. So that's going to be W equals, instead of R, I can write F cosine theta, and boom, no more R anymore. And then I get a sine theta over here. And you're like, wow, that is so magical. My equation almost looks like the one up there. It has a W, it has an F, but it has a tan theta. How do I get a tan theta? Well, see, this fraction is being multiplied with this sine theta, correct? So you can write it like this. F sine theta over cosine theta. And guess what, guys? This thing, sine theta divided by cosine theta, is basically equal to tan theta. And so you get W equals F tan theta. Boom. You have showed whatever you wanted to show. Okay. Part 2 says, state the significance of the force F for the motion of the ball in the bowl. So which one was the force F? The force F was basically this force over here, this force right over here. Or in other words, it was the horizontal component of the normal force, because we found out that the force F, or the centripetal force, is equal to R cosine theta. So they're basically asking us, what is the significance of this force F? So this force F, where does it point? It points in this direction, right? It points in the central direction of a circular path, right? This ball is moving in a circular path, and this force F acts in the center. So it basically provides the centripetal force. It's the source of the centripetal force. So what's the significance of the force F? It provides the centripetal force for the ball. That's its significance. Part B says the ball moves in a circular path of radius 14 centimeters. For this radius, the angle theta is 28 degrees. Calculate the speed of the ball. Okay, this 14, we don't like that, so we're going to change it to 14 meters, 0.14 meters. And as you can see, the speed over here also has the units of meters per second, so we definitely want to change that centimeters into meters. Now, so you're trying to find the speed. So you can, sure, go ahead. There is a second law formula that allows you to find speed, so you can go ahead and use that. So you can say F, and I'm not going to say FC this time, because in the question they're saying FC is basically F. So I'm just going to write F. So F is equal to mv squared over R. And guess what? I don't have to draw a free body, because I've already drawn the free body. I've already resolved the components. I've already done all of that. And at the end, I come down to this equation. So this equation right over here. Now, you might be tempted to say, well, I don't want to use this equation. Why don't I do F equals mv squared over R? And then look, I have this equation over here, this big equation over here that I found out. And this equation basically tells me that my force is equal to R cosine theta. So why don't I take this information, and why don't I combine the two and get mv squared over R equals R cosine theta? Why don't I do this instead? And well, you can try and do this, but you're going to come across a problem. The problem is you don't know what the mass is, and you are not given the weight, so you cannot find the mass. There isn't a mass m term on this side, so you cannot cancel the m's out either. What about the radius? Well, you do know the radius, but you don't know the velocity, or you don't know the speed. That's what you're trying to find out. You don't know the r either. So how are you going to do this? How are you going to solve this? You don't know 3 things in this equation. That's a huge, huge problem. So that's the entire reason why they make you find out an equation in part A over here, because that equation is going to help you find your speed. Now, how is that equation going to help you? Well, you already have the equation over here. You can rearrange this to make f the subject, and if you do that, you're going to get f equals w over tan theta. And then from here, what you can do is you have this equation right over here, w over tan theta, and you have this equation right over here, and you can basically combine these two. So that would give you mv squared over r equals w over tan theta. Now, you don't know the mass, you don't know the velocity, you don't know the weight. So you still have these unknown components, but here's what you do know. You know that the weight W is basically equal to m times g. And so what you can do is if you write mg over here, you don't need to know the mass anymore. You can simply cancel out this mass with that mass and poof, they're gone. Now what you have is simply g. You know the value for g, you know the value for theta, you know the value for r. You can go ahead and you can find velocity. So let me just rearrange, sorry, you can go ahead and you can find speed. Let me just rearrange the equation for speed. So it's going to be v squared equals rg over tan theta, and then you take the square to the other side. So you're going to get v equals under root rg over tan theta. That's going to be equal to, what's r? R is 0.14, g is 9.81, and what's tan theta? Tan theta is tan, and they already tell you the angle theta, that is 28 degrees. So you can put the angle theta in here. Pop your calculator out. So this is going to be 0.14 times 9.81 divided by tan 28. And you get an answer of 1.61. I'm rounding it off to 1.61 meters per second. So that right there is the speed for the ball. Okay, we got question number 6 over here, and this is a fairly old question. I believe it's from 2004. It says that a particle is following a circular path and is observed to have an angular displacement of 10.3 degrees. Express this angle in radians, show your working, and give your answer correct to 3 significant figures. So you're basically supposed to go from degrees to radians, and we learned a formula to do this. So we have 10.3. The way we're going to do this is we're going to multiply this with pi over 180. You could multiply it with 2 pi over 360 or pi over 180. They both do the same thing. So this is going to give you 0.180. I believe that's what you get if you round off. Let me just check that. 10.3 times pi over 180. Yeah, it's 0.179, and then you round it off to 3 significant figures as you're told, and you're going to get this value. This is in radians. Part B says determine tan 10.3 to 3 significant figures. So tan 10.3, you do this in your calculator. Make sure your calculator is in degree mode because this is 10.3 degrees, and you're going to get, you round it off, you're going to get 0.182 as your answer, okay? Part 2 says, hence calculate the percentage error that is made when the angle 10.3 degrees as measured in radians is assumed to be equal to tan 10.3. So they're basically saying you have this thing, this angle in radians, and you assume that this is equal to whatever tan 10.3 gives you. Now, unfortunately, 10.3 gives you 0.182, which is not equal to 0.180. So these two things are not equal. And so they're saying find out the percentage error between these two values. Now, the way you find percentage error is basically you find the difference between the two values of how different the values are from each other. And then what you're going to do is, so the difference, let me just find out the difference. It's going to be 0.182 minus 0.180. That's going to give you 0.002, and then what you're going to do is you're basically going to take this difference value, divide it, so take this difference value, divide it by what the actual value is, 0.182, and then times it by 100%. Now, some of you may be like, well, why don't I divide this by 0.180? Why am I dividing it by this value? Well, because see, what you're doing over here is you're making the radians equal to the tan 10.3, not the other way around. So if you were assuming the value of tan 10.3 to be equal to the radian value, then you would divide it by 0.180, not 0.182. But since you're assuming it to be equal to the tan value, therefore you're going to put the tan value in the denominator. And so what you're going to get from this is we can sort of solve this out. So 0.002 divided by 0.182 times 100. So you can round this off and you're going to get 1.002.
0.1%. That right there is going to be your percentage error. Okay, so we finally have the last question over here. It says a telescope gives a clear view of a distant object when the angular displacement between the edges of the object is at least 9.7 times 10 to the power negative 6 radians. What does that mean? So it means that basically, imagine if you're on Earth and you have a telescope over here, so something like this. So right here is your telescope, and you have an asteroid over here. So it's basically saying that these edges, so this edge and this edge right over here, should be making an angle over here that is at least, so that is at least 9.7 times 10 to the power negative 6 radian. If the angle is smaller than this, then this object will basically not be visible to you from this telescope. Okay, so part 1 says the moon is approximately 3.8 times 10 to the power 5 kilometers from the Earth. Estimate the minimum diameter of a circular crater on the moon's surface that can be seen using a telescope. So basically, let's say we have a moon over here. So instead of being an asteroid, let's imagine this is the surface of the moon, and this is some crater on the moon's surface. And then the edges, so this basically right over here, this would be some crater over here. Let me just give it some more realistic effects. So this right over here would be some crater over here. Okay, and then over there as well, because the moon's surface is obviously closed. And so what's going to happen over here is they're asking for the diameter, so basically of this, the width or this part of this this crater. And what you have to do is you have to find however much that length is, and they tell you that moon is approximately 3.8 times 10 to the power 5 kilometers away from the Earth. So what you can do is you can they already give you an angle, so they tell you an angle, and they tell you how far you are away from, how far the moon is from the Earth. So essentially what they're doing is they're also sort of telling you this length and this length, which is you can technically think of it as a radius. Try and think about it like this. You can sort of make a circle over here, boom, and this telescope could be the center of that circle, and then you would have a radius going over here, and they basically tell you that that radius or that distance is 3.8 times 10 to the power 5 kilometers. Now, of course, this is not what's happening. This is a completely different situation. We don't have a circle over here. None of that is true. But the situation is similar to if you have a circle, and you can imagine that circle has a center point at the telescope, and then you have this angle 9.7 times 10 to the power negative 6, and then the circle has a radius 3.8 times 10 to the power 5, and you're supposed to find sort of this arc length over here, and that arc length in our situation would then represent the diameter of that crater. So the way you can do that is you can basically use the formula A equals R theta, and the arc length over here is what's representing our diameter. So this is going to be 3.8 times 10 to the power 5, and we're going to turn that kilometer into meters. So how do you change a kilometer into a meter? Just multiply it by 1,000, which is 10 to the power 3. So I take this value and I multiply it with 10 to the power 3, and then I multiply it with that radian value, which is 9.7 times 10 to the power negative 6. Now you solve all of this in your calculator, or actually you don't even have to do this. So you don't have to convert it into meters, because the answer is actually in kilometers, not in meters. So that's good. So you just multiply 3.8 times 10 to the power 5 with 9.7 times 10 to the power negative 6. And this gives you, so this gives you 3.686 kilometers. You can round it off. I'm just going to leave it like that. Part 2 says, suggest why craters of the same diameter as that calculated in part 1, so of this diameter, 3.68 kilometers, but on the surface of Mars, so it's the same diameter, the crater has the same diameter, but now the planet is Mars. So we have the telescope over here, and now there's Mars over here, and it's a crater of the same diameter. But now we're trying to, so this is Mars, so we're trying to measure it for Mars. So they're saying, why is that not visible using this telescope? Well, see, the main reason is because Moon is much closer to Earth. So the crater appears way bigger on the Moon than it does on the Mars, than it does on planet Mars. That is because Mars is further away, and so it looks smaller. And so the problem is, in the first line of this question, they basically tell us this tiny piece of information that says that objects are only visible in the telescope if the angle they create is at least 9.7 times 10 to the power 6 radians. So maybe things of the same diameter over here are able to create that angle of 9.7 times 10 to the power negative 6, but maybe things that are far away create an angle even less than that. So it's not enough
It's not enough as this much, and therefore you cannot see the object. Now, you can also look at this from an equation perspective, where you have the A equals r theta, and A is constant because they both have the same diameter. So A is constant, and therefore what you can do is you can rearrange this equation for r and theta. So that would be I can take r and theta to opposite sides of the equation. So now I have 1 over r times the arc length equals theta. And since the arc length is constant, I can sort of take this term to be 1 over r is directly proportional to theta. So what does this mean? This means radius is inversely proportional to angle, proportional to the angle. And what that means is the further away you are, the smaller your angle is. And therefore, it doesn't matter if they both have the same diameter. Since Mars is further away than Moon, the angle Mars produces over here is less than what is required for visibility. So you can sort of write that over here. You can write that the angle that the crater of Mars produces on the telescope is less than 9.7 times 10 to the power -6 radians, and therefore the crater isn't visible on the telescope.